Hello, hello, hello. Yes.
We can do it.
We can do it. We can start it. Great. Whoa, this is amazing to see so many people here. Who is here for Bitcoin? Okay, just kidding. Just kidding. Oh, blockchain. Oh, no, just kidding. You can also stay. Everyone is welcome here. So we are really welcoming in Munich. Who actually is not from Munich? Wow. Okay. This is pretty amazing. Great. This is good to see. Cool. So who is outside from Germany? Still a lot. Wow. Well, really cool to have you all here in Munich. And we're happy to to host you here at this this event, made possible together with the Bitcoin Munich community. I would say. I mean, it's like it started as something, like the idea to do a meetup, but it grew into, as Michael loved to say, it grew into something bigger, and now we call it a conference. And yeah, so it seems like the interest here is high. So probably, well, maybe we're going to do it again. But let me hand over to Michael now. And then we go through some organizational details and stuff, and sponsors, of course, and then we will hear the first speakers.
Yeah, thanks, Daniel. Also, warm welcome from me. Daniel is also a long-time member of our Bitcoin community, and he also did a lot of organizing stuff here. And we also have a moderator today, Claudia. She's not so much into the Bitcoin technical stuff, but she's very agile and will help us organize the crowd here and also take Q&As and all this stuff. So, and I think she also has some words to say to us. Claudia.
Hello from me as well. Thanks for having you here. It's great to see so many of you. We are here in the rooms of JetBrains. They have an event space for just those gathering. And we thank very much for hosting us here and for sponsoring some food and stuff. Thank you so much. And for all of you, who don't know JetBrains, you can check it out on the website www.jetbrains.com, and they are hiring as well. We got a nice plate over there, and you can see it on the screen, some job offerings if you want. JetBrains is developing software for the developers, so they help you to do your job. All right, that's for that. And then as well, we have here somewhere, we have Andre. He is from the Bitcoin crypto community in Stuttgart and Köln, and they're sort of supporting us, the Bitcoin Munich team here, also with sponsoring us. So also please clap your hands for that. Okay, in between we have some breaks. We're going to tell you when you're supposed to do what. And for now we have three speakers. And the first one is going to be Konstantin. He's going to talk about Let's Play Lightning. So Nick, Where are you? Please get your mic over there. All right. Okay, and after that talk, you can ask questions, or in between, let's say what he's going to tell you. Yeah. Cool.
No, it's not working. Ah, yeah, now it's working again. Okay. So just one organizational stuff here. I mean, I think it's mostly men here. So and we only have one toilet for the men. So especially in the pauses, this might be a problem. And I guess when we ask the three girls in the room, if it's okay that we can share also your toilet. Is this okay for you? Yes, okay, great, perfect. So please, yeah, close the door and please be nice and leave the toilet clean afterwards. And so one additional thing, I mean, you have probably recognized that this event is for free, so yeah, you thanks. I mean, this is possible thanks to all the sponsors and, of course, people from the community who put a lot of work into this. But this also means it's not like it's not that professional as you might experience it at other conferences. And for example, one thing we couldn't manage to organize is the coffee. So I'm very sorry for that, that we couldn't organize the coffee. We couldn't find a sponsor, actually. So now it's too late to ask for a sponsor if someone is interested. But if you need coffee in between, there's a Hit supermarket downstairs and some other like localities around there where you can grab some coffee or anything else you are missing here. Yeah, so good. I think we can start now. What do you say? Konstantin, are you ready? Okay. you get all the moments you need. Hast du es angemacht? Ja. Welches hat er?
So, is the audio on here?
Yes.
Is it fine? Can you hear me or closer? Closer.
Welches Mikro hat er? Hier.
Now better? Not better. Maybe I should just carry it.
Welches hat er? 1 oder 2?
All right, so thanks to coming from a presentation. Let's play Lightning. So I have been working on building games and gaming infrastructure with Lightning for about a year now, so pretty early in the Lightning days, but I think we've come pretty far in this year. So today I want to share with you why I think that gaming will be one of the first markets which Bitcoin can totally penetrate. So I want to motivate you to maybe think about creating games or a lot of its needed infrastructure. So if you have any questions, just feel free to raise your hands. So gaming today is weird, I would say. So on one side, it's like super creative and you have super cool games. And so my childhood was, you know, it was shaped a lot by cool games like, I don't know, Pokemon and stuff like this. But right now it's in this, I don't know, uncanny valley where there's so many shitty payment systems. You buy currencies from developers, you know, this mobile games examples where you buy gems for $70 and They call it microtransactions because you will only spend 500 gems in one transaction. But then there are other games where you can buy assets directly from the developer, but mostly through a marketplace, which take about 30% of fees if you look at the App Store or Play Store, Steam, whatever. And what also pisses me off is, okay, now you have an asset, you have this cool gun skin, it's worth between $3 and $19, but actually you can't sell it. You can sell it for some currency, maybe for some Steam dollars, where you can buy new games, but I don't know, if I don't want to play the game anymore, it's wasted money, I would say. So, what could we do to fix that? It's easy, I think. A lot of developers, they took their time to build solutions for this, and they came up with shitcoins. So, in the last years, a shit ton of shitcoins appeared. I mean, you probably know some of them. You don't know any of them, probably, because they are marketed directly towards gamers. And I don't know if I need to point out their mistakes, but I don't know. They're not decentralized. They're not fungible. They have no liquidity. They're basically the same as those shitty diamonds. They have no proven ecosystems or developers, and the tokens have one use. I mean, Skincoin. What is it for? For skins, maybe? And I mean, they're all get-rich-quick schemes. So what should we use? Of course, Bitcoin, and specifically the Bitcoin Lightning Network. So I don't know, I cannot explain the Lightning Network here, so the gist of it is that it's a second-layer scaling solution for Bitcoin, and it relies on payment channels to allow for peer-to-peer, low-fee, lightning-fast, and scalable transactions. Wow, Lightning is really cool. And I think it has a lot to offer for games. So Lightning payments for games could mean a lot of things. So I thought about some of them, but probably everybody has its own vision what can be done with Lightning on games. So permissionless peer-to-peer payments, sending and especially receiving, because that's totally new for games, would be a novelty. It could change existing monetization models and create also new ones that are not thought of today, because we didn't have microtransactions before, just shitty diamonds. So peer-to-peer payments have been possible with Bitcoin before, but I think, I don't know, the high fees basically and confirmation times, they're not used for, cannot be used for a playful environment, I would say. The next thing is microtransactions. So again, to the diamond example, if I paid $70 US for some currency, and the smallest transaction I can do with that is in the $1 range because I need to spend 1,000 diamonds for some things, then I wouldn't call it a microtransactions. But it's called microtransaction in gaming, but I hate it basically. And Lightning, we can now send real microtransactions. Maybe we should call them nanotransactions, I don't know, because we can send them in the sub-cent range. I mean, what's 1 Satoshi now, or even milli-Satoshis? And again, this would lead to new gameplay mechanics, which I will show some later of. Now, what's really cool with Lightning and Bitcoin especially is assets. So in the gun skin example from before, you have seen that, okay, there is a demand for items in games and they have some value. And if we want to create metaverses, or I don't know, the Matrix, we need to have a way to trade assets. Unfortunately, now we have stuff like the RGB protocol or Liquid or Counterparty, which is starting to integrate Lightning soon, I think. And they could enable that the stuff that gamers do in their games, that it has a real world value, which would be totally new. But what we also could think about, and I know it's not a light word to think about centralized database for games, because games are centralized anyway, so we could have a quick way to do asset trading maybe next year, and gamers could use Lightning and Bitcoin. But more importantly for us, what would gaming mean for Bitcoin? First of all, it would bring in a lot of users and use cases. So I don't see a reason to buy stickers or t-shirts on the Lightning Network, because I can do it with anything basic, with cash, fiat shitty, but with gaming we can have some like real new technological solutions for stuff that hasn't been possible before. And I think if we solve some of gaming's problems with the Lightning Network, it's the users of the gamers need to go to the Lightning Network. So, I don't know, if you look at Steam, it has 67 million monthly active players. If we could just capture, I don't know, 1 million by this year, it would be amazing for Bitcoin. The liquidity it would bring to Bitcoin. So gamers today, they have no problems spending their money, and for us hodlers, it would be awesome that we get some spendlers. And the chicken and egg problem is, okay, we need game developers, because game developers are super creative and they are used to work with technological boundaries. Like we've seen before, they didn't have good graphics back in the days, but they still created awesome games which a lot of people wanted to play. And also, games are a super testbed for Lightning, like this centralized database I talked about. We can try to implement an eCache style system, which we wouldn't want to do today we wouldn't want to test it with real world assets, but with gaming, we wouldn't even care, I think. And also, one of my personal goals is that when we get like real desktop PC games, we also have the possibility to let users run a lot of full nodes, which would also help secure our ecosystem. But Lightning still has a lot of challenges we need to solve. I don't think we should try to reach out to Bitcoiners, especially with games. I know there's some overlap in Bitcoiners and gamers, but I think Bitcoin is fun enough that we onboarding and education. I think it's super important. Even if they have Bitcoin, Lightning is still so new and it's not easy to set up, I would say, and you wouldn't expect the average gamer to just run a full node for their first entry in Lightning gaming. And I think this is where stuff like Neutrino and maybe also custodial services will come in handy. And also channel management. I don't know how deep you are in Lightning, but it's pain in the ass, and we now get services like Thor, which will help us, and we will get stuff like, you know, the open node service where we can run our own custodial wallets for our services, but it's still a huge pain in the ass. And if we want to cater to the average user, we need to find a way to distribute it. So I will show an example later where a Lightning game will probably, maybe, hopefully, release on Steam, or it's trying to release on Steam. So how will the old marketplaces react when we find a way so that they don't get any fees? We need to find a way to circumvent that. And also, with a great payment system, we need to find a way to have cool gameplay. We cannot expect, okay, now we created poker on top of Lightning. I don't see a reason why a normal poker player would start playing poker on Lightning. I think we need like innovative stuff, like new ideas, so that we can get, so that there's a reason to come on Lightning. Yeah, that we find, I don't know how to say it, but just new payment and monetization ideas for games, I would say. And one of the biggest challenges in games, especially if we now have financial incentives, we need to find a way to shut down cheaters and bots, which is still a problem in gaming today, and I don't see how we solve it. But if we have a, you know, if the gameplay doesn't allow for cheating, if the payment model doesn't have an incentive for cheating, then maybe we can play around it. So some projects I want to show. There are, I think, a lot of cool gaming projects on Lightning right now. I don't know all of them, but I want to show you two today, which are using Lightning, and they're trying to solve the problems I mentioned. And yeah, I think they're solving them pretty good. So I'm starting off with Lightning Chess by Koala Studios. It was released, I think, 2 weeks ago, and it's it's basically chess with the added gameplay mechanic that you can wager bets against your opponent. You can wager on yourself that you will win, or you can offer the other party satoshis so that you will get extra time, or so that you can undo your move. And the prices, they are defined by yourself, and they can be as low as 1 satoshi, which is pretty cool. It is a web application, and it doesn't require any form of full node, so it's a custodial service, and it's built with OpenNode, which I showed you before. And it lets you basically deposit and withdraw satoshis with Lightning. For onboarding, they use a voucher system, which is pretty cool. So you can redeem vouchers, and I have some with me. So if you want some free Bitcoin giveaway, I can give you some. It's free satoshis. And you can redeem them on their website, and then you can start basically playing. But there is a caveat that it's chess. Chess has been beaten in the 80s, I think, I don't know. But you have to trust the other party that they don't cheat you. You basically, at the moment, can only play it with your friends or people you trust at least a little bit. Or you're cheating yourself, then it's fine. Who built the better bot? And now I want to shill my personal project, of course. So the stuff I've been working on since the last year is called Donner Lab. It's like a startup we built here in Germany, in Darmstadt. And we started with creating an open source Lightning plugin for the Unity game engine, which is the biggest engine for small to mid-sized teams. And as it is with a lot of open source projects, no one started using our project. So we had to create our own game, basically. And it's the first game I ever created. It's called Donner Dungeon. And it's an action brawler where you, the player, play against viewers from around the world. Like, the idea is that you play on Twitch, for example, or YouTube, or even in a local meetup, and your viewers, they will pay you to send you monsters. And so they get sent the invoices in Twitch chat at the moment, but we'll also have our own website where you can request to buy monsters from the viewers. So let me show you a short video. So this is from a Twitch live stream. And it's basically, okay, you can see this person, LA Eagle, he sent me a payment, so then now I can fight against his monsters. And yeah, here's some satoshis I earned. I earned 58 satoshis. And Lightning Koala sent some payments there. Yeah, it's like an action game. And the idea is that there is no incentive to cheat because you want to entertain yourself, you want to entertain others, and basically at the moment, because only you are playing as the streamer, there's no way of, if you cheat the game, no one will start paying you because it's boring for them as well. So we are on Steam. It's the biggest PC gaming platform, and we're trying, because for onboarding it's also out. Okay, now because the streamer, he needs to have his own node running, so he can generate invoices which are distributed via the IRC or Twitch chat. And I don't know, so we were thinking, okay, how can we solve the problem that, first of all, how do they get a node? How do they get channels, inbound capacity? And the way we think we will do it right now is we will ship a wallet, probably a neutrino-based wallet with the game, so that the users, that they have an entry in Lightning, and when they buy the game, we will refund them some of the price back in Bitcoin as a channel, basically. So they can start the game, we will open a channel up to them. Then the cool thing, because, okay, we need to be aware of chargeback risks, but Steam takes care of chargeback risks, and after 2 hours, they cannot refund the game. They can send us a request, and we will pay them like €5 back in Bitcoin, and then they have outgoing capacity, incoming capacity, and basically can start playing the game and also paying others who have the game. Yes. So the other stuff, because our game is not open source, unfortunately we cannot do this, but we're building more. For example, we have a Minecraft server plugin, oh, the quality is a little bit shitty, where you can, for one, pay invoices so that you, for example, can teleport in the game, so the cool thing, we can render QR codes directly to in-game items. If it gets paid. Yeah, this is teleport. So I set my home to the mountain area and paid for the invoice, and now if I pay for the teleport to go home, I will teleport back to home. So this is super fun, and the cool thing about it is that only the server needs to be running a Lightning node, for example, and the users, they can just use their mobile wallets, which I think are easier to integrate. And for some infrastructure stuff we're working on, so I started to stream every Monday some Lightning Chess and Satoshi's games, some other platforms, and we found, okay, even if I would have a lot of viewers, which I don't, I would want to have a way to give them a lot of, to hand them out Satoshis. So we created a voucher system, which is basically just a link you can click, and you have this web wallet stuff, and there are 100 Satoshis on it, so that's basically it, and it's super easy. And all of this is open source. And you can find it on our GitHub, which is on this website. So thank you for the organizer, thank you for having me, and do you have any questions?
Awesome.
There was a question.
Yeah, maybe it's a microphone. No?
I can repeat.
Okay, maybe I just ask
ask if the microphone comes.
Who wants to ask
First? Okay.
I was hoping I'm not the first to answer the question, because it's not directly about lighting, but about the game. So I heard what some game items sell for a lot of money.
Yeah.
So is there a work to allow to sell the game items or other assets via hash time lock contracts? Like where the pre-image is somehow allows you to claim the...
Okay, I forgot to mention two things. One, because you can sell assets for a lot of money, I forgot to mention this, but it's only on very scammy websites. And I forgot to mention about Minecraft, we use a trade system where if I want to sell an item, I say to the Minecraft server, okay, I want to sell this item, and this item will vanish from my inventory, and other users can request the invoice, which I attach to my item, and if they pay it, and they pay it peer-to-peer directly to me without the server knowing, if they paid it, they can claim the image from the server with a pre-image, basically, if that was...
But I mean, this is true lighting.
Yes.
Yeah, so what for $10,000, some unique sword. Yeah, is there a...
Sure.
Yeah, but they can do like hash time lock contract where the pre-image is something that gives you access to this, and do it at once, like atomic swaps, but with game items. Is there a work in this direction? My question.
Not from us or me,
okay.
But it totally makes sense what you're saying, because yes, maybe we don't have a sword for $10,000 today, but maybe tomorrow. I don't know. If we have real world value in games and metaverses, we need
probably some decentralized exchanges for stuff like this will appear, and the next speaker might have some answers for you.
Yeah.
Some more questions in here?
So I'm not too much into gaming, but I was wondering how the current distribution platforms see stuff like that. So is it allowed to have payments like this on Steam, in the Apple Store, whatever, or are they like very close to that?
I don't know, actually. Twitch hasn't shut me down yet with my 20 viewers, but I think maybe they will try to. But I looked through the Steam license stuff, and I didn't find anything about it. And I mean, still, if they buy the game from us, they will get 30%. So that would be. But if it would be free to play, I don't know. They they could be pretty pissed, but then we get the Streisand effect, so that's fine as well, right?
Cool. Some more questions? We have some room for questions still, if there are some available. If you want to ask some. Okay, here. Over there.
Thank you. Last year, I think the game Fortnite made 2.4 billion in revenue.
In earnings, I think.
In earnings, yes.
Yeah.
They have a purely inbound payment channel, and if I'm not mistaken, when you play, you can also earn diamonds, whatever. I don't remember the term exactly. If you create a system where the gamer has the possibility to mine through his gameplay an asset, that would be quite disruptive. How do you think those big players would react?
I don't know. So, first of all, I don't know how you would mine the asset, because then you would basically, if you assign it a Bitcoin value, you would basically be mining Bitcoin in a way, because you would earn Bitcoin by playing, and then it would be try to be exploited by bots.
No,
so
I misexpressed myself. I use the term mining just because you're generating a value in the
I
game.
see.
Okay, like
I think
what I mean is that when you play a game, say for example Candy Crush or whatever, you gain points. Those points you can use them for whatever skin. In your system, would you be thinking about also creating a value through the gameplay itself, not only by receiving rewards or donations from other players?
Yeah, probably. If you think about like online games where you can, I mean, if you kill a monster, you get a sword. It has a real world value if you can trade it with Bitcoin. And I think I don't know how the big players will react. Yeah, that will be the cool part for every gamers. How the current developers will think about it, we don't know. And I mean, I think they would like it because it gives them their game so much of a value.
It incentivizes the whole thing. I mean,
if it doesn't change their current monetization, if they still have their old monetization where they just get a payment stream, I don't know, for playing and for buying skins, but
I think there are some deeper questions. Maybe you talk after or in the pause directly to each other. This might make sense, I think.
Which Lightning implementation are you using and why?
We're using LND. Why? Because it's the only one that runs on Windows, basically. And yeah, we need to use Windows. That's the reason. Eclair runs on Windows too. Sorry, Eclair. Yeah, we use because gRPC has a super cool integration with Unity, so that's also a reason why we use LND.
I have maybe a similar question. There are already blockchain-based game hubs like Loom or Steemit, and you can also build a unknown coin like the Hunter coin. But what are the advantages of the Lightning Network to build a game?
I mean, so first of all, it runs on Bitcoin, which is sound money, which has liquidity, and second of all, Lightning Network. And I don't think games on Bitcoin or on a cryptocurrency that uses proof of work with the security of Bitcoin could work in a gaming context. So we need a layer for gaming, I think. Especially for microtransactions, and they need to be fast because you want to directly see the trade.
Yeah, but the other are also blockchain based. The other I mentioned, they're different blockchains. But what is the advantage of the Bitcoin blockchain?
Yeah, I don't have anything to say to that. I'm just looking at Bitcoin.
Yeah, I think this was quite good explained in the beginning why you're looking at Bitcoin. But are there some more questions, or also one more? Okay, great. So last question for this talk.
This has clear advantages for the player, but what do you think would be the incentive for developers and for stakeholders to implement such a system?
Yes, we're looking in this as well, because right now, if you look at, for example, Fortnite, you cannot compete with Fortnite. It's free to play, And so if you create a game similar to Fortnite, and if you charge money for it, nobody will play your game. So you need to make it free to play. And then we need to find a way so that developers can make money from us gamers. And the traditional way would be, okay, you can buy stuff from, like skins like before, but you could also think, okay, now if you think about Lightning specific stuff, everybody connects. If I want to pay you, we play the same game, we would both open a channel with the game developer, and he could take the routing fees, for example. Okay. Or he could be some sort of watchtower for our stuff. So you could think of some ways where you could leverage the Lightning incentive models also for games and game developers.
Okay. Cool. Thank you so much, Konstantin.
Thank you.
Okay, we're gonna have the second speaker here, Kilian Rausch, and he came all the way from Madrid, from Spain. He works for the Exchange Union as a product director, and he's gonna talk about atomic swaps on Lightning. And here he's gonna address the biggest problems we have here. Of course, hopefully delivering some solutions on that. And well, it's gonna take just a minute, and he's gonna be here. Great to have him here, and I hope you guys enjoyed the talk. After that, we're going to have questions and answers. All right, we got it?
There we go. Okay, thank you. Before I start, actually I want to do something different. So we have 3 talks treating Lightning in a row, and I just talked with René in the back. None of us is actually explaining what Lightning is, so maybe we should do that. So here's a try. So there's a little bit improvised now. What is Lightning? First of all, Lightning is Bitcoin. Lightning is just a different way of how Bitcoins get assigned from one person to another person, meaning they get transferred from one person to another person. So there's something called on-chain and something called off-chain. So Lightning is the latter one, off-chain technology. And what it is, metaphorically speaking, so Lightning basically takes Bitcoin out of the underlying blockchain and puts it in a so-called payment channel. And the payment channel only exists between 2 people or between 2 nodes. And this is how coins get transferred, is basically that these 2 people, these 2 nodes, reach a consensus what the balances are. So if both of us agree that I send 1 Bitcoin to him, the transfer actually happened. And the effect of that is it doesn't need to be included into a block. It is instantly fast. It is as fast as the connection between the 2 of us is, which is usually a matter of milliseconds. And that's it. So what Lightning basically does, takes the Bitcoins out, puts them in a payment channel, and enables nearly instant transactions. And that's why it's especially useful, for example, for gaming or for any other payment-based use cases. So just that we did treat the topic of what Lightning actually is. Okay, I'm Kilian. Thank you for the introduction again. I'm at Exchange Union. I'm doing product there. And I'm talking about atomic swaps on Lightning. And I'm also talking about a major problem which still has to be solved in order to make atomic swaps on Lightning work for a decentralized exchange. Just get a snack, yeah. Is that mine?
Ja. Zeg maar een kabel.
Ik heb helemaal normaal. Okay, so why I am interested, can you guys hear me? Yes. Okay. What I'm interested in all this, in atomic swaps on Lightning as well, because at Exchange Union we are building a decentralized exchange protocol for centralized exchanges on the Lightning network. Why the hell would we do that for centralized exchanges? That sounds pretty counterintuitive, right? Well, we also plan to build it for individuals in the long run, but there's this thing called liquidity, and that's why we're targeting centralized exchanges in the first stage in order to leverage the liquidity, which for 99.9% is on centralized exchanges at the moment. But the end game, of course, is that every individual who runs the software, which we call XUD for Exchange Union Daemon, is part of the network and can trade with everyone else in the network, let it be an individual or users of an exchange. Okay, let's start with atomic swaps, the concept. What is an atomic swap? An atomic swap is a trustless exchange of two different assets, whereas trustless is defined that there is no middleman or no escrow service holding funds at any point. And how's this trustless characteristic achieved? By guaranteeing the atomicity of a trade. So the atomicity of a trade always consists of two transactions. I give you A, you give me B. And an atomic swap basically binds these two transactions cryptographically together so that the A transfer is only valid if the B transfer is also valid. If one of them is not valid, the other one is neither. So none of them is valid. And the technology used here is so-called hash time lock contracts, of HTLCs for short. I think we have heard them before in the previous talk. And here's a visualization of how this looks in practice. So basically, for Exchange Union, we had two exchanges, of course, A and B, which integrated XUD. And step one is A creates a so-called pre-image, which is a random number, a random string. Could, for example, take entropy from the def random function on Unix systems, and yeah, it's basically just a randomly generated secret. Then it hashes the secret and creates a transaction with this hash, which puts 100 LTC in this example into a special wallet, which we just call a lockbox here. And this a lockbox with this transaction is configured in a way that it only opens if the before generated pre-image is presented and the signature of B. And that's called a hash lock and stands for the H in HTLC. Then we have B. B does the same. A sends over the hash of the pre-image to B, not the pre-image itself, just the hash, that's the difference. And B takes the hash and creates also a transaction which puts 1 Bitcoin into something we call B lockbox. And after this, B lockbox is configured in a way that it only opens, so it means the funds in there are only redeemable if somebody presents the pre-image and A's signature. Observation: both lockboxes need the same pre-image to be opened. So now A wants to get its funds. Say, okay, I see this 1 Bitcoin is successfully locked in the lockbox. So now I go and insert the pre-image and sign with my signature in order to get the 1 Bitcoin out of the B lockbox. And in order to do so, A has to reveal the pre-image on the blockchain or on the payment channel in our case, and exchange B knows about it and says, thanks for that one, now I know the pre-image, now I can go and sign the transaction, insert the pre-image and sign the transaction to get the 100 LTC out of your lockbox, of A lockbox, and the atomic swap happened. And there's a second thing to it, which is called a time lock, which stands for the T and L in HTLC. By the way, there will be a link to the slide, so if you don't want, you don't have to take pictures. We'll in the end. Maybe I should have said that before. So if something goes wrong, somebody's stalling the trade or becomes unresponsive, there's a certain time interval where both funds get refunded back to A and B, so out of the lock boxes back to them, in case something goes wrong. So that's a T and L in HTLC. And that's why they're called hash time lock contracts. And they're defined in BIP 199 on Bitcoin, and they are more or less native to Lightning, because Lightning uses HTLCs for the routing through different intermediaries. So BIP 199, HTLCs are defined in scripts, so basically using a couple of opcodes. And on Ethereum, they're also possible, actually, but in the form of a smart contract. And now it gets a little bit technical. This is how an HTLC with Bitcoin scripts actually would look like. So if you're A, from our example before, who's the creator of the pre-image, you use actually the first branch, the op-if branch here, and you would insert the pre-image and sign with your pub key in order to spend the transaction and get your output. If the time lock occurs, we're in the op-else branch, then basically the funds will automatically get refunded after a certain number of blocks, after a certain amount of blocks. And that's the general concept of atomic swaps. Now I'm going to switch over to atomic swaps on Lightning and what is special about them, and also the different phases we were going through while implementing them. So first we took LND because somehow it's somewhat mature Lightning implementation, and we tried to make LND itself multi-chain capable. In our case, Bitcoin and Litecoin, obviously. So, but we gave that up pretty quickly because we started to change major parts of the code base, and it got crazy. So we gave that up pretty quickly because even the chances that this will ever get merged into the master branch, they were close to zero. So that someone like Lauda would approve to merge that in, this was like simply not realistic. So we took a different approach with the goal to have minimal changes to the Lightning implementation, LND in our case. And this is how it looks like. So basically we have XUD, our open source node, and it manages 2 LNDs. So it manages one for Bitcoin and one for Litecoin. So LND itself is not multi-chain capable, but we have a special LND for LTC and a special LND for BTC. And we configure the LNDs also in a special way, but also this doesn't need a lot of changes to the code base. It's actually a couple of lines only. So the only special thing these LNDs do is, when they receive a payment where they don't know the pre-image for, they will query an external service, which is XUD in our case, and ask for the pre-image. That's the only thing that is needed in order for atomic swaps to work with LND. Assumptions here in our setup is that we have payment channels between all these guys here, and also that they are having sufficient funds in the payment channels. Also, we assume that somehow XUD blue and XUD red are able to communicate with each other, which they are with a special protocol we developed for this. And then the atomic swap starts. Step 0, the trade is negotiated. So blue is wants 1 Bitcoin, is offering 100 Litecoin, and coincidentally red wants 100 Litecoin and is offering 1 Bitcoin. So blue XUD goes ahead, creates the pre-image, hashes the pre-image, and the result is something called R hash on Lightning, and it starts with 3151. Step 1, proposal to XUD red. Let's make an atomic swap using R hash 3151. Then XUD checks internally, is the amount still available? Is that everything still valid? Is the swap proposal valid? And it is, and says, okay, acknowledge, let's go ahead. Step 2 is then XUD creating a pending HTLC of 100 LTC with this R hash from its blue LTC LND to the red LTC LND. Pending HTLC is because the coins actually didn't move yet, because the pre-image is still missing. And a little note here, this setup is actually the real amazing property here, is that in between here there can be any number of intermediate nodes. So there can be actually a route in between. It does not have to be a direct channel. And then the case that we predicted happens. The red LTC LND receives this incoming pending HTLC, but doesn't know the pre-image for. And then our if applies. If this happens, it will query an external service and ask XUD, what is the pre-image? At that point, red XUD doesn't know the pre-image neither, but it knows this one belongs to a trade I negotiated with the blue XUD before. So in order to get the pre-image, I have to go ahead and create a second pending HTLC using the same rhash on Bitcoin. And that's what it does. It creates a pending HTLC of 1 Bitcoin to the blue BTC LND. And then the same thing happens again. The blue BTC LND does not know the pre-image. So it asks XUD, what is the pre-image for the Bitcoin transaction with rhash 3151? And this time, blue XUD knows about it because it is the creator of the pre-image. So it tells the pre-image. So it lets BTC LND know that the pre-image is MVH set blah blah blah. The pre-image is revealed and the payment got settled. Through this, also red XUD learns about the pre-image. The pre-image does like basically one round back to the blue XUD, and both payments got settled. And this is how we do atomic swaps on Lightning. And again, the note in between the LNDs, there can be any number of intermediary nodes. If you're somewhat technical, you can actually try to do that on your own. So we put together a quite comprehensive guide. It's available at this link. You can just Google for SimNet, maybe Exchange Union SimNet guide. I think you should be able to find it. Takes you like half an hour. We automated some of the setup, and you can actually do this swap on your own. Okay, that's about it about atomic swaps, but there's a but. The but is actually in step 5. What happens in step 5? Step 5, recall, is right before XUD would reveal the pre-image in order to settle the trade. But instead of doing it, instead of revealing the pre-image, XUD does this. It waits and watches the LTC-BTC exchange rate up to the timeout that was agreed previously. This is minimum a couple of hours, sometimes even a week, which I think is a default in Lightning. It's like 1,000 blocks. So the timeout is quite long, and XUD can use this time and watch the exchange rate of BTC to LTC. And if the LTC versus BTC rate went up, it will just wait for the timeout to expire and to get its LTC back, and then sell them somewhere else for now much more BTC, so basically for a much better rate. If the LTC price against BTC went down, it will just go ahead right before the timeout, release the pre-image, and settle the trade. Because then it's a pretty good deal. It gets more through this trade than it would get anywhere else on the market. And in financial terms, that's called an option. An option is the right to execute a trade or not, so it's not an obligation, it's the right, in the future. And the real problem here is it's for free. So in traditional financial markets, an option, basically you have to pay a premium in order to have the right to do something or not in the future. Lightning is constructed in a way that payment failures, which in our case are the canceling of the atomic swap, is for free. That's why it's called, or at least I called it, the free option problem. I don't know if that's a common, if people already agreed on that name, but that's my name for now. It's called the free option problem, and it's a real problem for us. Good news is, this is already conceptually solved for on-chain atomic swaps, meaning atomic swaps, the same concept happening with on-chain transactions. Bad news is, it's still unsolved for atomic swaps on Lightning, which is a big problem for us because that's what we do. Okay, conceptually solved how? So I'm quickly walk through how the rough concept, I just read about it a couple of days ago, so maybe you guys can help me out if I struggle here, but I try to explain how some researchers try to solve this on-chain through punishment. So basically, both A and B are required to stake a collateral in the target asset. So if I'm A, which was the blue XUD, looking for BTC, I have to stake, I have to deposit BTC in an additional HTLC that uses the same pre-image, so the same hash, which gets unlocked with the same pre-image revealing procedure than the atomic swap itself. And the result is that both would get the collateral back if the pre-image is revealed timely. So if we look back, we look at our construction, actually we were missing something before. So if we would draw in all op-if paths, it would actually look like this, where we have op-if in the case of successfully revealing the pre-image, and we have op-else where a refund happens back to the origin if the timeout occurs. So what this proposal now does is it puts in additional collateral, in this case of Bitcoin, because that's the currency the Blue XCD is looking for. And this collateral is stand back, so basically refunded back to Blue XCD in the case XCD reveals the pre-image timely. If it does not so, it will be sent over to the red XCD. And the trick here is that this collateral, as maybe call it collateral transaction, belongs to the same transaction than the atomic swap itself and is signed by both. So it's basically ensuring that if the atomic swap goes through, then the Blue XCD can rest assured that it will also get its collateral back. So why not do the same thing on Lightning? Well, in my opinion, there is one big problem. And I call it how to uniquely attribute fault, or to how to be sure that who did something wrong. That's possible on a blockchain. So a blockchain basically can just watch and see if XUD redeemed this transaction and made this transaction effective. So the blockchain itself knows that this transaction happened. Then the blockchain itself also can take care that the collateral transaction also will be activated, but not so on Lightning. On Lightning, transactions are private, like I introduced before, because the transaction is private between two parties. Even if it's a couple of nodes, intermediary nodes, it's always private between two parties. So the collateral transaction basically has the problem that in the case the timeout occurs, one party will be saying, hey, timeout occurred, but the other party will be saying, no, the timeout didn't occur. So the collateral transaction doesn't know whom to listen to because there are only two. So, and an additional thing is needed. So we would need an effective timeout of a couple of seconds. If we want a decentralized exchange to behave like and to compete with centralized exchanges today, it has to be fast. So the timeouts also should be shorter. So timeouts can't be a couple of hundreds of blocks, which means hours or even days. So the timeouts should rather appear in a couple of seconds in order to mitigate the risk of volatility of the exchange rate. And if you're interested in reading more about this, there's actually a pretty good summary of this CM guy on the Lightning mailing list. He summarized it, and it started in late December 2018, and people did jump in quite actively in early January 2019. But up to now, it is still unsolved. So now we would need you and other bright minds in order to jump in and think about the problem and basically join the discussion. So for this one I opened a specific Gitter channel. I just did it yesterday, so there are not that many people in there yet, but I tried to gather some people there and make it a place where we can discuss about this problem and about approaches how to solve it. So you're invited to join this channel, and basically we'll also help people to really understand the problem and then to work on it. As promised, here's the link to the slides. So it's basically in our GitHub under docs. So that's where you find all these slides. And that's it from my side. Thank you.
Right. Hello? Hello. Okay, cool. Thanks, Kilian. Let's switch microphones here.
Okay, any questions on that? No. Okay. Here.
Oh, sorry. Thanks. I was wondering, did you already
think of something like hedging for centralized exchange, hedge BTC when they're putting BTC in the contract, for example. So it's not on the LND or on Lightning or on BTC, but because they're an exchange, they can put in positions that hedge their hash time locked contract position, maybe.
Like a collateral, right? So they have to put up a deposit and...
Yes.
Yeah, we're actively thinking about that. Since it already solved the on-chain problem, we are thinking that way, that collateral somehow solves it. But the problem here is how to judge who did something wrong and who didn't. That's the main problem, because everything is happening privately in these payment channels. We can't tell with 100% certainty who did not reveal timely or who says who revealed timely. So that's the main problem to solve. But yeah, it goes into direction collateral, the current way of thinking.
One thing in between, sorry. Maybe the guys who are sitting near the windows, can you please open the window a little bit so that we get some fresh air in here? And also for the viewers on YouTube, if you have questions, just type them in. I will forward them.
Okay, so you're doing a decentralized exchange on Lightning. So probably if there's for the exchange, for centralized exchange, so probably they want to exchange big sums. Is there a problem for channel liquidity for them?
Yeah, good question. So at the moment, the channel capacity is limited to 0.16 Bitcoin, but that's only an artificial limit. I think it's called training wheels, so that people don't put that much money in, because Lightning itself is not 100% mature yet. So there is no real limit for channels. There's even something in the work, I think, René, how's it called? Bit, I think, from Laura, right? So there's something that increases the channel capacity. And in the case, let's say I'm in a big exchange, and I know my users will quite often trade with the other big exchange. I can open a direct channel with the other exchange and put in as much money as I need, basically, as much funds as I need. So there's no technical limit on the capacity.
Yeah, but you don't need Lightning now. You have direct channel.
Direct channel still solves the trust problem. So a direct channel makes sense for exchanges, actually, or for parties I quite often transact with.
Why would they need your decentralized exchange now, if they can just make it a direct channel?
Well, they have to negotiate trades. So what our system does is basically it helps them to negotiate the trades and then automatically settle the swaps. Lightning itself is Lightning. It's pure Lightning, right? So we don't even want to touch Lightning. We want it to be as is. Yeah.
Hi. Here. One remark and a question. So first of all, I would like to believe that the free option problem is more of a theoretical nature, because eventually in the free market, this free option will be priced in the exchange rate. So, for example, in local Bitcoin, the exchange rate is usually always higher than on the average exchange you can see. So this could eventually be solved in the moment we implement and actually see the exchange rate.
I hope so as well, actually, so I'm totally with you there. So maybe we go out there and it appears that it's not a real problem because it just happens to be in the exchange rate. But then there will always be situations where this premium that somebody priced into the exchange rate is less than the volatility that actually occurred. But yeah, it's a possibility, but we know that theoretically at least it's there.
And my question is, have you looked into other cross-blockchain atomic swaps on Lightning? And have you eventually looked into cross-blockchain atomic swaps on Lightning which have different elliptic curves?
Different elliptic curves. Something like, so basically enable cross-chain swaps.
Bitcoin Monero, for example.
Monero, okay. So for starters, we'd need a payment channel. And actually, it's not depending on the elliptic curve. It just depends on that somehow the HTLC outcome somehow has it's a compatible HTLC. That's all we need. So the two chains that are swapping with each other need to have a compatible HTLC.
Okay.
And a payment channel, of course, which Monero, I think, doesn't have yet. Maybe something is in the works.
No, Monero doesn't have that yet.
Yeah,
yes.
Exactly. It needs a payment channel and an HTLC to work together.
Thanks.
So for example, Ethereum will work. That's actually something we're currently actively doing. We are developing with Brainbot on Raiden, so that actually Raiden itself will have compatible HTLCs in order to actually swap with us. It's not because we're big fans of Ethereum, which we're not. It's more about like stable coins, so to have like to have fiat in the system.
I got a question that it's about the legal side of your business. I'm still
the legal
side. I'm wondering a little bit, since the central banks understood that they can't really enforce new customer requirements on decentralized exchanges. I learned that the SEC started to going after the developers of decentralized exchanges. Is that something that already affects your work, or how do you deal with that problem?
Well, as far as I'm concerned, we are an open source protocol on GitHub. If somebody downloads the code and does something with it, it's their responsibility. It's the same thing when our target users, the exchanges, actually integrate this, our software. It's down to them to obey any local law or any local regulation. I mean, obviously, we can't take care of any regulation or regulations in so many different jurisdictions. So in the end, it's down to the people using the software to obey the law. It's actually the main reason why it's designed in that way. We even, for example, the peer-to-peer layer is also directly peer-to-peer. There's nowhere a central party. For example, other decentralized exchanges, most of them have a central matchmaker, a central matching engine. We don't have that for this very reason. We don't want to be operating anything in order to not be liable for that.
Actually, that's exactly the problem that the SEC solved by going after the guy who developed on GitHub a decentralized exchange. Like
I doubt that this is possible.
That's what they did.
Then they should also go after every Bitcoin Core developer. I mean, I think we're good from that side. Yeah, don't live in the US. That's a good idea.
Don't go there.
Yes. So why don't you use two different pre-images? So one pre-image for the BTC node, one for the LTC node, or is the problem of ascribing blame because there's routing in the network? The nodes don't have direct payment channels. Because, I mean, the XUD kind of like knows everything, and in this way you could ascribe blame, couldn't you?
Well, if we used two different pre-images for the respective chain, let's say one for BTC, one for LTC, I don't think it would be an atomic swap anymore. So an atomic swap has the basic principle that's basically one of them is creating it, and if one of them releases it, both sides of the trade settle. So if we have two pre-images, basically one side is releasing it, and then the other side is like, thank you for the money, and walks away. So that would be, somehow we find a way to mitigate that, but I think this would be redesigning atomic swap, so yeah.
If you see this problem similar to options,
yeah.
The second party in this exchange has all the information needed to calculate the premium. So it knows the delta, it knows the theta, it knows the volatility, so I can just factor that in.
But you have to factor it in the beginning. That's the problem.
When I receive the opening transaction.
Yeah.
So I received the transaction. Sorry. And I know, for instance, I have 3 days. Then I can just factor in the premium would be this and that.
Exactly. That's basically what we had over there. It's like in the end it will be just in the price. The premium will be included in the price. Okay. So if everybody agrees, let's say the whole network has a timeout of 3 days, then everybody just calculates their own price. What is it, the risk for 3 days volatility? What is worth to me? And that's what I price into my offer. Hopefully that's what's going to happen. But yeah, nobody knows.
Okay, one last question. Christoph, do you still want to ask a question? No? Okay, not anymore. One more question. Over there. Okay, 1, 2, 3. 3 questions. I think you don't want to. I mean, you were the first. Okay.
So you have the idea to reduce the timeouts to like 10 seconds, but doesn't that invalidate the block timeout tree, basically?
It's not possible nowadays. As I said, what we need is ideally something like 10 seconds, but it's not possible nowadays because at the moment the time lock is based on a block, and since, as we all know, the average block time is about 10 minutes on Bitcoin, so it's not even possible to do that. But we would need something.
But what would that be? Is there something that you have in mind, that you have an external time oracle or something that you use, but then you still reinvent HDLCs, basically, right?
You reinvent time locks, and you basically make yourself dependent on another third party, on an oracle. So I'm personally not a fan of oracles at all because they can be compromised. It's really, really hard to have these decentralized oracles and take an average out of them, and I don't know what. Like, we could do that with a time server, basically, that everybody trusts a set of oracles of time servers. We thought about that. Not sure. Join the discussion. Okay.
Any last questions here? That's you.
Are you also looking into atomic swaps between a Bitcoin sidechain and Bitcoin? And do you think this makes sense at all?
Would work the same way. It doesn't matter if it's a main chain, side chain, 3 degrees in there, it doesn't matter. As long as there's a payment channel and a compatible HDLC, it works. So Liquid itself, for example, Blockstream's Liquid could also have that. Rootstock, was it SBTC, RBTC, would also work if they have Lightning, like real Lightning at some point.
All right, thank you for their questions and thanks for the talk. So we're going to end up this round now. Okay, you can ask your questions, of course, later in the breaks. And now we have René here, Rene Pickhardt. He is a Lightning developer. He works as a freelancer or self-employed in Koblenz. And he knows a lot about that. He talks about the Autopilot as the new chance for the Lightning Network. And he's about to write a book, actually, an open source book. And he's dealing with the Lightning Network, of course. And we will see when this comes out, but now he's going to tell us about what his learning is.
Okay.
Welcome. Thank you.
Hello, everyone. Microphone is working? This one?
No, it should work.
Microphone's working. Okay, perfect. So, first of all, don't take me too seriously yet. This is work in progress. I'm a data scientist, and this is research also. That's the reason why the talk is a little bit unstructured. The second reason is my notebook crashed, and on the way here I discovered that I planned to talk for 1 hour, but I only have half an hour. So I already know which slides to skip, so we're going to make this really fast now. So last year I was on the Lightning residency in New York in Chiang Labs, and this is a bunch of important people, and they all discussed that autopilot and routing is difficult. And I came to Lightning development pretty much 1 year ago when Blockstream released Lightning Charge, and I decided I have a friend who runs an Instagram channel and sells stickers, and I thought, hey, selling stickers with the Lightning Network is perfect, because she was using Etsy and has to pay like a ridiculous high amount of fees. We never managed to implement this, but I was spinning up my first Lightning node, and stuff became complicated, and I had to like dig down the rabbit hole. And then what I realized is pretty much this one. Yeah. Okay. Okay, so what I then realized about 2 weeks later is that LND has this thing called the Autopilot. And for those who don't know the Autopilot, what it does is it automatically creates payment channels with other nodes. So if you don't know with whom to open the node, you just run the Autopilot, and then you have like a bunch of payment channels open. And I looked at the source code of the Autopilot, and they use a model from graph theory, which is the Barabasi-Albert model. And I thought about this, and I thought, no, this is not a reasonable choice for reasons that I will explain. But I opened an issue on GitHub, and I asked about this. So the current Autopilot in a nutshell, as I said, it's a recommender system for nodes. It suggests which channels to which nodes to open channels with. And it's supposed to do this automatically. So how does it work in LND? So as I said, it's the Barabasi-Albert model, or as other people know it, as preferential attachment, which means the rich get richer. What this does is it's a random process. So it's basically rolling a dice, but it's not doing this with uniform distribution. Right? When you roll a dice, every number has equal probability, but the Barabasi-Albert model uses a probability distribution that gives a higher probability to nodes that already have a lot of channels. Right? So if you're a Lightning power user, if you're YALS, the chance is really high that people open a channel with you. Right? Which also seems reasonable for many people, because they say, hey, this is a node that already has a lot of channels, So if I open a channel with them, then I have access to many other nodes, right? This is great. The only problem is what happens if yours go down, and you don't have much access anymore, right? So because you destroy the network for a lot of others too. But still, if you run this in computer science, the result will be a graph with the following properties. First of all, it's scale-free, which is really nice because what it basically says is it doesn't matter how big the network becomes, the topological properties will pretty much always stay the same. It's very similar to how we observe social networks being built, right? So if you assume there is no autopilot at all, with whom would you open your channels? Well, probably with people you know or with your friends, right? Everyone knows them right now. So it's similar to social networking graphs. So I guess that's one of the reasons why they use this. Small networks, small world networks, they have a particularly small diameter, which means that the longest route in the Lightning network to go from one node to another is generally small. I think nowadays something like 5 or 6 hops, right? So this is really great because routing gets more and more complex as longer the routes get. So we likely have a high reachability, and we have a power law distribution of no degree. I have some videos, but I think they don't play here, so I skip them. How graphs look like this. I have a picture of them later, so it's no problem. What are the pitfalls with the LND Autopilot? As I said before, it creates highly popular hubs, and the problem is by the algorithm, the hubs will mainly have inbound capacity, right? So one big important concept about payment channels, I will just repeat this because the question comes up so often. If I'm running my Lightning node and I open a payment channel to James over there, then I can only send Bitcoin to James. James can't send Bitcoin to me. Right? Only after I made a certain amount of payments, now the balance is at James' side, now James can send Bitcoin to me, right? But many people always think, oh, I open a payment channel and I now can use it to pay and receive, but you can't do this directly. So if everyone automatically opens a channel with YALS, this is not so great because YALS now has a lot of inbound capacity, but you actually can't really route something forward, right? So it creates these inbound capacity hubs. Then also technically it could overwhelm nodes, right? So I have my node running, it's getting bigger and bigger, everyone sees me because I'm up there in my probability distribution, everyone opens a channel with me, and at some point in time I just have too many channels, which is also not so great for software like this. The next big problem is that the number of triangles in this graph is relatively low. I think here you can see this. So this is an automatically generated network with the Barabasi-Albert model. And what you see is you get these like power nodes over here, maybe this one, but you hardly see something like this that you have like 2 nodes connecting in a triangle. And what you actually want to have in a, I'll just go back to this slide, what you would have seen this in the video before. What you actually want to have is you want to have more of these triangles, because triangles mean that if any of these 3 nodes fails, you have a separate node. And the Barabasi-Albert model in general basically does not create triangles. I mean, some because it's a random process, but not too many. And then another pitfall with the LND Autopilot is that the created channels all have the same balance. So if you run the LND Autopilot and let's say you have like 1 Bitcoin in your LND node and you say you want to have 20 channels, basically you get 0.05 Bitcoins capacity for every channel, and that also might not make sense, right? You might want to have some channels that have high capacity, some channels that have lower capacity. Another pitfall that I don't talk so much in this talk about is that it doesn't even suggest the routing fees that you should use. Okay, so after I created this issue, Roastbeef answered to this, and he was like, yeah, this is a great question, and yeah, if you want to join in, here's an interface and you can implement this. And I was like, hey, this is great. I looked at it, and the problem is I don't speak Go, and I was not sure if I really wanted to go down this road. And then there's, well, then there's the other implementation, C Lightning, but my C is kind of rusty, so that's also, thank you. That was also a little bit of a problem. So yeah, I decided I first have to learn a little bit more about everything. So I started reading more of the bolts, I started reading source code, and then there was the second Lightning Hack Day in Berlin, which was announced on Reddit also. And I went there, I was finally having the chance to talk to some people from LND about the Autopilot, and I think we also had a small session there. I wrote a blog article about ideas for the Autopilot, and something else came up, which was that C-Lightning decided to create a plug-in system for C-Lightning nodes. So now it's possible to write plug-ins in a different programming language. And since this entire thing is like a data science task, and data science in Python is great, I was like, yes, I can do this in Python for C-Lightning. So this is what I did. So let's recap a little bit why it's important to think about the autopilot early. Right? So even with the Lightning Network, blockchain transaction will be precious. Right? We know that we can basically create or change 7 payment channels per second, right? Because this is how many transactions we can get into a block. That's 630,000 per day, right? And imagine if you grow the network for a couple of years and the network is getting really big and we use this Barabasi-Albert model and we get this, like, I would say, bad topology. At some point in time we realize the topology is not so good for the autopilot. We can't change the topology so quickly because it takes time to like close payment channels, make new payment channels, and then we maybe run into another problem where everything gets stuck in like, oh, there's too much traffic here and stuff is not working properly, right? So I think it's important. And routing success depends on the topology of the network, right? I mean, what many people already have discovered is that sometimes routes fail. That were all these like 5 pictures in the beginning that I was showing. And if you think about the problem with the Lightning Network, there's a lot of privacy encoded in the Lightning Network. Right? We don't give information about what the graph really looks like. We only know with whom people have channels. We don't know what the channel balance is. But routing really depends on the max flow min cut, which is a topological property we would have to compute in order to, even with AMP routing, where we do small payments, use the topology in order to make payments. So yeah, even with AMP routing, it's going to be difficult. On the other side, we say when we have less routing errors, we have better user experience, we have a better utility of the network, right? And we created the Lightning Network to have a better utility of Bitcoin. I think the first talk from Konstantin, he said Lightning Network is Bitcoin, right? So the only thing we do this is to have a better utility of Bitcoin. So my solution would be to say, let's grow the network in a smart way to avoid future problems. So I will skip these slides because they're critical anyway. It's not so important. So my first approach and first prototype, and again, I'm prototyping here. I have 4 different strategies for node selection. So I create a probabilistic model in the same way how LND does this, but I use 2 strategies which I think are very good for the user. And the first strategy actually is the Barabasi-Albert model of LND, because for a particular user, as we discussed in the beginning, it's probably still good to connect to a highly connected node. And the second one is to respect centrality. I will explain this in a second what this means. But then I have 2 strategies which I personally think are healthy for the network. Right? The first one is try to decrease the diameter. Look which nodes are really poorly connected and connect to them. Right? Give them a chance to like participate in the Lightning Network. And the other one is called the Rene model, which basically means I randomly connect to a node. Once I have these 4 strategies to generate candidate sets, there's following an estimation or suggestion for balance of the channels. So let's look at these 4 strategies. One word, the Barabasi-Albert model. I have already discussed this, so I don't repeat this again. It's basically creating a probability distribution that is proportional to the amount of channels that are connected to the nodes. And the Rene is just randomly with a uniform distribution, just like rolling the dice connecting to anyone. So also that one I don't explain in detail. We have to discuss a little bit about betweenness centrality. Just for me, that I know how many people are aware with the term betweenness centrality. Okay, so I really have to explain a lot here. Thanks for brevity of not raising your hand. So what the betweenness centrality does, if you take one thing out of this talk today, you should take home that betweenness centrality is like one of the most important properties of the Lightning Network. Right? For example, if you want to earn a lot of fees, you should aim for your betweenness centrality. And it's actually quite easy. It's just hard to compute, that's the problem. So what we do is, we take all pair of nodes that exist in the Lightning Network. And for each pair of nodes, so these 2 nodes, we compute the shortest path between them. And then for each node, we count on how many shortest paths this node lies. right? So my node could lie on, let's say, 100 pairs of nodes that have the shortest path. And then we compute the relative frequency. So we divide this number by all paths, or by all shortest paths, or basically by the number of pairs, which is basically n squared. And this is the between centrality, right? So I am more central in the Lightning Network on the more shortest path that goes through my node. That's basically the between centrality. So what this means is that nodes that have a high between centrality can reach many other nodes quickly. Right? So if you think about this, it might make sense to connect to a node that has a really high between centrality, right? Which might already correlate somewhat with nodes that have many channels. But if you do the calculations, and I brought some diagrams, there are sometimes nodes that have just like 20 or 30 channels that are really having a good between centrality in the network. And it makes so much more sense to connect to those nodes than to connect to somebody who's just spamming channels. So yeah, connecting to such a node is desirable. So the strategy that I'm using here is basically I compute the between centrality for every node, and then I create a probability distribution that is proportional to the between centrality of the nodes. And the problem with this strategy is it's computationally heavy. I can run this now on my notebook computer with a Lightning network of, let's say, 5,000 nodes. But if the Lightning network has 50,000 nodes, it's probably not feasible to run this on my notebook computer anymore. So this is an issue, right? So while this is like the best strategy to some degree from a scientific point of view, it's kind of infeasible to do. But for now, the Lightning network is small, so we can use it at least for now. So yeah, this is a graphic from Chiang, who is also thinking about these problems, that shows something that people who think about graph theory are well aware of, that the between centrality is pretty skew distributed. So there's also only a few nodes that have a high between centrality, and most nodes basically don't exist, right? So this strategy also has this disadvantage that we overpower a few nodes. Okay, so decreasing the diameter of the network. So I'm already thinking about shortest paths on the Lightning network, so I already have computed all the shortest paths, which is great. So now I can again look for each pair of nodes and calculate the shortest path between them, and I can keep track of the length of this path. And now I find the pair for which the path is the longest. And then I say, well, the end nodes of those, it's good if I connect them, right? Because also for their neighbors, I create a path that might be shorter. So again, with a higher probability, I connect to those nodes. So it's pretty much the inverse probability distribution from the one where I'm trying to go proportional to the between centrality. And this makes my own node a little bit more central, which is great, right? Because as we saw, not many nodes are actually central, right? So this again increases the chance that others might connect to me, and it creates utility on the network, which is nice. Okay, some technical details. All strategies are currently implemented to produce a probability distribution, and I'm then sampling from this probability distribution. So this is where randomness is coming in, right? So even if I'm following this strategy of like connecting to central nodes, I could still, by random accident, to connect to some other node. I can always smooth these distributions with the uniform distribution or another distribution that's already implemented, and I can also consider a cutoff of saying, well, let's just like sample from the top probability mass of these distributions. And then there's two different strategies how I use these four strategies. The first strategy is what I call the diverse strategy, where I'm basically just averaging all the probability distributions and I'm just sampling from the average of these distributions. And the other one is the merge, which means that I'm sampling nodes from each of these distributions and then I'm merging the result set, right? Which basically says, yeah, go more in each of these like strategies. And the cool thing about this piece of software is if you come up with a different strategy now, you can easily implement this. So some of these strategies are just like 40 lines of code or something like this. So if you have a better idea, you can just add another strategy and you can just also integrate this into this autopilot. And as I said before, I have cutoffs, so I can basically then say don't sample from the entire probability mass, but just from the very top of it. Okay. So currently the API looks like this. So currently it's a command line tool where basically I have like call this with Python, and I have help, and then I have like a few arguments to give. I started implementing this as a C-Lightning plugin, but I have a little bit problem with the asymmetry because some of the calls take a little bit of time. I have to come up with a nice user interface to make this a good API that runs within the Lightning node. So if any one of you is a UI developer, it would be really great to talk later, because I really have some open questions of how should I design something. So it's not technical challenges. Then, as I said before, I do a balance selection for candidates. So the question is, how much of my unspent transaction outputs should I use for each channel that is recommended? So what I do is, from my candidate sets, let's say I have 20 nodes that I want to connect to. For each of these nodes, I sum up all the total balance of their channels, and I divide this by the number of nodes they have. And then I create, again, a probability distribution that is proportional to the results. Meaning that if I'm connecting to a node that already has a lot of capacity or high capacity channels, I create a channel with a higher capacity. But if I connect to a node that only has like small capacity channels, I create a small capacity channel, right? Because it doesn't make sense to provide like a really high capacity channel because routing will not get through to the next smaller capacity channels. Obviously, this strategy could also be changed, right? By basically taking the maximum channel that is connected to the node or something like that. And then also this probability distribution, I smooth this a little bit to avoid dust channels, because you don't want to create too small channels. Okay, as I said before, I brought some graphics. So some statistics about the Lightning Network. Okay, so it's bad that this is cut off. I don't know why here it's displayed properly. So what I'm showing here is, I'm showing for all Lightning nodes the base fee rate that is currently being taken for routing. So every Lightning node can announce for every channel what fee they take, and all units are measured in millisatoshi. And what you can basically see is, this is a logarithmic scale here, and this is a histogram. So this is the number of nodes that use this fee. So you basically see that these three fees are the ones that are mostly used currently. So it's basically something like 0 Satoshi, 500 millisatoshi, and 1000 millisatoshi. Or if you look at the cumulative distribution function, that's the same data but just in different function, you can see that something like 30% of the nodes have a fee that is lower than 1000 millisatoshi, and then pretty much like 60% of all nodes have a fee that is like 1000 millisatoshi currently. So what we see that a fee market hasn't really emerged yet on the Lightning Network. It's pretty much everyone just keeps the standard configuration. I think LND has a standard of 1000 millisatoshi. So this is just what people take for routing. If I look then at my node, I could start to calculate what fees I would have to pay to reach all the other nodes. Right, so I can reach about 800 nodes with a fee that is roughly 500 millisatoshis, and when I pay 1,500 millisatoshis, I can reach another 1,400 nodes, and pretty much, I mean, there's some nodes I have to pay something like 2,000 millisatoshi, but this is pretty much all that I can reach. So it's still very cheap for me also to use the Lightning Network. But maybe my node is very good connected or very bad connected, so I created the same picture for all nodes. So now I looked at every node.
Sorry, it's a
microphone?
Yeah.
Yep. So now yeah, so I think now it's on, right?
Yeah, should.
Yeah, should be. Okay. I don't know.
But the other one already was. Take it off.
Okay. So in this graphic, what I did is, for every node on the Lightning Network, I calculated for all paths to all other nodes, what the fees would be like. And then I looked at how cheap routing would be. And again, what you can see in this graph, that most routes on the Lightning Network actually just take 1 Satoshi of fees currently. And again, when you look at the cumulative distribution function, you can see already that 50% of all paths on the Lightning Network actually take 1 Satoshi or less in fees. Okay, this is great to know, but does this really help us with the autopilot, and why am I doing this? So I have to look at one more mathematical thing. I wanted to estimate the expected routing fees that I would own by running my Lightning node. So how can I estimate the routing fees that I will earn? So first of all, I make a really, really hard assumption, which is most likely not true, which is that I assume that between all pairs of senders and receivers, it's equally likely that a payment takes place. And we already know this is not true, right? There is bit refill, they receive a lot of payments, and the average Joe just makes a couple of payments per day, right? So this distribution probably doesn't look like this. So we could model something else in, but I don't have the data, so I'm assuming the uniform distribution here. And then I try to calculate again the property that my node is on a path between the sender and the receiver. Okay, and as I mentioned before, the most important concept that we want to understand is the between centrality. So the probability that my node is on a path between a sender and a receiver is pretty much the between centrality. So good luck that I already have calculated this. And then my expected routing fees that I will earn is the between centrality, which is the probability that I am routing the payment times the fee I'm charging. And if you look at this, this is an optimization problem, right? It's first of all hard to solve because it's nonlinear, and the between centrality is hard to compute. But what I can do is, if I try to solve this optimization problem, and I did this on my node with 8 hours of computation time, I get this nice graphic where I see on my particular node my expected routing fees will be highest if I take a little bit less than 500 millisatoshis of fees. Right? But this only holds true for my node. For your node, it might be different. Right? There's some people who have much higher expectation values and they have a lower fee, and there's some people who have a much higher expectation value and they have a higher fee. So this thing depends on two things. First of all, on the overall topology. So how am I connected in the network? Right? Again, the between centrality. If I'm more central, then I'm having a higher chance to earn fees. And of course, on the fees that I'm charging. And I think why I'm showing this is like the future work part of my slides, that an autopilot should work with these kinds of data in order to make better estimations of which fees you should charge and which channels you should connect to. Just some more graphics to display the situation of fees currently. So here I have the average base fee rate for each node, and here I have the expected earnings in millisatoshis per payment that takes place on the Lightning Network. So what you can see basically here in this line is that most people actually who have a pretty good expected earning have a fee that is a little bit less than 1,000 millisatoshi. And that makes sense, right? If we remember before, most nodes, I think 60% of the nodes have 1,000 millisatoshis as a fee. So if you go slightly below this, chances are pretty high that you are routing the payment currently. Right, but now after my talk, maybe everyone goes for 950 millisatoshis. Right, so I think the fee market now kind of starts, and maybe it's decreasing. Right, maybe the utility of routing is just like really low. We don't know yet. Then I have plotted the number of neighbors each node has. Again, on the y-axis, the expected earnings, and what you can basically see on this diagram, it doesn't really correlate. Right, so. Maybe a little bit. Yeah, I haven't calculated the correlation scores, but it's pretty overall. I mean, you have some nodes that have only a few neighbors, but already pretty high routing fees, and then you have some that have a lot of neighbors, and yeah. So what I'm trying to show is that the amount of neighbors is not the most important metric to look at, right? Whereas the Barabasi-Albert model just only looked at the number of neighbors. Right? That's pretty much my argument. However, and again, I mean, this is also a little bit skew. If you look at the between centrality of the fee graph, and you look at the expected earnings, you see that you have a pretty good line. So the more central you are, the better your earnings are. Which, of course, currently is true because almost everyone charges the same fees. Right? This will change if the fees are being played a little bit differently. But what I'm saying is, for an autopilot, it makes sense to make you more central, in particular if you want to like earn routing fees. Yeah, and one thing that maybe for you all it's obvious, but for me it was quite enlightening, is I have here the centrality of the base fee graph, and on the other side I have the centrality just with the distance measure in the Lightning Network. Because when we had the discussion about the Autopilot in the past, it was always being used just the distance graph. And what I'm showing is it's really a different thing if you like compute the between centrality on the fee graph, and it makes sense to study the fee graph a little bit more, right? So when I have a payment channel with you, I basically attach not the capacity of the channel to the node in the graph, but I attach the fee that I'm charging or that you are charging. Yes. So there are some future ideas. One is again by Kulprit Singh, who talks about articulation points that are these points that would split the Lightning Network in two separate components. It's amazing if you look at these like Lightning Network visualizations, it seems like those points don't exist, but actually if you count them, they exist quite a lot of them. Usually at the border of the Lightning Network, right? But as I said, one of my strategies is to like connect these nodes and provide them with a little bit like with triangles, right? Look at the node age and the channel age. This is stuff that is basically being shipped to you in the Gossip protocol. Make the Lightning node collect more statistics. The uptime of nodes, the routing fees, how often does routing work, how often does routing fail, right? So you yourself can collect way more statistics than there are out there in order to make the Autopilot smarter. One idea by Alex Borsworth was to actually recommend closing channels, which I think is a pretty neat idea. If you say this channel is really bad for me, for some reason, everyone tries to route over it, but I can't like really fulfill them, just close it down. And then implement strategies to increase the collection of routing fees. As I said, currently I haven't implemented this, but this might happen soon. And yeah, recommend a fee for certain channels. Currently I didn't do this, I just leave this to the user to set the fees, but it makes sense to also recommend this automatically. And since this entire problem is an optimization problem and calculating the centrality is hard, it might make sense to make even harder stuff like machine learning, but sometimes you can make estimates. So yeah, I will skip this. What I want to say is, as a conclusion, there's a trade-off between privacy and quality of recommendations. That belongs a little bit to the slides that I skipped, because if nodes would share information about their balance with partner nodes, obviously they could make smarter routing decisions. And obviously an Autopilot could be like a third layer protocol where nodes communicate with each other and give hints to each other how they could like create these nodes. What is important is that pathfinding and Autopilot are somewhat related problems, and recommending the channel balance seems reasonable. Also, communication and information sharing might be the way to go, as I just mentioned. And selecting routing fees yourself, well, I think that's a typo. Because I think this should also be recommended. So yeah, we need more simulation frameworks and research and some real-world usage data to do this. So if people want to help out researching, I have contact to one master student now in Koblenz who wants to write a master thesis about this, which is great. So if other people are interested in this, just talk to me. This is really great. And yeah, this is some other stuff that I'm doing, but I also skipped this, so thank you for your attention.
Hello, so you got any questions?
Hey, thanks for the great talk, René. Just one question. You always mentioned the base routing fee. So this doesn't include at all the part of the fee that goes up when the value goes up. So far, I mean.
Yeah. So I should have mentioned this. For the calculations that I did, I always assumed 1 Libbitcoin payment. Right. So. Oh, sorry. So for the calculations I did, I always assumed 1 Libbitcoin of the fee, and then the base fee rate. I didn't show the graph, but the relative fee rate is even more stable than the base fee rate. But it makes sense to also look at this, right? But then you need
change the statistics, right?
Yeah, but you need even more data because then you also need to simulate payment amounts. So I mean, this is science, and it's science to make assumptions. So I start with simple assumptions. But yeah, very, very good point out here.
Hi. For calculating the betweenness centrality, do you take into account the inbound and outbound connection capacity?
No, this is not because I don't know it.
Ah.
And so when I compute the centrality, I need to decide how to model my graph, right? And in this case, I model the graph in the following way: the nodes are the nodes on the Lightning Network, and the edges have weights, and the weights are the fees, right? And I use the fees for path finding because I want to find the path with the lowest fees, right? So I can't take capacity into consideration, and especially balance, right? That's what I mentioned in this like conclusion slide of saying it's a dynamic problem and it's a private problem, and of course if nodes would be willing to share some information, stuff might get easier.
Thanks.
Hi René, thanks for the great talk. I learned quite a bit today. I don't quite understand if we can have dual funded channels. How you had a slide with the UTXO allocation for channel funding. So how would you structure the problem if I now would have to react to channels inbound, but which I also fund? So how would that problem change?
Yeah, you said dual funded channels, right?
Oh, which don't exist today, but like
yeah, no, perfect. I was just not clear if I understood correctly.
Thank you.
So the thing is, if you have a good recommendation system, you could basically recommend also if you want to have inbound capacity or outbound capacity with someone. So if you have dual funded channels, we have to have some mechanism of accepting a dual funded channel or not, right? So maybe the Autopilot could basically say, hey, these are the nodes I would accept dual funded channels with, and these ones are the ones I don't. So if somebody opens a channel with you in a dual funded mechanism where you also have to provide funds, you could basically query the Autopilot data and say, no, I don't. Right? I mean, you don't have to respond to this. That might be one idea, which just came up when you asked the question. So yeah. No, honestly, so it's, yeah, but maybe.
Hi, great talk, thank you very much. I'm question about the API, about C Lightning, you're implementing that on top of. So you said you're not using the plugin system. How much effort would it be to port that maybe to the LND API, or is that even possible?
So, first of all, I already, when I created this piece of software, I separated it in two files. One is the lib autopilot, and the other one is the autopilot daemon, or whatever you want to call it. And the lib autopilot is the one that you can actually hang into LND if you wish to, right? So you can just like build on top of this, right? So, but you have to like somehow have like a Python, Go, bridge, whatever. The second thing is that LND recently provided a better interface for their autopilot, so you can just provide them with scores, which is great. One thing to take into consideration, their scores are not probability functions, but they use the weighted average, which doesn't make sense for scores in the range between 0 and 1. They should use the harmonic mean. I haven't had the chance to open the issue yet, but I mean, that's easy to fix for them. So yeah, you can use this Python library, one for simulations, and one also to hang it into LND. I would be very happy if somebody does it, actually. As for the C Lightning plugin interface, one reason why C Lightning pushed with the plugins was actually because of this autopilot, because I like took the initiative there. And it's pretty easy to like wrap this now into the plugin system. The only problem I'm having is some of my commands take something like 10 seconds to execute. And the question is really a user interface thing. How do I make this, right? Because you don't want to have your C Lightning node be blocking on the command line interface. Yeah, you can make it asynchronous, but then you have to have a different interface of saying, hey, what's the state of the autopilot, right? So this is a little bit of the problem. But yeah.
All right, we answered some questions now, and I want to thank you, René, for your great talk. If you guys have some more things to talk with him about, you can do that during our break. We have like 30 minutes now. We're gonna start around 4 for the next sessions, and enjoy some drinks in there, and hope to see you soon.
So, Sound ist mal wieder an.
Hallo. Hallo, wir werden gern weitermachen. Darf ich euch bitten, wieder in den Raum zu kommen? Keiner hört mich. Danke. Hallo, wir würden gern starten mit dem nächsten Track. Der Daniel wartet, bitte kommt doch hier rein. Sehr schön. Wir haben nachher noch viel Zeit, uns weiter auszutauschen, aber jetzt gerne erstmal starten. Dankeschön. All right. Come closer, here's some seats. Please have a seat. Okay, we have Daniel here now. Can you please come here, Daniel? Welcome. Here is the CTO of Ficsor, a company in Zurich. They work there. They actually, since 2013, they are dealing with the Bitcoin topics, and they're very knowledgeable about it. And he's going to talk about game channels today. Enjoy.
Hello, everyone. Is the microphone working now? No, no. I can just say. Yes, now?
Did you switch on?
I did, yes. I think so. But I can just take...
Yeah, take the other one.
Yeah. I can just... Yeah? Okay. Okay, great. Now it's working. Perfect. Now everyone can hear me. Yeah, thanks for the introduction. I'm Daniel, and since about a year, I'm now working at the Ficsor project, which is like a startup in the blockchain space. And actually, in some sense, I'm mostly an altcoin developer. So before everyone shoots me, I have like some things to say in defense of that. The first thing is I'm also hodling Bitcoin, mostly. And the second thing is that the projects that I've been involved in, namely Namecoin, which is maybe something that the old school people in the space know since 2013, and now also the Saya platform, they are based on Bitcoin Core code-wise, which also means that all the things while developing those as the main goal that seemed like useful not just for Namecoin but also for Bitcoin, I've actually contributed to Bitcoin Core, so I have like 30 something commits in Bitcoin Core also, so I try to like support that even if it's not the main project. Anyway, and also like this talk, I don't want to like promote our project. I want to give more a technical talk about some ideas, some specific ideas that we've been working with. So so what we are doing is blockchain games, and in particular this one. Maybe some people know it. I've already heard the name here today. This is Hunter Coin, which was the very first blockchain game, as far as I know, back in 2014. And it's actually a game that is like fully decentralized. It's not like Konstantin said that games have to be centralized, or like a lot of games are, of course, but you can build games that are fully decentralized, and that's like what we want to do. We want to build games that don't just have like some assets on a blockchain and where you have just some payments on the blockchain, but where the full game logic runs on the blockchain, which also means that if I pay someone crypto coin to buy a sword from them, then I can verify in the blockchain that they actually got the sword by killing some monster and not because the developer is their friend and gave it to them or something. So that is the rough idea of what we want to do, and that's the context of like what this talk will be about, not about gaming specifically, but about some ideas in that field. But for the basics, so if you do this, then how do you do that on a blockchain? The basic idea is that you have a game state, which is just like where each of those hunters is on the map, what items there are on the map to pick up, and also in the case of Hunter Coin, you actually have a cryptocurrency as well, so it's also like the ledger of balances. And just like Bitcoin tracks the ledger itself, like the UTXO set, in this case you track the balances and the state of your game. And then you use the blockchain to get consensus on the whole network of what the current state is, so that everyone agrees, and like you can play a game and everyone agrees what the current state is. And here is that's a bit more technical. On a high level, how it works, like you have the blocks in your blockchain, and then you record the actions of the players. You record, we call them moves, in transactions. That's just like Bitcoin transactions. And then if you know kind of the sequence of all the transactions, of all the actions that were taken, then you can just, knowing the game rules and this kind of the actions, you can compute what the state is. That is just how the UTXO set is computed in Bitcoin, right? So the UTXO set is not stored in the blockchain or something, but you just store the transactions, like the changes, you store them in the blockchain, and then everyone can just follow this sequence to compute for themselves the current state. And that's how the basic model works. So you have like, you can even have one blockchain, you can have two different games on it, two different states that are tracked. And one big problem that we saw with Hunter Coin was, of course, scalability. But that was at a time when like most of the people who are now doing blockchain gaming on Ethereum didn't even know what blockchain was, like in 2014. And like we had the chain grew like hugely because the game was very popular. So that is one of the big things we have to work on, of course, that every blockchain game will come across. So we think there are actually two different aspects to consider here. One is what I would like to call horizontal scaling, which means that if you take Ethereum, for instance, as an example, and then you have like 1,000 games on it or even more, then one big problem is that those games have to be trivial. Because if you want to do something even like slightly complicated, for instance, some team tried to implement like a chess game on Ethereum, and they found out that just checking whether a position is checkmate or not is just not possible on Ethereum, because you have to kind of try all the potential moves and figure out that none of them works. And the problem here is that due to the way how Ethereum works, kind of every full node has to compute every smart contract, so they have to compute kind of all the games on the blockchain, which is just how the system works. But the problem is that if you have like 1,000 complex games, and I don't care about 999 of those, then I still have to compute all of them. And that makes it expensive for those games and for the players of those games, because they have to pay transaction fees for all those other people computing their game. So what you can do is you can try to shard the processing in the way that I briefly mentioned, that you have one blockchain that just records the data, and then the actual computation of the game states is done. Only those people do it that actually need one particular game because they play it. That is horizontal scaling, and that has like already some benefits. But the other thing is, like, within a game, obviously, if you have even one game that is hugely popular, where you have like, I don't know, tens of thousands of players that are making transactions all the time, then just that game alone will just fill all your blocks, and you cannot really implement that on a blockchain. So what we want to do to solve that is to try to do off-chain scaling for games, or in this game context, where what we want to do is really build games as games. But of course, those games could also be not games for entertaining, but for doing whatever economic interaction that you want to do, for trading or for things like this. And this second aspect about off-chain scalability is what I want to talk about today in this talk, basically. So there is one concept that we called game channels, which we kind of developed independently and roughly at the same time when state channels came up for smart contracts and stuff like that, already 3 or 4 years ago. And the basic idea is that we do something like like payment channels, that you have 2 or more players. Say the very basic example of when you can apply this is if you say, okay, you want to build a game where 2 players play chess against each other, and the winner gets 1 Bitcoin, or 1 millibitcoin maybe makes more sense. And you want to do that in a way that is obviously kind of decentralized, or at least trustless, that I can verify, and that the other person is not cheating, except maybe if it's actually chess, then they can just use a chess computer, as we heard already. But like apart from that. So and yeah, the idea is very similar to payment channels, that we just open a connection to each other, not even using routing as on the Lightning Network, maybe for simplicity, just a direct connection, and then we send each other the moves like we would if we were playing chess by email, say. Yeah, and in the end, if like I don't know, I win and my opponent agrees that that's actually the situation, then all is fine, and we can just say, okay, now I won, we both sign a transaction that sends like 1 Bitcoin to me. And if we do this, then we just kind of need a kind of opening and a kind of closing transaction on the blockchain. But all the moves in between, they can just stay private and can be removed afterwards, kind of. But if there is a dispute, like one of those parties disagrees of what the current state is, or like even harder to solve, or the main difficulty is actually if someone just stops responding because they don't like it, or because the network failed or something like this, then in this situation the other party can still kind of go on chain and settle this channel. So it's, like as I said, like payment channels, but with some twist that I think is important for gaming. I will talk about this a bit later. And also, like state channels are related. They were kind of developed independently, but they are also not fully addressing the same issue that we have here. And I'm aware of like 2 implementations on Ethereum games. One is this chess that I talked about, that is like going in this direction, but not in a very simplified way. Then there is another project that's called Etherships, which is battleships on Ethereum, that also goes in this direction, but also doesn't solve the what I think is the most important difficulty. So that's this one. So in a classical payment channel or in a state channel, you have always a well-defined state of like what are the balances of the two people, and anyone can just go and say, okay, I want to settle it now because whatever. So I can just put it on chain and settle the current state. But the problem with games is that you cannot do that. Because if we are playing a game of chess, then you cannot just simply say, okay, I don't know, I have a queen more than the other guy, so I surely win, because that's just not the case. So for such a channel, you cannot just always settle the current state, because the current state might not just be well defined in terms of balances. So you can only do it at the end. And the problem is now, what do you do if someone actually stalls that, or if someone just stops responding? Then somehow you have to prove to everyone that this guy actually stopped responding. And I think it's very interesting when I heard that in the second talk by Kilian, that I think that's kind of the same problem that he has for this Lightning Network atomic swaps, where you need to attribute who's at fault. That is, I think, a similar problem. And with this Etherships problem, what they did is they just said you get a partial balance, and you can just settle any time, and then you just get a payout proportional to like how many ships you have left and how many the other guy has, which kind of works in this concept, but is obviously not really the full experience in some sense. And they are dodging this this hard problem by just doing it that way, making it kind of simple. But for like games, there are a lot of games where you simply cannot define any kind of partial balance, or it need not be games, as I said. It could be trades, it could be any kinds of interactions. So here's how it works basically. You have a main blockchain, and then off the chain we have two people, Alice and Bob, or A and B, or whoever you want to call them, that are playing, like, say, a turn-based two-player game. So they just send moves to each other and kind of always sign their last move. So in some sense, they build like a federated chain where like each second block is built by Alice and the other by Bob. They sign it to kind of build a record for it. And if they both agree, and in the end kind of both sign the outcome that Bob won, then you only need like these two transactions in the main chain, one that defines the intent of playing this game with maybe some parameters, and that's the payout, and the other one that actually sends the payout to the winner. Yeah, that's just the simple case. So now what happens if Bob stops responding here? That is, like as I said, that is the hard problem that we need to solve, because of course, if Bob stops responding, then Alice wants to get the payment eventually. But for that, she needs to be able to prove to everyone that Bob actually stopped responding, so that it's fine to approve the payment to her, kind of. So what she can do is she can send an on-chain transaction here after some timeout that says, okay, look, this is the current state in this game that I play with Bob, and I think that Bob stopped responding. And once that transaction gets into a block, at that point in time, everyone knows that Bob would have seen that block if he's still there, obviously. So if then, after, I don't know, 2 more blocks or whatever, maybe make this a bit longer to be secure, Bob still hasn't responded, then Alice can kind of prove that he's really gone, and she can get the payment in this block. But if Bob is actually still there and Alice just tries to cheat, then Bob can see the transaction in the chain and can send another on-chain transaction to say, look, I'm actually here and this is my next move. Then everyone sees that as well. And ideally, if here there was just some network failure or something and not malicious intent, then Alice also sees the transaction, so they can just pick off and continue. And by that way, by this system, it's possible to like solve this dropping out problem. However, there is like one small or maybe not so small issue with it. Yeah, so like as I said, that's the hard problem. That you're not actually able to just settle the channel if you think that the other guy stopped responding and you don't like it anymore, but you have to prove it. And you have to prove that the other guy is at fault in that situation. So, and with the system that I described, the problem is that you can get a back and forth with on-chain disputes. Say, Bob can always like not respond, wait for Alice to actually go on-chain, and then he responds on-chain. It continues, and then he does it again. And if he does that, then he's able to like cause on-chain transactions again to bloat the blockchain, make the game slow because you always have to wait like for 1 block or 2 blocks or whatever the timeout is. And also both parties need to pay transaction fees for that. So there's probably not really that much incentive for Bob to do that, except for to disrupt the system, which might be like a valid incentive in some cases. I don't know. But it's not actually possible to gain money except by I don't know, delaying the game so that Alice just gives up because she doesn't like it anymore. And we have one idea for improving that a bit further, which is still like a very theoretical thing and something that we've not yet been able to actually try out in practice and see how much of a problem it really is. But I think it would be a nice idea to share that and see, and also see, of course, in the future, if we implement that, how it actually looks like in a real world system. Whether people will actually do this, or whether the games will just run fine anyway, and no one will try to do this because they have to pay transaction fees themselves. And like the solution that we propose here, we call them ephemeral timestamps. And basically, here are 3 properties that you have to believe me at the moment. Then I will talk about like how they solve the problem and then how you can achieve them. So what if you could create like a timestamp that you can use later to prove to everyone on the network that you published some piece of data D at time T. This D would be like Alice's move, claiming, or Alice's like claim that Bob stopped responding. And you can do this, but you only have to actually put it on chain and actually pay transaction fees for it only if it's really used later on. So only if you really have to prove it, not just for like creating the option of proving it later. And you can do that in a way that maybe there is still like the right incentives for miners and everything, that the whole system like works together. And in this system of game channels, you could use it like this. So if Bob stops responding, then Alice can create such a timestamp that kind of publishes data that says Bob stopped responding. Here's the latest position in the game, and I think that I should get the prize money. And then if Bob doesn't respond after like a timeout, then she can use that proof to prove that actually like she published this dispute already n blocks before, and Bob could have seen it, so he hasn't responded yet, so it's fine for her to get the money. And yeah, but if Alice does that and Bob actually saw it, then Bob can do the same. Like if Alice publishes a dispute, then Bob can actually publish his next move as well, and also create a timestamp so that if Alice then tries to defraud him by saying after n blocks Bob didn't respond, then Bob can actually prove that he responded. And so in this case, it's also clear that Alice is doing something bad, so Bob wins. And at the most, in the most case, you only have to like 2 steps. You cannot get a back and forth where you have to go on chain all the time. And like here's a rough idea of how you can actually achieve those properties. So you have again the blockchain, but in addition to the block data, you also attach some extra data which you use for the timestamps. But you do that only kind of for recent blocks. So that obviously has the big issue that you still have to send those data somehow. You have to publish it in some system. So if you just use like block propagation for it, you still use network bandwidth, which is maybe the bottleneck for the whole thing. But at least you get something that you can prune later. But the clue is, like, if you do it that way, that all recent blocks have to kind of include that extra data, then it means that all, like, full nodes that are up to date, they get this extra data. So everyone on the network knows that this data was published at the time. And but later on, you can prune that data, and you only have a hash commitment, like a Merkle root in the block data itself, and you can get rid of that extra data for blocks that are more than, I don't know, a week old. And if you do this, yeah, as I said, you have a Merkle tree in this extra data that kind of includes all the individual pieces of data, like all the moves that Alice's and Bob's send. But if they after n blocks they actually want to use that proof because the other party didn't respond, then they can provide the full Merkle branch, tying it to a block header to actually prove that I published the data in this extra data at like n blocks before, and so everyone can afterwards verify that that's the case. But if you only have to include that in a transaction that gets stored forever, and that every full node forever has to verify, only if you actually use that. And yeah. So finally, how does it work for transaction fees if you do it like this? So one thing is that actually publishing the timestamps is free, with a small caveat. So only if you actually use the timestamp, and if you want to include the Merkle branch proving that you had that data in the extra block some time ago, only then you pay a fee. You pay transaction fees, obviously, for just to get your transactions into a block, but you also pay a fee to the miner that originally included your data in the extra data, not in the block itself, just in the extra attached data. And how much you pay here, you have to promise when you create the timestamp. So in some sense, this means that if you play a game and Bob stops responding, then Alice can create a transaction or a piece of data that says, I think I should win that game because Bob stopped responding. Here's the latest state. And if a miner processes this, and later on Bob really stopped responding, then I will pay, like, from the Bitcoin that I get for winning the game, I will pay 0.1 Bitcoin to that miner. But only if later Bob really stops responding, and if that data is used. And then from the miner's point of view, of course, they don't know if that will really work out in the end, if Bob will really stop responding and they will get the fee or not. But there will just be some statistics involved, or the miners can just, like, analyze the data and say, okay, I think this is a fair price for this, assuming that the probability is whatever, that in such a situation the game will really be won by Alice. So there is an incentive for the miner to process that if this promise is high enough. But the advantage for Alice in this case is that she only has to pay the money actually if she at least wins some more money for it. So there is no way that a malicious player could just go back and forth and cause the other one to pay transaction fees at every move, like using up all the potential prize money, or even more maybe. Yes, so that was on a high level my talk. So what I think are the important points to take away, maybe. Scalability is important. I think everyone knows this. I mean, we had 3 talks about Lightning just before, so that's clear. I think especially for gaming, I mean, maybe not especially, but also for gaming. Yeah, there are a lot of games on Ethereum, which I think, I mean, here is not an Ethereum meetup, here's a Bitcoin meetup, but also my opinion is that Ethereum is probably not the best platform for games, for this very reason that I said, that you have to have, like, very, very, very simple games, because everything else just doesn't work the way Ethereum is designed to work. And then, yeah, we have maybe some solution or some ideas for how to do proper off-chain scalability for complex interactions, not just for payments, but for interactions where you have like arbitrarily complex game rules, where the hard part is actually this proving that a player stopped responding, and because you just cannot settle any time. And like as I said, that's actually, I think, the same problem that Kilian has for the on-chain, for the off-chain Lightning Network atomic swaps. And yeah, we have some ideas that that might improve that in some aspects, not in all, and we have to see how that works out in practice. Thank you very much. And
okay, first questions here.
Maybe I just missed it. What happens if Alice publishes an old state of the game to the blockchain? So Alice starts to lose, and then she decides to publish an old state. Then Bob can say, hey, I'm still alive, and makes his next move, right? But then Alice can deviate from this.
Yeah, so yeah, that is a good question. But at least in the simple situation that I described, that you have like a two-player turn-based game, but you can actually generalize that to like more complex game worlds, kind of real time. But the clue in this case is that everyone signs the current state or the sequence of moves. So if Alice goes back, I don't know, 10 blocks, then Bob can actually prove that she signed the later move as well. Maybe then they can actually, he can just win the game. But at least, like if Alice publishes 2 or 3 signed versions of her move, then Bob can kind of decide which one he wants. So yeah. And in the worst case, like if Alice just publishes an old state, then Bob can just like publish his move to it again. And if Alice does it again on chain, then it's clear that something is bad.
Sorry. So what will prevent the player put the timestamps, just some again malicious timestamp, but just some garbage in the blockchain if they not pay the fee for this?
Yeah, you mean this last thing, right? So yeah, I mean, as I said, that's kind of an idea for now, and it's not yet tested in practice how the system actually works out. But of course, one thing is that you only kind of it only pollutes at least the long-term history of the blockchain if it's actually used, and at that point the player actually pays fees. So, but what a malicious actor can do is publish timestamps that can be removed later, but that have to be like published with the blocks for a day. And if it, I mean that's better, but it's of course not a perfect solution. But ideally, what could happen in that case is that miners who decide whether to actually process that or not, they figure out that this garbage typically doesn't get included later on because it's just garbage and it's not a real game. So I won't process it because I don't have a chance of getting paid for it. I mean, whether that really works or whether like a malicious actor can just fake it in a way that it really looks like a real game, that remains to be seen.
I mean that the player might just want to save or ensure their timestamp and put in all the off-chain.
Of course, they could just put in like every move to be faster, but in that case, maybe miners also have a way to detect that like this guy, or for this game, he's doing that all the time, so probably he's not going to use it as much as like someone who just puts it in when the other guy really stops. So maybe they want a higher promised payment or something for it.
Thank you. Two questions. The first, what if let's say if it's always going to be settled on chain, if someone drops out or wants to cheat, then you can assume that will happen. Well, will not happen a lot. And then for a miner, it will become pretty expensive to put all the data on the chain constantly, and maybe not get paid out that much. So then he would probably need a higher fee for the payout. and then the fee may be higher than what is used in game as settlement or as winning. So maybe have you thought about it? So that was my first question.
Yes, that's a good point. Of course, like when I said miners try to kind of compute what is the expected payoff if I include this now, because 10% of these games typically actually resolve in the end. Of course, that means that by this percentage, there will be like a higher fee in some sense. But yeah, I mean, at least it means that you only, as an honest player, you only pay that fee if you actually win in the end. So you cannot just lose something and then you don't even win. But of course, it could be that Bob only stops responding when the game is kind of lost already. So then instead of winning the full amount, what you would, you have to pay a fee to the miners, but at least you still win. And for your other question, of course it could be that games have like very low stakes to the point that miners will not process your data. But I think that just remains to be seen what those fees really be and for what games it's really gonna be used.
So could you say that it's basically watchtowers but with different data? So couldn't you just basically locally store the whole moves of all the games and then just send like the transaction of all your moves, or like the hash of all the moves basically to like a watchtower type of service, and pay like for each backup transaction or timestamp? You would basically similar to how you would do that with like a watchtower and Lightning transactions. So you don't propagate all the data and only propagate the data when you need to like publish it with the hash to prove that the hash actually contains the data to move stuff.
I have to admit that I'm not as familiar with Lightning as maybe some people here, so I only know roughly about this. But I think that the main problem is that you have to prove that you published actually this data some time ago, and that everyone could have seen it. So it's not enough to just have some hash commitment in a block and then reveal the pre-image later, or to send the data to some watchtower. I mean, of course, the game could be built in a way that you have like semi-centralized publication where like the game is built in a way that it says, okay, I trust these sets of watchtowers, that if I publish data to them and if they claim that it was published, then it was published. But then it's not fully decentralized.
Sorry, only the ones here.
Another question then. The data is Merkleized and you post a hash on a chain, I think, but because it's so well defined, probably isn't it easy to compute what a hash may be of the next move, because the move is like yes or no, for example?
Yeah, that is of course a good point, and also like you have that if independent of these game channels, if you just send moves and you want to make it in a way that only like both players make a move and only then it's revealed, then you have the same problem. But of course in that case you could just include a salt or something, which of course increases the data size, but you can do it.
Jetzt geben wir mal ein bisschen Hint.
In the case of Ethereum, as far as complex computations are concerned, the whole ecosystem is moving towards outsourcing computations with zero-knowledge proofs, like Golem, for example. Why isn't that a solution for your problem? Like, why can't I publish a zero-knowledge proof that my state is the latest correct state of the channel?
I mean I think that is more a solution to the first scaling problem that I mentioned, that you kind of have to do all the computation for all the smart contracts, which we actually solve in a different way by actually doing computations only at those nodes that actually run a particular game. But I think zero-knowledge proofs won't help you in this situation later if you want to prove that your opponent stopped responding moves on the channel, right? Unless I'm missing it somehow.
Well, your opponent could later try to publish like their own latest state. You can verify, because it's a zero-knowledge proof, you can verify which one is the latest.
No, but you can do that anyway. I mean, maybe you can optimize it that way, but like you just, if you have like a sequence of signed moves, then you can always prove that that is the latest state anyway, because that's the longest kind of chain of blocks where your opponent still signed one. But of course, maybe you can use zero knowledge proofs to optimize that. So instead of having to like publish the whole sequence for an on-chain dispute, you can actually use the proof for that. I think it's orthogonal in that sense.
Okay, one more last question maybe. After that we move to the next. All right.
Hi, thank you for the presentation. I missed the beginning of your presentation, so apologies if you have already addressed my upcoming question. Okay, the question is this. What makes it worthwhile to put a game on a blockchain? It seems like it just creates a whole bunch of problems that you wouldn't have if you didn't put this on a blockchain in the beginning.
Yeah, that is of course a very good question. I think like the first talk also tried to talk about it a bit by Konstantin, but I mean I think it's not yet really known whether consumers and developers actually want it, but there are of course some unique properties, like you can run a game that doesn't have any servers. I mean the first thing that most projects in the field actually like marketize is that you have true ownership of your assets, because they're all like ERC 721 tokens or whatever. But the game itself is still centralized in a way that, say, CryptoKitties generates the graphics on their server, and I mean you have maybe a kitty, but the game is not fun anymore if the server goes down. So in that sense, we think that it's actually true ownership only makes sense if the game is fully decentralized, so that you don't have any servers, and that the company that developed the game maybe they cannot just shut it down and the game is worthless, because you can just keep on running it. But I mean, whether or not that actually outweighs all the drawbacks, I think that is still not yet known.
Okay, thank you so much for this presentation. Okay, we have our next speech here. This is Stepan. Welcome. And he's going to talk about DIY hardware wallets. He's going to explain how easy it is to use that and how safe at the same time. And he's going to explain a little bit how this can be done. And tomorrow we have our workshops. And in the workshop, in the afternoon, he's going to do some practical examples on that. And for those of you who have assigned to that, you're going to have lots of fun with him playing with your tools. Today, I forgot to say, he is actually working in Munich. He's the founder of Crypto Advance, and we are really welcoming him for the speech.
Microphone? Yeah. Okay, so it should work. It should work, yeah.
Can you hear me? Yeah, it looks like there is a microphone and this microphone works. So let's just hope that it will keep working for the rest of the talk. Okay. Hi guys. First, I want to thank organizer for inviting me, and also I want to say that it is amazing how this conference popped up and collected all these wonderful speakers and people, and from all over, not only Germany but like from other parts of Europe. That is really exciting. Today I want to talk to you about the do-it-yourself hardware wallets. And probably when you think about do-it-yourself hardware wallets, you think about something like this. So this is actually the very first prototype that appeared on, I think, Bitcoin Talk forum from Someone 42. So it is actually a Bitcoin hardware wallet. Looks messy, right? So hopefully from 2012, lots of progress and a lot of very convenient developer boards appeared. So now you don't need to have this mess on the table, and we will get to it. So first, let me tell you why you should listen to me at all. So I am a quantum physicist by education, so I used to work in experimental quantum labs for a decade or so, and last 3 years I worked in Max Planck Institute of Quantum Optics here in Garching. And in 2013 I kind of found Bitcoin and read about it and got really excited about it because all the math is just so wonderful, so beautiful, so like I just fell in love with it. Yeah, thanks. Awesome. So it still took me a few years before I actually decided to move completely from quantum physics, that is also awesome, to something different and more kind of connected to the real world. But a few years later, I decided to build my first hobby project hardware wallet. And why I did it? Because back then, well, we had Trezor and Ledger, and I thought that I definitely don't want something to plug to my potentially compromised computer. So I just felt that my security model is not exactly the same as the one that was chosen by the creators of the hardware wallet. And I think that still in many cases, our assumptions about security and how we want to secure our private keys may be different from what market tells us we can do. So I think that we should be able to do something. So this was my very first prototype. You see, not that ugly, not many cables there at all. So just the better one. Then I moved to another one that already supported SegWit and QR codes. Then we participated in the building on Bitcoin hackathon, where we built kinda Lightning hardware wallet, not really, but it was a proof of concept. And yay, we won, and you see here a few guys. So Justin is here, he will be giving a talk afterwards, and other guys from the team. Then I had another revision where I was playing with Wi-Fi, Bluetooth, and all other hot wallet stuff. And I met these two guys, and so we actually started a company here, and now we kind of partnering with real security labs, and I was able to move from quantum physics to embedded hardware development, and we are trying to build a new kind of generation hardware wallet. During all this journey, I learned one important thing, that basically everything can be hacked. And no matter actually what you use, the question is only how much effort the attacker needs to put into breaking your hardware wallet or your security system. And the same trade-offs goes to you, because basically the more you go in the security side, less convenience you have. So basically, if we are talking about the daily expenses, then probably your mobile wallet is okay. Then for the salary, it's already slightly different. I would prefer a hardware wallet, maybe a normal one. But if we are talking about the life savings, then I want to go crazy. I mean, I want multi-signature, I want air gap, I want Shamir secret sharing. Well, depends on your life savings. And you don't want to expose how much you own, obviously. Because what the attacker does, they basically do the same. They see what is the easiest way to hack most of the people. So if there will be a software vulnerability that allows to check all the software wallets on the computers, then they will sweep all your Bitcoins from there. If there will be a vulnerability in Trezor or Ledger, they will also try to do that, because there are just very many Trezors and Ledgers and other kind of normal hardware wallets that are in mass production. So then supply chain is also not very hard. So you just bribe the guy that is giving you the DHA packet, you just replace it with another one, and you're good. But much harder to do either evil-made attacks or stealing the device, because then you actually need to target the person specifically. And in this case, probably the cheapest attack is just $5 range. So you just take a range and hit the guy until he tells you the password. Basically, we need to place ourselves on this axis and the attacker on this axis. And maybe the existing hardware wallets don't exactly fit our needs. yeah, a few more words about the attacks that are possible on the hardware wallet, no matter if it is a real hardware wallet or the thing that you do yourself. So there can be software bugs. So if you don't handle the user data correctly, then maybe you get a buffer overflow, and then your mnemonic suddenly jumps from your hardware wallet to the computer. So this kind of attacks is very easy to do if you are doing the hobby project, but it is also possible on the kind of commercial products like real hardware wallets. So it still can happen. And there can be implementation bugs in the either cryptography algorithm, because well, there was a bug in Heartbleed on OpenSSL that you probably heard of, and then there was also a very interesting hack of Sony PlayStation 3, I suppose, where they didn't implement the elliptic curve algorithm correctly, and they used the same nonce all the time. So basically, in the signature scheme, you have a random number that is hiding your private key. And if you are reusing this random number, then given two signatures, you can extract your private key right away. So this can happen even in the industry. Then if we are talking about the kind of mass production hardware wallets, then people can put fake chips there, like you contact the Chinese company that will create you a chip that is labeled exactly the same as the original one, that looks exactly the same, but it has a slightly different functionality, and then your secure element is not securing your private keys, but actually, for instance, trying to leak your private key to the blockchain with the signatures, bit by bit, or something like that. Or the hardware implants that was shown, I think, on C3 in Leipzig, like you can have a radio controlled button on your ledger that accepts all the transactions all the time, or something like that. And then if we go about like really targeted attacks, then if the guy gets your hardware wallet, then he can do all kind of stuff. So the voltage and clock glitching, when your microcontroller behaves not exactly how you think it should, but maybe leaking some secret through it, or decapping, side channel analysis, of kind of stuff. So if I have time, I will maybe tell about that a bit later. But for now, let's talk about what we can do by ourselves. So probably first thing that you think about is I can just have an air-gapped computer, something like a Raspberry Pi, and then at least it doesn't have any communication channel, and I use SD card or camera to transfer unsigned transactions, and then I sign and send it back. So in that sense, there is a good option. So Raspberry Pi, plus you can use Tails OS or Cube OS that are kind of security-focused operation system, but all this stuff is working on your basically computer. And the problem with the normal computer is that first you have a huge code base, so you have the whole, I don't know, 100,000 lines of code of your Linux kernel or whatever, so the attack surface is really massive. So if the attacker will be able to get there somehow, then he probably will be able to find bugs there. Then another option is to look at the developer boards. So there is a very convenient Arduino stuff that is not security focused, but still can be okay. Then there is an ARM embed that is current development, and that is what we will focus on the workshop tomorrow. And there is a MicroPython that quickly becomes an industrial standard. For instance, ColdCard is using MicroPython, Trezor is using MicroPython, and in principle it is very nice language to write a high-level logic. So the problem with the developer boards is that by default they are all based on the normal application microcontrollers. So they don't have any protection mechanism against the hardware attacks. You can build a hardware wallet with all this stuff, either air-gapped or dev boards, that is pretty secure from the software attacks, but as soon as it gets to the hardware, it's hard. And then you have a bunch of security-focused chips that you can either embed in your device, or you can and you can use them either only for the key storage. Then at least if the bad guy gets your device, then there is no way he can extract the keys. or you can even use it to store the keys and sign. That is kind of the ideal case, but right now in the do-it-yourself community it is a little bit hard because normally what you get out of the shelf doesn't support our Bitcoin curve. So you need to find a workaround there, and our hope is that sometime later we will be able to provide the convenient hardware to develop the hardware wallets yourself that support both our elliptic curve and kind of gives you the convenient framework. But for now, these are the options. Now about the flexibility. So the thing is that our hardware wallet manufacturers make the choice for us. So air-gapped on the cold card, I suppose. Trezor will add support for the air-gap at some point, but that's it. Then, if you are thinking about some extra scripting capabilities, for instance, you want to do coin join or you want to do Lightning, then you need to wait for a long time before you can actually get it on the existing hardware wallets. So maybe you want to kind of build something and on the way while they're still developing it. And how far you can get with this. So first, you can choose whatever communication channel you want. You want Bluetooth, you have Bluetooth. You want Wi-Fi, I don't know why, but you can get Wi-Fi. Then you are pretty paranoid, so you don't want all this stuff, and instead you want to pass your transactions over the audio cable. That's fine, you can do this. And yeah, obviously you can include the QR scanner and just do it with QR codes. Or whatever, you can even use the button and the Morse codes to encode the transaction if you want. So the communication is fine, but then regarding the security. Imagine that you build a hardware wallet and you include the accelerometer that is constantly checking that the position of the hardware wallet doesn't change. And then as soon as it changes, it is recorded on your secure key storage, for instance, and then when you take it, you see, so probably someone was trying to move my hardware wallet. I should reconsider where I should store it. Or, for example, the hardware wallet that unlocks only somewhere in the woods a few 100 kilometers from Munich. Yeah, and then you basically kind of stay in the field, looking around, and check out if no one is staring at you. One important thing with the GSM module, there is still a way to hack you, because basically if you you can use the signal that is similar to the one from the satellites and then kind of virtually move your hardware wallet to another place. So it is not a perfectly secure thing, but for fun, why not? Or plus you kind of add extra costs to the attacker to hack it, because, well, our goal is obviously to raise the cost of the attack to more than what we have. Because if the attacker spends more than we have, then he will not do it, because why? Yeah. Then you basically can protect yourself with any kind of sensors and environment measures. You want the wallet to unlock at certain temperature, at certain pressure somewhere in the mountain, you can do it. Yeah? So whatever level of paranoia you want. And believe me, people actually do all kind of stuff similar to this. So people, for instance, are splitting their mnemonic to 11 places across the country or even across the continents, and then when they really want to get some money out of there, they reassemble it, and it is a pain in the ass. So with these kind of things, you can at least make it a little bit more convenient. Then about user authentication. Fingerprint, terrible idea, never do it. It can help in in certain situations when you want to confirm a transaction that is kind of smallish amount in public, when you don't want to expose your PIN code, or you can use it as an additional authentication mechanism. So I still left it on the slide, but think twice before using it. Then, yeah, you, for instance, used to play your favorite game back in the days, and you know exactly the combo for a certain character with the perfect timing and the sequence of the button. Yeah? Sure, why not? Voice activation, yeah, there are also extension boards for that. And, oops, and NFC. For instance, you have your additional key that is used for encryption that you always take with you instead of carrying your hardware wallet with you. And then the final step that commercial products will never give you. I mean, never, ever, ever. It is an active anti-tampering of the whole device. This is normally available only on the commercial HSM modules, hardware security modules, and basically what they do in the banking industry, financial, and all kinds of stuff where they really need to secure the secrets. And if you own millions, then you probably can consider yourself as your own huge bank. So what they do, they constantly run the currents through a very thin mesh, very dense mesh, and they constantly monitor if the current is still running and what are the voltages, what are the impedance, and all other characteristics. And as soon as you try to drill even a tiny hole into this thing, it just wipes all the keys. Yeah, so maybe you can do something like that, and even some state-of-art things. So that are 3 groups that are working on the ultimate defense mechanism, I would say. So one group of guys is using the reflection of electromagnetic waves from the inside of the casing. And then they are measuring the interference of this thing, and they use this input as initial data for decryption key derivation. This means that even if the device is completely turned off and someone tries to open it, then when it is turned on, there will be a completely different pattern of the reflections, and then the key will be different, and you can't even decrypt your keys. So similar approach using the waveguides, where you basically use interference of the light inside the random pattern, and also the mesh that is measuring both the impedance and basically the response of this mesh is measured on the boot to derive the key. So yeah, why should we limit ourselves? We can do all kinds of crazy stuff, but we should be very, very careful with the actual implementation. So here, well, this part I basically took from my London talk, but I think that we can quickly go through it. By the way, is there a way to check how much time do I have? Okay, so there is a clock, but it doesn't help because I don't know when I started.
You have 25 minutes.
25 minutes, okay, great. So if you are scared of the code, too bad. If not, this is a piece of code that is written in C, and C is currently the most common in embedded development, and it is really, really terrible because we can attack it in 6 different ways. And the only thing that it does, it checks the pin. And this is the kind of mechanism that, well, basically, if you can pass the pin check, then you can assign whatever you want, and then the attacker can steal all your funds, right? So what we have here, we have a certain pin counter that we will increase when the wrong pin was entered, and that will introduce the delay mechanisms. So then there is an enter pin, the correct pin that we will compare, and then some arbitrary messages, and actually our mnemonic, this is the most secret part that we have. So first, I'm assuming that you will, after this talk and after the workshop tomorrow, you will start writing your own hardware wallet right away. So these are the 6 ways how you can shoot yourself in the foot. First, if you look at this very nice and convenient C function scanf, what it does, it basically takes the user input and puts it into this entered pin buffer. Unfortunately, it is built in C, but it is not secure at all. And on every conference, everyone is saying, don't use scanf and don't use any other functions that don't know the number of bytes that are available. So basically what happens, we provide the input, we put the pin code here, then our program compares the entered pin with the correct pin, and then if they're the same, we pass. If not, then we kind of get back in the loop. if we write there more than 4 characters, then this function will just continue putting bytes in the memory. So if we enter 5678955678, then we overwritten the correct pin with our user input, and then now that's just because C doesn't really check the memory. Well, at least on the microcontrollers. On the computer it doesn't work. Yeah, then basically you have this and this the same, so you pass this in the pin. So the correct way to do it is use a secure function that knows how many bytes it can write there. Then let's look at another one. This function just puts into the message how many times we entered the pin wrong and then print it. So if we entered the pin from 0 to 9 times, everything is fine, and we were stupid enough to put here only this amount of memory. So basically, as soon as we get to 10, we have 1 extra character. The new line goes here where we had the end of line, end of string. And then when we print it, we will print you entered pin code incorrectly 10 times, and then the whole mnemonic. So very stupid bug that can directly print your mnemonic phrase. So yeah, it just happened that it was right after this message. Well, I put it there just for demonstration purposes, but yeah. Okay, so then another thing. Now it is what we use instead. We just allocate enough memory to have any arbitrary amount of wrong pins. If you look at this one, here we were checking the actual pin code. The problem with this function that is not designed for security stuff is that how it works, it checks the first characters. If they're not the same, it instantly returns to the false case. Then if we are lucky enough to get the first character right, then it will move to the second one and already compare the second one. The problem is that in this case it will take a little bit longer. So we are not comparing 1, we are already comparing 2 characters. And this is basically a timing attack. So we can just guess the first digit, then we move to the second one, to the third one, to the fourth one, and instead of 10,000 tries, we can get correct pin in roughly 20. And maybe for 20 there will be not such a long delay. Okay, so instead we want to use a secure version that compares the memory in constant time. Yep. Now, our thing is more or less safe. Now let's talk about using microcontrollers. So if we are using a normal microcontroller like STM, blah, 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 whatever, that is not built for security, then it has a certain kind of characteristic. So expect it to behave correctly if your clock is rising and falling with a certain frequency, and if your voltage is around 3.3 volts plus minus epsilon. So as soon as you go below or above this safe region, you get to undefined behavior. And what it means that basically you can encounter any weird kind of behavior. For instance, skipping instructions, calculating it in a wrong way, some numbers, and things like that. So for example, within the single clock of the microcontroller, there are a few things happening. So there is an instruction pointer moving to another instruction, and actually instruction execution. So if the attacker is lucky and he will be able to lower this clock a little bit earlier when we already moved to the next instruction pointer but didn't actually run the function itself, then we can skip arbitrary functions. For example, I said, the same happens if you drop the voltage at the right time. You also can skip instruction. For example, you can completely skip the wait delay. And then you can just brute force the pins without any delays. So yeah, you try 10,000 times and you're still fine. Then you can even exit the while loop completely. So just you glitch the device and you pass to the actually signing part. Then when you are printing the messages, how the microcontroller works. It calculates the length of the string, and then it prints into the, I don't know, USB, for instance, this region of the memory. So if we glitch during the calculation of the length and we make it some weird value, then we can actually print not just our string, but the string and then the memory that is followed after the string. So maybe there are our secret keys. So this is pretty scary. And unfortunately, it is extremely hard to deal with this kind of attacks if you are using the application microcontrollers. There are microcontrollers that are designed for security. And they're used in our banking cards, the government IDs, and also Ledger and Cold Card are using them. Trezor are not using them because of the ideological reasons, and well, they don't have to. They really work very, very hard to mitigate all these attacks on their software, but it's just hard. And then another thing. If all this glitching is not possible, you can get actually access to the microcontroller on the semiconductor level. So what you do, you put your microcontroller into the laser cutter, and they can actually just do it in the makerspace in Garching, and you pay like 60 euros per month to get access to the device. Then you remove the plastic from the top, you put a few droplets, of nitric acid, you heat it up to something like 100 degrees, and then it dissolves the rest of the plastic, and at the end you have an image like this. And then you can use your microscope. If microscope is not enough, you use ion microscope or electron microscope, and universities will be happy to give you access to these devices if you pay a little bit, because this equipment is expensive, and well, you know, they need to cover the costs. And then you actually can, if you know what you're doing, you can observe the photons emitting from the transistors that basically disclose your private keys. Or you can look at the input and output registers of the microcontroller. So you can actually extract the firmware. Even if the firmware is encrypted inside the microcontroller itself, it goes to the registers unencrypted. You just need to know what to look at. So another option is you take the laser and hit with the laser to a certain region of the memory, and then just change it in some way. Or using ultraviolet light, you can zero parts of the memory. So for instance, if you know where the correct pin is stored, then you can basically shine the use the ultraviolet light to erase it, and then your pin will be 0, 0, 0, 0. So not that hard to guess. Then if you shoot with the laser to another region, then you can reset the pin counter also. So all these kind of things. And so what people do in industry to prevent this from happening, they're using, for instance, the Faraday cage around the whole chip, such that you cannot dissolve it with nitric acid, so basically a metallic thing. Then you can put temperature and light sensors in there, such that as soon as you heat it up, you detect it and the keys got erased, and many other things. So, in summary, yeah, sorry, it was very scary, but basically, the problem with the secure microcontrollers is either you need to sign NDA, and for this you need to be pretty large, or you need to rely on the proprietary OS, like Java Card OS, for instance, or another alternative that I hope will happen in, I don't know, 5-10 years. We will actually build an open source secure hardware. That is my dream. But yeah, we are not there yet. For now, we can use Java Card OS for security storage, and basically, as I explained in the very beginning, there are chips that you can buy and just store keys there without even thinking what is happening in there. Yeah, kind of storing keys somewhere that you don't really know how it functions is also a little bit scary, but right now it's just the state of the industry. Then to mitigate all these kind of attacks, the software bugs, we can use memory-safe languages. So most of the problems happen because we used C there. So MicroPython is a very good choice. Another option is embedded Rust that appeared recently, and Rust in general is awesome because it was from the very beginning designed for security applications and for system programming. And they are now supporting certain microcontrollers. And there is even an operation system for embedded systems that OS that is written in Rust and allows all kind of memory protection and memory check mechanisms. Then, regarding the side channel stuff, what people in industry do and we still can do and is adding some random noise to mitigate the power analysis. So just as soon as you start encrypting or signing, you just turn on random power consumption noise. Or better not random, well, yeah, random is fine. Then you can use either constant timing everywhere, constant timing function, or add on top of that some random timing delays. For instance, you can use threads. Then your microcontroller code becomes really unpredictable because who knows when exactly it gets executed. And for all these kind of attacks that I explained in the beginning, it is very crucial for the attacker to make a precise timing. For instance, the guys on C3 Leipzig, when they demonstrated extracting firmware from Trezor using glitches, it took them 3 months to find the correct timing. I mean, this kind of effort. And then if you're using something custom that you built for yourself, do you think someone will spend 3 months on trying to glitch that? Well, depends on you. Yeah, but I just want to say that there are obviously different kind of threat models, and maybe you'll find this do-it-yourself approach also reasonable. Yeah, and obviously the Faraday cage or some kind of chip protection also works. So then for glitching and decapping, it is pretty hard to deal with, but you still can use all kind of watchdogs that write certain bits whenever they detect that the voltage drops below a certain value or something like that. It is a little bit advanced, so I really hope that at the end we will be able to make something that is secure out of the box, but I can't promise you anything right now. It's just dreams. Yeah, and all kinds of sensors and internal references. And for ultimate security, we can use the device level anti-tamper mechanism, either powered from the battery or the approaches that I told you before with this key derivation, so physically unclonable functions to derive the decryption. I think that's basically it. So thanks.
Right, any questions?
Hi, thanks a lot for the presentation. It was amazing. So in your presentation, you showed an axis in the beginning. You showed convenience versus security and attacker axis. Yeah, that one.
Yep, sorry.
Yep, that one. Mm-hmm. So I'm curious for tomorrow. The tomorrow's do-it-yourself hardware wallet. Where is it going to fit in these axes?
Okay, so tomorrow we are not using secure elements, unfortunately. So in sense of security, well, you definitely don't get any supply channel attacks there, just because you're using a general developer board, not a real hardware wallet. You can, so this point, the software attacks, it depends on your programming skills. Hopefully you're can make it secure enough. So I would say that it will be not as good as current hardware wallets, definitely. But on the other hand, it can be inconvenienced much better. So if you want to use something, basically that allows, that enables more from your kind of Bitcoin experience, So if you're thinking about some kind of custom scripts or something, then probably you will move forward here, but the attack will be probably somewhere in the middle. Yeah, so hopefully later it will change, but right now something like this. Yeah.
Next question.
So on the slide about side channel attacks, there's protection to use the protection is to use the random noise, right? But getting a true random in an embedded system is hard. And also it can be the influence from the outside. So what is the measures? So if you protecting from the side channel attacks with random noise, someone might either create
okay, I get the question, so
yeah,
I will answer it. For example, if you look at the elliptic curve signing algorithm, when we are using, about random numbers. Currently, many hardware boards actually have a hardware true random number generator. That is kind of okay.
But they depend on the environment.
Well, not quite. So there are a few ways. One is using the environmental noise. Another one using the shot noise on the resistor that is basically quantum mechanical. Then another approach you can also use in semiconductor industry. You can have basically a tunneling effect through the potential barrier that is also quantum mechanical. So in principle, you can have pretty good random number generators from there. Plus you can hash on top. So even if you have a little bit less entropy, you hash a few times, and then it's at least homogeneous across the number. In that sense, random numbers are okay. Regarding generating the keys from random numbers, I will get to that in a second. About random timing and power consumption. One trick, for example, that is used in elliptic curves, I think in Trezor's crypto library. Basically, you take your private key, before using the signing algorithm on the private key itself, you multiply the private key by the random number. Then, in this case, the power consumption, as it depends on this product of two numbers, will be already random. And then you divide again by the same random number. So the result, you still get message times the private key, but the multiplication by itself already is masked with this random number. Regarding the key derivation, so I think this is what worries most of people in general. How do you derive key, and how do you trust the hardware wallet to generate a random key? How do you think this random number generator, how good is it? So one simple example that we can do with do-it-yourself stuff. You plug the camera to it, so you roll a dice, and then you take a picture of the dice. And then you take this picture and hash it. And then basically you have a pretty good environment. So yeah, you can do it without a dice also. You just take a picture, and this picture plus noise from the sensor will give you a pretty good randomness. So this is a very easy way. Another approach that I think was discussed right now on the Bitcoin mailing list is using the shuffle of the cards. So yeah, if you want to do this, you can basically build a very small user interface where you just click what card you have next. So you get a random string. No matter how exactly you encoded the card, you just hash it afterwards, and then you have the same entropy that you had in the beginning in your hash, as soon as it's less than 256 bits, obviously. But yeah, so if you want to use not a hardware random number generator that you don't trust, you can add user input on top of that.
So you mentioned CoinJoin with hardware wallets.
Yes.
The problem with that is that the wallet has to sign a transaction when the user is not on the computer, but hardware wallets work in a way that user has to explicitly click OK for the transaction signing. So how do you imagine that?
Yeah, so if you're doing something yourself, you can use arbitrary policies in there. So for example, what you can do, you initiate the CoinJoin transaction where you define, okay, I want these inputs to be mixed with inputs of other people. Yeah, just a quick reminder. CoinJoin is when you take a few inputs, you mix it with inputs of other guys, and then you get a bunch of outputs, and no one can say which output corresponds to which input. So it's just a huge Bitcoin transaction. Well, in a simple words, Adam will probably tell more about that afterwards. So what we can do here, we can initiate the transaction where we say we want these inputs and we want outputs that in total give us, well, that send the money to our addresses, and that in total gives us roughly the same amount as our inputs, maybe a little bit less up to a certain input. And then click OK, and then our do-it-yourself hardware wallet can just wait until your Wasabi wallet will send you the actual transaction that we need to sign. Then our hardware checks that, okay, I have this inputs, I have this outputs, the user funds are decreasing by maximum few, I don't know, satoshis, so I should sign it. And it signs and sends it back to Wasabi wallet. So in that sense, if you want something custom with a delayed payment, then you can have it. Yeah, the same, by the way, goes to Lightning when you want to route the payments, but you don't want to click the button all the time every time you have the HTOC. So you can also program some kind of logic inside the hardware wallet that will automatically sign if the certain policy fulfills.
Yep. Right, Dario here, right?
Yeah.
Backing up the keys, something notoriously difficult across all the vendors. What are your thoughts on backing up with a DIY solution?
So I think mnemonic is more or less a standard way. If you want to add Shamir secret sharing on top of that, you can do this. I personally find Shamir secret sharing is pretty good solution. So basically what you can do when you're generating your mnemonic, so it's just a random number with a certain checksum. So it's a phrase. First, how you can improve. If you are setting up the hardware wallet for your mom that doesn't know English, then you can use your own dictionary. For example, my mom is a chemist, so I can use chemistry, I don't know, some organic molecules in the name of the seed, and then use that. Well, it will be very custom, so you probably will not be able to port it from your thing to something else. But in principle, you can use arbitrary non-standard ways to generate the keys and back them up. But I would personally use something like a standard English mnemonic that is split into Shamir secret sharing scheme. But yeah, obviously another way is you take your NFC tag and you encrypt your mnemonic into the NFC tag. Or, well, but then you need to remember the password for decryption this. And if you get hit by the bus, then all your family will have really hard time recovering this. But you don't care anymore. Yeah, so there are ways, I don't know.
Hey, just a remark. You mentioned that you're dreaming of one day we as a Bitcoin community will have one secure hardware wallet. But you also mentioned that everything is hackable. So I just want to make the point that we should eventually not look for one solution, but we should look for your solution. And that's why I think it's great that you encourage people to do your own hardware wallet.
Yeah, so what I meant is not like one hardware wallet, but more like we will be able to design a chip, actual semiconductor chip, that will use all these fancy industrial countermeasures like watchdog and countermeasures against glitching attack and so on, and still be open, that will not require NDA, such that, yeah, ideally we should have many of them, but we should have at least one at some point, right? Right now we have like 0. Yeah.
All right, we are closing the questions now. One last question. All right.
So imagine if you build this custom wallet, yeah, and it just fail. How much time you will need to recover it? For example, right now you can buy another Ledger Nano and then type in this mnemonic and then you get it.
Okay.
But if you build it by your own and it just burn out.
Yeah, so,
So
if
you need
you
time to
use out-of-the-shelf, thanks, I think you can go here. So if you are using the components out of the shelves, for example, the developer boards that we will use tomorrow, then you just reorder them. So I mean, what for tomorrow workshop, we have a standard developer kit from ST Microelectronics that costs like 55 euros. Then if you want to add some additional extension boards, they are also like variety of them that are available just to buy and wait for 2 weeks. So as soon as you don't solder something custom, it should be fine. If you do make something custom, well, maybe you want to have a spare.
Okay, we have 2 more questions online, which Daniel is dealing with now.
Yeah, so the YouTube live viewers are, I mean, there are 2 questions, maybe I combine them because they are both regarding the company you founded, and it's more like the question is, or the questions are like, what are the plannings in terms of retail customers, or do you only want to serve business customers? And the other one is, what is the business model, or I mean, is it just selling, or is it more like selling the hardware?
Okay, so first, we are working on the customer hardware wallet that we hopefully will release early next year. So it's yeah, okay. So I can't promise anything right now, but that's the plan at least. Then I really hope that together with this we will be able to make the developer kits such that you can basically buy it and have a secure hardware in there, and it will be hackable such that you can program whatever you want and put whatever extension shows to it. That's a hope. Plus, everything will get open source as soon as we release. So before we are not going to release anything because we need to keep certain advantage, because it will be stupid if we release everything and then someone builds the hardware wallet before we actually manufacture it. Yeah, and what was
like the business model? So what is the business model behind it? Just besides selling the hardware?
Yeah, so the hardware, selling the hardware obviously, but also my hope will be that we can integrate it, kind of partner with the services and companies that, for instance, running Lightning services and keeping their private keys like on the server, to move them away from the server to the real hardware, and basically making this kind of business-to-business solutions that can be tuned for different use cases. Yeah. And we are raising funds in like summer. Okay.
All right. Thank you for that. Thanks for being here. All right, that's time for our dinner break. The pizza has just arrived. It's still hot, so be fast, be quick. Or you can also go outside. We have some nice places to eat, to grab some food outside. And please be back at 6:30 as scheduled. And another thing, would be kind if you get your glasses and your bottles. Please bring it back to the kitchen. Would be great. Thank you. Konstantin here now, and he's going to talk about digital cash from scratch. Here's a trainer, a teacher for Bitcoin developers back in the US in Austin, Texas, and he's going to help us to understand how that all works. Thank you.
Yeah. So my talk is a little bit different from some of the other ones. I think a lot of the perspective we've seen so far is like we have this Bitcoin thing, and now what can we do with it, right? So maybe we can do Lightning with it. Maybe we can make hardware wallets, this sort of thing. And I'm going to sort of go in the other direction. It's like maybe we don't understand it so well. Let's try to, like, I'm going to give you a sort of an attempt to explain the Bitcoin itself, because I myself don't feel like I really understand it yet. So yeah, that's the perspective, and the way I do it in my class, the first thing we do is we try to implement Bitcoin in a series of little, I call them like educational shitcoins. They're like little attempts at digital cash that gets increasingly sophisticated and eventually have all the major features of Bitcoin. So I'm going to like run through this project with you guys. It's insane how we do it in the class, where we do it in about like 15 hours of videos. And so I'm going to try to cover the same journey in 30 minutes here. And so it's like doubly insane. So I'm going to sort of gloss over some things, but I think it's an interesting high-level journey on kind of motivating how Bitcoin is made, how it's built. So here it is, digital cash, a play in 6 acts. So these are the names of the shitcoins that we'll be going over. So here we start with PNG coin, and PNG coin is the worst coin I could think of. And I think it's informative to make a really bad coin, because then we can think about how to improve it. And so the idea with PNG coin is it's issued by the government. A coin is a chain of signatures transferring ownership of the coin. So that's what it is, a chain of signatures. And this is going to be the case as we go. And so what kind of signature, you ask? It's a PNG photograph of a physical signature. That's why it's called PNG coin. Ownership changes by appending more PNG photographs to the chain. So like the current owner is the one who is at the end of the chain. The coin is a bearer instrument. This list of PNG signatures could be emailed. It's actually digital cash, and the first transfer is special. It comes from this guy. I issue 10 PNG coins to Alice. That's how they're created. And you can inspect them. You go look to Wikipedia. You check, oh, okay, that signature matches here. Okay, Alice. Yeah, it's good. So on the left, we have a good signature. See, it's I, Alice. This would be the next one. Alice transferring it to Bob, right? It says, I, Alice, transfer 10 PNG coin to Bob. Signed Alice, right? The person who's transferring them matches the signature. That's good. Over here, I, Alice, transfer 10 PNG coin to Bob. Signed Bob. Signature doesn't match. It's bad, right? So let me give you a little demo here. So in the class, we start in a Jupyter notebook. And so it's like this interesting computation environment. And so here we have a class. PNG coin is a list of transfers. Very simple. And so here's a little function that can validate some user input and just basically extract a yes or a no, extract a Boolean. And then here, we try to validate a coin. We iterate over its transfers. We display that transfer. We ask the user, hey, is this valid? And because this is labor intensive, this coin. And if it is valid, we keep going, and at the end we return true. If not, we return false. So I will walk you through this. So here it is. It starts with him, that's right, and we can look, this all looks good, the signature checks out. So we'll say yes. Then another one shows up, I, Alice, transfer 10 PNG coin to Bob, signed Alice. Yeah, that looks good. And so this is validation. This is actual digital cash implementation. You could email this. It's a complete disaster. Down here would be a forgery, but I think let's escape and get back in here. So it would be a complete disaster because it has a lot of problems. It's easily counterfeit. Here's a meme generator that you could counterfeit coins with. I'll just open it. Right? You just go in here and send coins to yourself. Right? Like it's a bad idea, right? And so you can forge the transfers. You can make a transfer that isn't valid. It's easily double spent. You could make, if Alice wanted to make a photograph saying like, hey, I'm going to give it to Joe, I'm going to give it to Jerry. She could get two units of product and only give up one coin. Actually, she wouldn't even need to give up the coin. She could give it to a third person, right? So that's double spending, and it's really easy with this coin. Verification is labor-intensive and unscalable. That's terrible. It's the privacy it should be disastrous privacy. You actually have to have your photo of your signature, your name. It's really bad. It's not divisible, and there's an undefined monetary policy. So what's the most obvious problem? Physical signatures. Your physical signature is basically public data. Like Trump's is on Wikipedia. This is not what we should be using to issue or issue a money supply, right? It shouldn't be public data that's on Wikipedia. And so a person's physical signature also looks the same for every message, and that's also bad, right? If you see Alice's signature once, you can forge it on any message, right? Especially in a digital context. So we'd like to find a better way of handling physical signatures. And so this is obvious, like it's begging the question, this is a digital signature, right? There's a digital analog for this that is much better in the context of digital cash. And it'll fix counterfeiting and forgeries. Let me see the time here. Okay, 6 minutes. So, and it's a simple idea. So I'm going to walk you through like a little basic math here. And only you don't really have to understand it, but mostly just to understand like what a private key is, what a public key is, and what a signature is. That's what I want you to remember here. So let's all agree on a pair of huge numbers. Let's call this pair G. So it's a pair. Here's what Bitcoin uses, I think. This is a slide I made a long time ago. So they're like really big numbers, right? But they're just numbers. Anybody who wants to create a digital signature must generate their own random number, right? You can ask Stepan how to do this. He's an expert on good ways to do this, and it's not easy to get a real random number. And so you keep this secret. It's called your private key. Then you can multiply P times this G, this pair, and if it's like a scalar times a pair, so it'll get a pair. You just multiply them pairwise. And this is your public key. And you do it with a special type of multiplication, which I'm going to completely gloss over. And so in order to provide a signature of a message, let's call it M, with a private key P, you generate another random number. And this R is this thing that Stepan was talking about where Sony was reusing it. This is the thing he was talking about. So you perform a calculation on M, the message, R, the second random number, and P, the private key that it's sort of long-lived. R is short-lived, P is long-lived. And then you produce this S, which demonstrates the possession of the private key P, but doesn't reveal P, which is miraculous. It's like you can, you give someone a signature of your paper signature without actually demonstrating what your paper signature looks like. It's vastly better when you compare it to this ridiculous, stupid case of P and G coin. And so if Bob can produce these three R and S basically, given an M and given some P, we can conclude that he's got this private key, this lowercase p, and he doesn't reveal it. So that's like a big win. It'll be a lot better for issuing the coins. It'll be a lot better for transfers. And the signature is different every time, right? Partially because we base it on a new random number that each time, but also because you mix in the message. So even if you reuse the nonce, the signature will be different as long as the message is different. And so if we can cook up every time our message be different, then we're really in business here. And like I said, R is the same nonce that Stepan was talking about. And so this is just kind of a view of where we're at. A coin is a chain of signatures. The signatures are not photographs, they're ECDSA coins. And the first one is signed by Trump's keys. And again, in my class, we actually code all this out, which is really a fun exercise. Everything else is the same. So, who needs a blockchain when you got a sig chain? This is the thing I'm going to try to popularize. It's like the next big idea. No, I'm kidding. It's terrible. So yeah, let's revisit some of the problems here. So counterfeiting, it's a lot better because digital signatures are harder to fake. Transfer is easily forged. Again, we're good there. And we went from horrific privacy here to just bad privacy because we replaced names with public keys, and public keys are at least you can be kind of pseudonymous with them, and it's a little better. And then one of the two talks from now we'll learn a lot more about this. But Bitcoin still isn't great at it. So now what's our biggest problem after this ECDSA coin? This is our second shitcoin. What's our biggest problem? It's double spends. The double spend attack I just talked about is still possible. You could go and create multiple transfers for a given sequence of transfers, right? Because that's what a coin is in this contrived example. And you could send them to a few different people, and you could get multiple pieces of product for one. Let's just say ECDSA coin. You could still double spend. And so now we're to our third act here, bank coin. It uses the time-tested centralization or double spend solution, get a central authority, right? And it works. So here's the idea. It's like, here you are. Can you see my mouse? Yeah. Here you are. Alice just gave you a coin, right? How do you know that she hadn't given it to Bob already? That's the assurance you want, right? You want to know that this is going to you and only you. Currently, we have like subjective point of view, right? Validation is in the hands of the individual. And like we celebrate that in Bitcoin, right? That you can validate things in your own, but it's only because it's designed well. Like in this context, validation on your own is terrible because it's not sufficient, right? Like you don't know that someone else, you don't know what other people are up to. So we need a shared source of truth. And so here's kind of the idea: is like whenever you want to move coin, this isn't the best slide, but whenever you want to make a transaction, you don't send the transfer to the person. You just tell the bank, right? You only have a relationship with the bank, and the bank will just update their database. It's a canonical list of every transfer. And when you want to see whether a given coin belongs to the person you're doing business with, you just ask the bank. And this is a little glossing over it here, but yeah, there's code for this. And so yeah, but buy Bankcoin. That's I wouldn't recommend it, but we're making progress. At least we've solved the double spend problem. But and along the way, this is what we do in the class. I'm going to gloss over it again. This is a good time to replace this simple transfer object, right? This is basically a transfer will have a public key of who's going to own it. This is the next owner, and a signature, basically a signature of the kind of from the previous the private key of the previous owner, right? So this is how the chain would work. And let's move to more Bitcoin's model, right? Where you have a transaction, which is a mapping of inputs to outputs, right? It spends outputs and creates new ones. The inputs will have an ID and an index. This is basically the location in the set of all previous transactions that this input is spending, and then the signature that sort of performs that spend. And instead of a script here like Bitcoin, we just have a public key because we're trying to keep it extremely simple. And so you can do a lot of, you basically get better divisibility by doing this. And so this is like, you can see why this is like kind of how Bitcoin works, right? And so you can get complicated stuff like this. It's a picture from Andreas's book where you can get, this wasn't possible before. We didn't have denominations before. Every coin was just one, right? We didn't even have amounts, right? So we got a mount. That's good. Another thing is UTXO set. So currently we just have this list of every transfer ever, right? If we want to see if a given, if we want to see who owns a coin, if we want to see if a spend is valid, we have to like basically traverse the entire history of every transfer. And it'd be better to cache it, right? And that's all a UTXO set is. It's just a cache of the unspent ones. That's all you care about, right? As long as you can trust that it has integrity, that's really what you want. And so the UTXO set, in a pragmatic sense, is just a cache of the ones that haven't been the outputs that haven't been spent yet. And so I never thought of it as a cache, but I think that's a good way to explain it. And so yeah, a little bit. A coin is just an unspent output now. Like Bitcoin. Coins are transferred when the bank accepts a transaction. Remember, transaction is just a mapping of inputs to outputs, just like Bitcoin. And coins are issued with special transactions. The first input is signed with Trump's keys. So that's how you know it's good, right? Because we're still very centralized, right? Sorry. So now what's our biggest problem? Well, this isn't digital cash. We have an intermediary that's involved in every transaction, the bank, right? And so this is like kind of, I think, where the state of the art was kind of before Bitcoin happened, is like, well, we could solve a double spend problem, but not in a cash way, kind of, in a sense. Well, yeah. I mean, people tried, but yeah. So that's kind of it's another meme. What if I told you there is no coin? It's just like at this point, it's just rows in a database, right? And the bank controls that database. There's like coins only exist according to their whims, and that's kind of the case of fiat money today. And so here's the next act: Blockcoin, decentralize a little. So let's try to reduce the monopolist's control over things, right? The bank, Trump. I use him just to piss you guys off. Oh God. So here's like Blockcoin's basically EOS, right? It's like right. So Blockcoin's basically EOS. So let's try to create a federation. Let's create a cartel that are banks. And so the way it works is you have n banks. They agree on validation rules. Each bank gets an ID, right? Which is in a context where you don't have n banks, that's actually really hard to do. Like who gets the next ID, right? But in a context with a fixed number of banks, you can do that. You can just, and it doesn't matter who goes first because you're going to go around the circle many times. And so let's say every m minutes, we nominate, these banks alternate nominating a set of transactions. And that basket of transactions we'll call a block, right? Just a set of transactions. And the non-nominating blocks will verify. And this scheme spreads out the power a little better. A cartel is probably better than a monopoly. And here's the way it works. I'm not a very good artist. But you know, bank 1 goes first, then there's bank 2, then bank 3, and it just kind of goes around. And so at this point, we haven't actually discussed how to send stuff over the internet. I just said like, hey, you could save a PNG coin to a file and email it, right? That's my verification that it's digital cash. And so in our class, we go and start making a network protocol here. You know, how do you connect to an IP address and send raw bytes, right? And I'm going to gloss over this, but I think this is one of the really fascinating things about Bitcoin. And in my workshop tomorrow, we'll do this on the real network. And it's one of the, I've learned a lot. I think it's just fascinating that we can create such like an organic beast like Bitcoin with just sending like numbers from 0 to 255 over a wire. It's absolutely remarkable to me. So yeah, we start doing this, and here we go. Now that you can send it over the internet, it is magic internet money. This is Blockcoin. I cracked myself up. So what are the problems now? Censorship. The banks could still ban certain coins, certain outputs, and their political identities still, right? So it could be in their interest to do this, right? Because, you know, they're not like they wouldn't be a pure market phenomenon most likely, at least in the world we live in. So yeah, let's move one more step, called POW coin, proof of work coin. Let's move from a bank cartel to like kind of be your own bank. Everyone's a bank. Let's try it. It's a good idea, right? It's the direction we're moving. And so here's just like a list of traits of money that I took from Vijay Boyapati's excellent essay. And so we're doing pretty good on these. Fungibility is not so good. Portable, right? We have an internet protocol, durable. You know, you can save files in databases backed up by a bunch of people. A bunch of like a cartel, that's pretty good. Verifiable, cryptography, divisible, right? We have the transaction inputs and outputs. We could issue a large number of coins, and so those are all pretty good. These two are not good: scarcity and unforgeable cost, and the censorship resistance. So, right, not scarce because you know, the cartel basically gets to choose what the supply is, no guarantees on supply schedule, and there's no cost behind issuance. So, like, scarcity and cost, like this unforgeable cost, are like these really profound ideas that are like somewhat related, not exactly the same thing. And then, so lastly, at the end of the day, block producers can do whatever the hell they want to this UTXO database. They can blacklist. They can do what they want. And politics is our only resort if they misbehave, and that's obviously not what we want in a digital cash protocol, right? So, so let's look for some analogies. Like BitTorrent is a pretty good example of a censorship, a technology that achieved some degree of censorship resistance. Let's just like kind of use that as an example and try to complete this logical progression from bank to cartel to like peer-to-peer network. Make sense? Just one more step. So here we are at my beautiful drawing. We have nodes, 3 nodes, and so what happens when this next one joins, right? Like, what's their block ID, or what's their ID, right? We had three IDs. Like, what happens if these 2 nodes join at like the exact same moment? Like if half the network sees one of them first, the other half sees the other one first. Like, how do you sign node n plus 1? Basically, there's no, yeah, and like here you go. What if one leaves, right? What do you do with the nodes, the node IDs? Like, you know, as I understand it, there's really no good way to do this. And even if there was, you'd be vulnerable to so-called Sybil attacks. And what a Sybil attack is it's like you, in a peer-to-peer network, you create a bunch of nodes that look like they're independent, but you actually control them, right? So they sort of do your bidding. And this is really dangerous if it's cheap to create nodes. And so, so in this setup now, everything's cheap, so we're super vulnerable to these, right? Like, this is how you take over the network, is you spawn a bunch of these little mindless nodes that do what you want, right? And so back to the drawing board. So like, this is the kind of a, like, I don't know if from here on out, I don't know if I explain it very well. This is like me trying to convince myself I understand what's going on. So to me, it sort of seems like there's some sort of relationship between the censorship and the scarcity. Like I was saying, we have these Sybil attacks because block production isn't costly. It's so cheap, right? So you can just flood it with these sort of spies, so to speak. Like, what if we make it more costly, right? What if we make supply sort of more scarce? Maybe there's like, it's kind of related here. Like, what if we approximate the honest assignment of round-robin IDs, right? Round-robin just means in a circle. I don't know if Germans know that word, round-robin. It's just like go around in a circle. We approximate the assignment of round-robin IDs by instead awarding block nomination privileges for like the next block in proportion to the, or I guess overall, in proportion to the consumption of a resource that we hope nobody can monopolize, right? So the idea is like we're basically trying to approximate what we had with Blockcoin. And so we get censorship resistance by assumption, right? We assume that no one could monopolize the resource. And as long as you could get at least a little bit of it, you could get your transaction in, right? You could get in a block as long as no one can completely dominate. And it would be Sybil resistant because participation would be expensive. You'd have to consume this resource and prove that you consumed it. So there's sort of the interplay between these sort of two ideas, at least as I see it. And so here we go. I mean, this is obviously like Bitcoin, right? What if we, like gold, what if we demanded solutions for computationally intensive math problems, right? And so here's hash cache. This is, it's not just any old problem that will work. Like, you don't want a problem like Euclid's algorithm, for example. You're trying to I think it's like factor large numbers or something, or whatever it is, find the least common denominator, the greatest common divisor of two large numbers. Because with a problem like that, the fastest computer will win every time. So it's an important insight. You don't want a problem where the fastest computer will win every time. You want a problem where the fastest computer will win kind of in proportion to the amount that how much of the network, how much of the power they have, right? And so they can't dominate. And so here's the idea. We've seen a block, right? And here's this hash function, which is this magical function that outputs 256 independent ones and zeros. And so you put this block together with a nonce. It's just a small number, or not a small number, a number. And you run it through this function, and then you get all these zeros and ones. And so the chance of any one, and they're independent, right? There's no relationship between these. So it's like coin flips, basically. And so the chance of any one digit being 0 or 1 is 1/2, right? So the chance of n leading 0 bits, or 1 bits, whatever, or at the end, or in the middle, who cares, is 1/2 to the n. So it's just like coin flips, right? Repeated coin flips. And so if someone can present a block and a nonce where you do this, and you get a bunch of leading zeros, on average, they ran SHA-256 2 to the n times, right? And that's expensive. Doing operations on a computer take energy and heat and everything. And so, that's where the cost is. And so, yeah. Here's a little. I got to speed up a little bit, but the question is like, why will they do that, right? Like, why will somebody do this? Why will somebody be so generous to secure our network for us? Well, we'll pay them. Basically, that's the answer. We'll pay them. They wouldn't, so we got to pay them. And so we'll give them Coinbase transactions, basically. And so this will kind of recoup the cost of mining, I guess, and it's a more incentive not to cheat because you get something valuable, right? You don't want to lose that. So yeah, Coinbase transaction. Every block, the miner sticks in a transaction that pays themselves, and that's their responsibility. And yeah, just like Bitcoin. And so here's this kind of like chart I made that, I don't know, this is just how I kind of think of it. Like, so on here you have these two features we've been talking about, and here we have these two properties, right? And so like, you kind of achieve, the miners achieve scarcity because like SHA-256 is costly. It's just like, there's only so much energy, right? So you could, it's like, there's sort of like a cost there, right? And cost and scarcity are kind of related. Censorship resistance from the mining in the sense that you got to monopolize hashing in order to monopolize transaction processing at the moment, and we assumed you wouldn't be able to do that. Maybe it's a bad assumption, right? We've gotten close in the past, and then on the peer-to-peer side, right? The scarcity would be kind of enforced by validation, the transaction rules, the monetary policy, etc. And if people aren't doing it how you'd like to, you want it done, you can go and mine yourself, right? And so the censorship resistance now, just like BitTorrent, you have no honeypots. To kill the network, you'd have to kill every node, sort of. So I don't know. This is just kind of a way I look at it. I kind of make sense of this whole. So there's no bank, right? There's no like cartel you can go to and say, hey, this is on the blacklist, right? You could go to all the known miners, but someone else might start doing it, right? Like it's maybe not no, but they're not as important in like if you just have one bank. Does that make sense? Yeah, maybe not the best way of saying it. And so yeah, some details. You got to have. I'm going to skip through this. You need to be able to have people join the network, and this is like Bitcoin's version handshake. You need people to discover each other. You need to have peer discovery. So you need to say, hey, who do you know? And they'll tell you who they know. And so you can sort of discover new nodes that way. And so these will be new network messages in our network protocol that we talked about a little bit. And then you need initial block download. You need to be able to say, hey, these are the newest blocks I know about. Could you give me the next ones? And lastly, we need chain reorganizations as a dispute resolution mechanism. If you have everybody all over the world sort of mining on their own, you're going to have disagreements. Like you're going to have two blocks that happen at the same time, or two mine blocks that happen at the same time. So you got to just let that play out and let people kind of decide. In order to do that, you basically have to be able to undo blocks as the network rejects them. And so this is kind of a little graph. Don't try to understand this. This is just some new network messages that you could send back and forth between nodes, which we actually implement in this little project. Here's how you do initial block download. You just say, like this would be the, join the network, and these two would be like discover new peers. This is how you do initial block download. You just say, send a sync message with your recent nodes, and they'd send you blocks in return. And here's how a chain reorganization would work. And this is, so the idea is you'd have, I think I'm running out of time. So you'd have these, this is how, this is the blue chain's your main chain, and you see like kind of a competitor, right? And all of a sudden it's overtaken, right? The question is, how do you back out and like get back on that purple chain, right? You basically need to do the opposite of accepting a block, and implementing this is actually a lot of fun. It is really interesting. So yeah, you just do the reverse of what you do when you accept a block. And so here we go, another meme. So SHA-256 is painful, right? This is the miner, basically. And here's the network. It's like, just keep going. You gotta, we want this security. So it's kind of like, it's a painful thing. So what are we left with? We have an inflation problem. We have no monetary policy. If a bunch of new supply of miners comes online, we're basically screwed. You're gonna have huge inflation. And so, yeah. We needed it to incent mining participation, but it's basically wealth confiscation, so we should try to eliminate it. So I kind of look at it as like you have two inflation problems that Bitcoin solved. One is like the global inflation problem. This is like, let's try to reduce the block subsidy over time as we get adoption. Right? We don't want to confiscate wealth forever. And the other one's like a local inflation problem. This is like if a bunch of new miners come online, how do you make the sort of block by block issuance respond to that, right? If you have 10 times as many miners, you don't want 10 times as many new coins issued, right? It's like just hyperinflate, right? So those are two ways of those are two different inflation problems we need to solve. And so the first one is happenings. basically, you all know how halvenings work, so just skip through that. And the second one is, well, maybe you just every n blocks you cut the subsidy in half. And important, you need fees in order to basically make up for the incentive. And I never thought about fees as like a monetary policy thing, but that's the way I think of it now. It's like vital to having a monetary policy, like to stop or slow down our issuance, you need fees. So that's the way I look at it now. And right, more people mine. There are more guesses being made, more blocks being mined. That's inflation. So you want difficulty adjustment. So we have these like difficulty periods. Every n blocks, we sort of recalculate how hard it should be. And so I'll just show you this this little. Can you see it? I drew this. So this is like the first difficulty period, right? Every block needs 15 leading zeros, right? Let's say the duration is below the target. It happened too fast. It means we need to make the problem harder. So let's just increment, go up to 16 bits. One more leading zero. Let's say here the duration was too long. The problem was too hard. So we go back down, and then we go back down again. So it's just like it just checks based on a target of whether we should make the problem easier or more difficult. And it's actually really easy to implement. Bitcoin is a little more complicated. And so yeah, let me give you like a really quick demo. So like at the end we do we implement this thing in, I don't know if you can see that very well. So we implement, if this will work, yeah. So we write all this that it's going to run in Docker. And so this is going to spin up 3 nodes that actually can do all this stuff. So the first node comes online. It tries to handshake with the other 2 nodes. They're offline because they start every like 5 seconds. And so it's started mining. It can't find a block yet. And so you can see you have like a main thread. You have a miner thread. You have a server thread. So you have a couple different threads that do different things. And here's node 0. Right. So on the left is which node. Oh, sorry. The logging got jammed up for some reason. This is like Windows subsystem Linux, so it doesn't work very well. But as you can see, like now we have 3 miners up there. They just mined a block at height 8. Here's a difficulty adjustment. You can compare the bits went from 16 to 15. Yeah, so we learned how to do that. So like somewhere there's probably a reorg. Yeah, that's it. That's my talk. If you want to learn how to do this, you can watch these videos. There's a link and there's a Git repo with all the code. And I do this as part of my little class called Bittle Bootcamp. This is the way to think about it. It's like I take in people who are interested in Bitcoin, and I try to like output open source contributors. That's what I try to do. So yeah, we do this, and then we actually deploy the network, which is fun. That's it.
All right. Any questions on that?
No questions about my shitcoin?
You don't have to, but all right, in case.
Oh, so yeah, so hopefully I'll post these slides, I guess. Like justinmoon.com is my website. Maybe I'll post them there too. Yeah, find me on Twitter.
Okay, no question. Oh,
Michael.
there's one.
Well, I did a free class, which I recommend if you want to learn. Like, teach a couple of your friends. And this guy was like one of the 3 people that would show up every week. So he's the one that encouraged me.
So there's one problem you didn't discuss, which is scalability. So could you outline? Could you outline the steps of going from Donald Trump Lightning to?
It's actually a good question. Like, it would be really like with a few modifications, you could add like output level time locking, like Bitcoin, right? And you could make a Lightning channel. You could make a channel like you'll learn in the next talk, and like you could actually do this. And I've had a couple students who played with it a little bit, but yeah, I mean, it's a really like you could make your own little mini Lightning on top of this, and I haven't done it yet, so I don't really know how. That's a good question.
Anybody else? No. All right. Thank you, Dan. And we move to the next speech. Thank you.
Sorry, I went over time.
Don't worry.
So, yeah, this is if you want to get the
Okay,
clicker.
just something in between. So guys, please, can you take your bottles, your empty ones, when we start the next way, can you please put it, remove it, bring it back to the kitchen. Thank you so much to help us to get this clean here in the end. Thank you. We got the next one here, this is James. He's currently teaching Bitcoin protocols in London. But he's flexible, he can go wherever if you need him. And today he's going to talk about payment channels, how you do that, for example, with Libbitcoin or on other networks. He's going to be with us in a minute, and well, I'm looking forward to this speech. It's got his cable. You got your cable?
Yeah, I think it's all mic'd up. So I changed the topic of the talk a little bit. I was going to do more demo stuff, but I thought it'd be nice to explore the protocol design of Lightning a little closer. And there are a couple perhaps non-obvious subtleties in there which I think are pretty interesting. I recently did a short YouTube video on payment channels, and so I want to review that, but also expand on that a little bit. So quick thing. Who am I? Why am I here? What have I done? I started learning Bitcoin by reading Libbitcoin source. So you guys, maybe some of you guys know that. It's the oldest alternative C++ or oldest alternative implementation to Bitcoin core that there is. And the reason I started reading Libbitcoin was I couldn't read the core source code. Like the style just killed me. And in the process, I learned a lot about what is implementation, what is protocol. And then I provided the first documentation for Libbitcoin. In recent months, Eric, who's the lead maintainer of Libbitcoin, has dragged me to a couple of meetups where I do like quick Libbitcoin trainings or introductions. That's something I really like to do. In recent months, I've also started doing more things around education. I started teaching Bitcoin protocol at Swiss universities. I'm based in Switzerland last year. And very quickly, the guy who organizes the Bitcoin community in Switzerland started a company to do Bitcoin education. That's 21 lectures, so that's an in-person class. And what I'd like to do is I'd also like to teach the class in a little more expanded form online, which is teachbitcoin.io. And so my end goal really is, the reason why I went on this journey is that my end goal is really I want to understand the protocol better. I want to contribute to the protocol research. And that's something I continue to working on. Okay, these are the things I want to cover today. I'm going to start with payment channels, and then we'll go into more interesting things like payment routing and future protocol work. And I think there's some pretty interesting conclusions that we could draw there. Okay, so what are payment channels? We'll start with the channel states. Essentially, a payment channel is a negotiation between two peers. And during the negotiation, we try to update the balance between these two peers. And we apply this update to the balance, so we update the state of the channel. And part of the design of this protocol is to be able to deliver that balance to spendable UTXOs on the blockchain, right? So we've got this negotiated balance between two peers, but what I want to do is I want to be able to walk away from this channel and transact my share of the balance through Bitcoins. And so we need some kind of mechanism to deliver that. We're talking about two peers right now. So that's what balance delivery is about. So when we talk about payment channels. So to be able to deliver a balance, we need to fund this whole spiel somewhere, right? Otherwise, we would be creating coins out of thin air. If I create outputs on the delivery side, they must come from somewhere. So there's a funding transaction, as you probably all know, that spends to a multi-sig output. And the funding transaction then is spent by a commitment transaction, which is the first state. So when I open my channel, before I've done any transaction, I have an initial state. That's captured in the transaction right there. I don't broadcast it though. I sign them together. I send them together because if I don't have a commitment transaction before I sign the funding transaction, I have this multi-sig output, which basically locks the funds, and I can't release it without the cooperation of the other peer. So they're signed together, but only the funding transaction is broadcasted. And now we have an open channel. And what we can do is we can update these states. We were talking about negotiated balances on the top before. They are reflected in the commitment transactions which are signed by both parties. We update these transactions as we go. We create a new commitment transactions for every channel state that occurs. And then when we want to complete the channel, we want to walk away, we broadcast the most recent transaction that's confirmed on the blockchain. And now these outputs, or the most recent balance of the channel, are spendable on-chain, right? That's what we want. Okay, so quick detour. Payment channels require SegWit or witness transactions, and the reason is because of transaction malleability. So before SegWit, the TXID of a transaction could be changed. We had input signature, input script malleability. The signatures are malleable, the input script themselves are malleable. And with SegWit, we've moved the entire input script data object outside of the transaction. So whenever we have a transaction chain, as we do in payment channels, we have a child transaction spitting a parent transaction. And if the TXID of the parent transaction changes, the child transaction necessarily becomes invalid. So the witness transaction that was solved. Now the funding transaction is a witness transaction, right? So we don't have this malleability problem. Okay. Now we have a further problem that we have to solve. In our current design, we have no way to invalidate older states. As you move along in the payment channel, you want to update your state, but you want to make sure that the old states are revoked, that they can't be broadcast or they can't be used to benefit perhaps another party, right? So a party broadcasting an old state has a possibility to roll back the state of the channel. So we want to prevent that. As you can see here, in our current design, all commitment transactions, all states are all equally valid, right? They're all signed. So we want to be able to revoke the old ones. We do that with RSMCs, revocable sequence maturity contracts, and that's just a outputs contract that can be spent under two conditions. The first one is spendable by the primary recipient after a delay. And the second condition can be revoked cryptographically. So the counterparty, if the counterparty receives a special half of a penalty private key, the counterparty can then spend this output immediately. So let's see how that works. I have these revoked outputs. That's important takeaway. If B broadcasts state in the middle, B benefits, right, because he has a higher balance than in the most recent state, and that transaction is actually valid. So it will confirm, it will broadcast on the blockchain, but the output that pays out to B has been revoked and therefore can be swept by A. So by the penalty transaction. Okay, just to recap, we now have a payment channel. We have one state that is valid. We revoke all previous states that are not valid. And we can talk about a couple more interesting things. So fundamentally, when I have a balance in payment channels, I think one conclusion that I like to take away is I cannot equate those to spendable outputs on the blockchain. So if I have, I don't know, 10 Bitcoins in my Trezor wallet, those are UTXOs confirmed with a certain height. The security that I associate with that amount is not the same as the balance that I have in my Lightning or my payment channel. And the reasoning is because the payment channel that is still open, in order to be able to actually deliver those outputs to the transaction, I still need to first broadcast. I needed to confirm, and so that's essentially a security trade-off for more transaction throughput, right? Okay, there's a second observation we can make. The balance negotiation that we have in a channel is in arbitrary units. It can be anything. Once we try to connect it to a delivery mechanism where we deliver to a network, we are restricted because in Bitcoin I can only transact in Satoshi. That's the smallest nominal unit. So what happens in Lightning, for example, is I can transact in milli Satoshi, and I will then round down the units. I'll round it to the closest Satoshi in my commitment transactions. So that gives me the advantage of being able to transact in smaller units in the payment channel, but the accuracy of the balance delivery is decreased. So that's another trade-off that is pretty interesting. Okay. So now we have payment channels. So those are like the core primitive of Lightning. And what I want to talk about is how the routing works. So routing, basic idea, I have multiple channels between multiple peers. So A is connected to B with the payment channel, B is connected with C, C is connected with D. And what I want to do is I want to forward a payment to D, and I want all the channel balances to be updated to reflect this forwarded payment. And the incentive for any intermediary node to do this is through the transaction fee or the forwarding fee that is associated with this forwarding. So the amount that A forwards to B will necessarily be higher than the amount that B forwards to C because there's a fee included in there. Okay, so how do we set this up? The first primitive that we talk about is hash locks. Hash lock, as you probably all know, is simply a contract script that can be a lock with a pre-image. And we want to construct a route beginning with A. D creates a payment hash that's in your invoice. So whenever you do a Lightning invoice, there's actually a payment hash embedded into the QR code. And then the payment hash is forwarded with the onion routing packet. And as the onion packet is unwrapped, every node along the way gets the information that it needs to forward this hash lock in the next payment channel. So it knows what amount and to which node it needs to forward to, And once we've completed this forwarding, we now have committed, this is the important part, we've committed the forwarded amount to a hash-locked output. So the reason why we want to do that is because we want to make sure that with this amount that we want to forward is actually available somewhere in a payment channel. This is the mechanism to do that. So we know it could theoretically be routed, it's locked, it's pre-committed, and if we look at the commitment transactions, so what we're seeing now is a single snapshot of the state of each payment transaction. This, before we had a time series, now this is the most recent channel state in each of these 3 channels. And as you see there, we have this output, which is hash locked, right? So the output necessarily decreases. There's a fee that's subtracted, but this output spends to the receiving peer under the condition that the pre-image is provided. Okay, so how is this payment then ultimately unlocked and propagated backwards? The pre-image is released from D. So D either can close the channel by broadcasting onto chain, and since he has the pre-image, he can spend this output with that pre-image, since the block is locked to the hash lock thereof, right? He can also, or it can also propagate the pre-image backwards, and it can negotiate a new state with peer C without having to close the channel, update and absorb the locked amount into the regular outputs of the commitment transaction, and as we propagate back the pre-image, we can conclude the forwarding and the hash locks are released. The reason why we have to propagate backwards is because if we were to propagate it forwards, which theoretically we do, let's say a peer receives a forwarded amount of funding, the peer actually has no incentive to forward it farther along. So it always has to be forwarded backward in order to maintain the incentive to participate in this thing. Okay, so we introduce one more primitive. We introduce time locks. So what happens if this construction doesn't happen successfully? Because Bitcoin scripts can only enforce things on chain, and in this case they only enforce things between 2 peers, we need to find a way to recover if this coordination of multiple peers or multiple channels fails, and we do that with timeouts. So if the pre-image does not propagate backwards over a certain time, the hash locks necessarily just release, they unlock. The time locks from channel to channel have to decrease, and there's a good reason for that. So let's say the HLCs time out. The amounts from the HLCs are now, or the hash locked outputs, they're now absorbed into the regular outputs. And the reason why the timeouts need to be in decreasing order and not the other way around is because it can happen, otherwise it would happen that I might have a timed out transaction here, the amount is absorbed into the sending peer, but C has already forwarded the amount on this side, right? So that's a bad situation. So that's why we have those timeouts in that order. Okay, now we can have a quick look at how HTLCs are designed. We've kind of said what they need to do, right? They need to be able to lock funds in the hash lock, and they need to time out. These are the 2 basic requirements that we provided to the protocol. So we also need to add one more thing. We mentioned that commitment states need to be revocable. So every time I have a new channel state, I revoke the old one. The same goes for HTLCs. In order to revoke it, I now add a 3rd spending condition, which says the HLC must be spendable with a verification key, and to give the counterparty time to spend it, we add a delay to the spending scenario that benefits the broadcasting peer. So let's see what happens. So if I have a revoked state, in this case B broadcasts the revoked state that it has, I now have a delay. The delay prevents that broadcasting peer from spending, right? Even if he might have a pre-image, a success spend, the counterparty can revoke with a secret R because it's an output that's been revoked. There is a problem, however. Generally speaking, we want timeouts which are shorter than delays. A timeout is the way an HLC or routing recovers from a failed routing. The delay needs to be long because it gives the counterparty time to react to an invalid state broadcast. So in this case, what can happen? If I have a valid state being broadcast on the chain, I have B broadcasting its commitment state, and it wants to spend it with a pre-image in a success spend, right? It has the pre-image is propagated back, and it wants to spend it. What can happen is, if the delay is so long, the HTLC can time out before it can make that valid spend. So what happens here? HLC times out and is spent by the counterparty. So what we have here is a coupling between the delay and the timeout that is in the HLC. So we need to find a way to solve this problem, to decouple those two. And the way we do it is with a two-stage design. And so you'll see in HLC output, every HLC output will have its corresponding second stage timeout or success transaction. And the timeout transaction, for example, spends the HLC in the timeout scenario. The counterpart, we have a symmetric design for the other party. In this case, it is the success transaction that spends in the success scenario. And what we've done here is, I can show how that works. So we have a revoked state. B, the receiver of the channel broadcasts the state. It can immediately spend the HLC. We no longer have the delay. It can immediately spend it with the success transaction, assuming it has the pre-image. However, since it is a revoked state, the output of the success transaction is revoked. The delay applies, right? Meaning delay necessarily because it's RSMC B, and because it is revoked, it can be swept by the counterparty with secret R. So what we've done here is we've decoupled the timeout from the delay, and that's more obvious when we look at the timeout spend. So in this case, the peer A has broadcast the revoked transaction. It can, right after the timeout, it can broadcast the timeout transaction, but the output of the timeout transaction has been revoked, and so that's when the delay begins, right? And obviously the counterparty can spend whenever with the revocation secret R. Okay, so that's why we have two-stage design in HTML-C. Okay, so today we have single-funded channels. I want to talk about why dual-funded channels are possible and why they're a little trickier. So let's look at how a single-funded channel is set up today. We have a handshake, and the first thing that we do is the funding peer will forward the funding out point to the counterparty, so it can then sign the commitment transaction. Right? So only one peer needs to actually do the funding transaction. It needs to construct it. It forwards the TXID and index to peer B. Now peer B can construct this commitment transaction because it knows what funding output it's spending. And now peer A can sign. They countersign each other's commitment transaction. As we remember before, the commitment transaction needs to be assigned together with the funding transaction in order to be able to broadcast and open the channel. So important here is, because only one person is funding the transaction, at this point, peer A could never return or reply or walk away, and peer B would have nothing to lose. So it's a very relatively simple and secure way of setting up a channel. Right? So if peer A signs and broadcasts funding TX, if peer A aborts here, peer B can safely ignore. So that's single-funded channels. If we look at dual-funded channels, it becomes a little more complicated. So in the first, after the handshake, in the first step, we are peer A needs to communicate the output that it is funding. He needs to communicate the change output, and B needs to do the same. So the two funding peers exchange the UTXOs that they're spending, and also the outputs to which to spend the change transaction. Now, the first important conclusion is whenever I do this, one peer is initiating the channel, and the other one is responding. And the responding peer is essentially committing funds to a channel in response of a query. So that's one thing. And then they sign each other's commitment transactions. And the tricky part is they now need to exchange signatures for the funding transaction, right? Both of them need to sign the funding transaction. And what can necessarily happen is that one peer will first have both signatures before the other. So if one peer has both signatures before the other and does not continue the protocol, the other peer necessarily needs to double spend the UTXO that was funding that transaction. So there's a little more work involved. That is not a trivial case to recover from, but there are drafts for dual-funded channels. But there are a couple of edge cases that you need to catch, which are a little more involved than the single-funded case. Okay, this is also very interesting. So, layer 2 protocol contracting needs to work when blocks are full. We've talked about different commitment transactions. We talked about how them being broadcast to the state, but they need to be confirmed. The thing is, though, when we sign or we create these commitment transactions, they are signed with a specific fee. And maybe at the point of a broadcast, the fees no longer are high enough to be either accepted by node policy or to actually float to the top of the mempool. So what happens if I've got this great contracting protocol, but I can't actually deliver to the blockchain? One way to solve it, which has been proposed, is to use child pays for parent. So basically you say, I have a, this is a common thing that Bitcoin Core mempool optimizes for. You have a unconfirmed transaction, which has a low fee rate, and you spend one of the outputs with a child transaction with a higher fee rate. Now both of these transactions are in the mempool, they're both unconfirmed, but because the average fee rate has been increased by this transaction package, the mempool optimizes for that and says, yes, I want to include this in the next block as a high fee rate. This is something that benefits the miner. This is the block template that it creates. So that's the basic idea. This is one way that you could solve the fee adjustment issue with contracting protocols like Lightning. There is, however, a problem with that, with the current replace by fee policy that today is implemented in Bitcoin Core. If I have, let's say, a commitment transaction that works perfectly fine, I've got the two outputs here that you can spend with child pays for parent, and the malicious counterparty decides to spend an output with a very large child transaction that has a high absolute fee, but very low fee rate. So fee rate is satoshis per virtual bytes, and high absolute fee is necessarily high if the transaction is very big. The way replace by fee works is it only replaces by absolute fee. So there's a tension between how child pays for parent optimizes in the mempool, namely by fee rate, and how replace by fee works, namely by absolute satoshis. So this is an attack vector. I can basically pin a perfectly fine commitment transaction to the bottom of the mempool, and it never gets confirmed. There's one scenario that's even worse. It can be the case that the node policy is so low that it is no longer relayed. I have a commitment transaction that has a very, very low fee, and it is not even included in the mempool. It's not relayed because it doesn't fulfill the minimum relay fee. So I could create a child transaction that increases the fee rate of the transaction package. That's possible, like I did in step 1. But that means that transaction 1 needs to be relayed in the mempool to be able to do that. So there are proposals out. This is work in progress. The core guys are working on it. But to have the ability to relay transaction as transaction packages. So you have perhaps a very low fee rate parent transaction, and you have a very high fee rate child transaction, and you want to relay those across the nodes on the network in unison. Yeah. Okay. That's it. That's what I wanted to share today. I'll do a questions in a bit, but I am teaching an online class that I'd like to share with you guys today. It's the same class that I teach in person, but it is focused on the Bitcoin protocol, and we have more time to build projects, and that's something that I wanted to do. The course is built on the Bitcoin. There's the Bitcoin library. It's one that I know very well, and I think the benefit there is it allows the attendees to really learn how to work with the Bitcoin protocol, the fundamental Bitcoin protocol, in more production environments. I have one example I can show from the class. So we were talking about payment channels, and the goal of the class is for the learners to understand how I can actually build a payment channel by scripting these different kind of transactions, and that's what we're doing in this exercise right here. So I'm not going to go through it in detail, but that's one example. Okay, thank you very much.
Thank you for the great talk. So anybody, any questions?
Hi, thanks for the very nice introduction. I have a very basic question about hello?
Yeah, go for it.
Lightning protocol. So when you exchange revocation keys,
yes,
for old commitment transactions,
yeah,
is there? I mean, nothing is atomic on the hardware level, right?
Nope.
What prevents one party from just basically unplugging their network card the moment they receive the other party revocation key?
Well, sorry. In terms of revocation, only one party revokes its state. So when I move from one channel balance to the next, it's always a payment from one node to the other. So one node will benefit, and one node will obviously have a lower share of the balance. And so the node that benefits is the one that shares his half of the revocation key.
First.
Or at all.
Okay.
The other one doesn't need to.
Right.
Right.
Okay.
So it's always the peer that has to gain from the old state that needs to revoke. Yep. Sorry, actually, in that sense, it is atomic. Yeah. Sorry. Yeah.
Hey, for the last problem you described, when the fee in the end is higher than the fee when you create a transaction. Sorry. I guess it's fine. It's just a short thing. Couldn't you just use a transaction accelerator? And just say to one minor direction, hey, I have this issue with this single transaction. Can you just please take this in your next block?
Sure. Yes. At the same time, I would argue the protocol should be robust to reflect the true fee market. If the protocol cannot reflect the true fee market, because the policy fails us to do so, and I have to do it out of because that's also a fee market. That too is a market. Rather, there's a market price for confirmation, and whether that's paid on the chain or indirectly, I would argue the protocol should be able to manage that. And the problem is the protocol prevents the market from working right now because one part optimizes by absolute fee, and the other one optimizes by fee rate, which is what you should be doing. But RBF was introduced in an era where blocks were not full. So if the blocks are not full, then the miners can optimize for absolute fees, right?
First of all, thanks for the talk. I just had a remark on your answer to the first question just now.
Okay.
If the second party doesn't end up giving the revocation key, a later state might occur where this specific state, they're still better off. And if you don't have the revocation key at that point, they could still broadcast that to the blockchain. You couldn't revoke it, so that sounds like a bad idea.
You are right. You are right. You're absolutely right. So the one part, you're absolutely right. So one needs to revoke first, but you're right.
So it has to be
Thank you.
order, right?
Yes.
It has to be, that's forced.
Yes.
The order of exchange is forced. Revocation keys.
Say that again?
The order of exchange of revocation key is forced to be the party which benefits most.
That's correct. It's the order, it's not the revocation. Thank you. My mistake.
Wanted to ask you if you could elaborate or just give us some insight into what the plans are on backing up channel states, because it's probably going to be an increasing, or like as the velocity on the network increases.
I'm not sure if Bob's here already, but Bob's going to talk about like covenants and some really cool new potential opcodes. So today, like for every HTLC, I need a second stage transaction, right? So I need a signature for that, and that's actually very expensive. So for imagine you have multiple HTLCs because you're doing multiple routes, right? For every state and every HTLC, I need my own different signature. And the reason why I need that second stage is because I need to be able to encumber certain output conditions on the spending transaction. So I have a parent transaction, and the parent transaction needs to find a way to say the child transaction that spends me needs to have certain features. It needs to have an output that is revocable. And today we can only do that by signing a second stage transaction. We sign a child transaction together with a parent transaction, so I know the only thing that can spend me is this transaction, and this transaction looks like this. What you can do is with opcodes which aren't in what is it called, check sig from stack. That's actually in Cash, Bitcoin Cash. They've implemented that. But what that does is it allows you to check a signature against any message hash. So I can, for example, say I have a signature for a transaction that's spending the parent transaction, and the signature has the transaction committed to it. So I compare that signature with let's say a pre-image of a certain type, and that pre-image must have an output that is revocable. So that way I can enforce that the spending transaction, even without having signed it, I can enforce that the output script validates that the signature of the output script in fact comes from a transaction that has those features I want. So it's like one generation of transactions imposing features on the next one. So that way you don't need a second stage transaction. That can be done in the output script of the parent transaction. Johnson Lau has a couple pips on that, yeah. that's really, really cool stuff. Okay, thanks for your time. Cheers.
All right, we have the next speaker now, but before that, we are curious. So, who of you is gonna attend tomorrow's workshops? So it's gonna be like, oh, wow, that's quite a lot. All right, thank you. Wish you lots of fun there. We have Adam here now. Adam, he's gonna talk about privacy. Privacy, how the history is, how it's gonna be in the future, and he is actually working on the Wasabi wallet. He's creating that, and he's sort of like living everywhere. Like, I could not get him to tell me where he actually works, but I think he's a word kind of citizen. I hope the technique works in a minute. Okay.
Yeah. Can you get his mic? Sorry. Ja, das zweite funktioniert nicht. Vernünftig.
Right, you get it sorted. Okay, and the question again, please get your bottles to the kitchen. Would be so great after this talk. Thank you. Okay. You see wasabi's on his shirt, so let's see what he's gonna get us. Yeah. All right, we got it.
Can you guys hear me? Like in the back? Yes? No? Not yes? Can you guys hear me now?
Yeah.
Turn it up. This one? All right, so how's my voice? Can you hear me in the back? Okay, awesome. All right. So, you guys are so lucky. You guys are so lucky because I just gave the exact same presentation a couple of days ago in London in the Advancing Bitcoin conference. But it's not going to be the exact same presentation because I didn't have enough time because I had so much things to do. So I had to go through in 2 minutes in the second part of my presentation, which is actually the exciting part. And that's what I'm going to do now. I go through in 1-2 minutes the first part, and then we are getting into the second part. Luckily, you don't have to know the first part in order to see the second part. So what am I? I'm NoPara73 going with the handle NoPara73. I'm one of the creators of Wasabi Wallet. We are working on privacy. Not going into my privacy is important because I don't have time, and I'm going to tell you everything that's happening in privacy in Bitcoin. Every technology we are going to go into. You might heard about some like confidential transactions, CoinJoin, Join Market, Tumblebeat. You might even know what they are, but you cannot really connect them together. And I want to bring this connection in your mind back, so you have a mental model of how things are going. All right, there are the first 3 parts I'm going through very, very quickly. A little bit of history of the early days, then the network parts. How do you keep yourself private on the network part? One part of it is how do you broadcast your transactions. The other part is how do you establish your balance. And then how do you break the links in the blockchain? And that's what we are going to talk about. So early days, in 2010, I have no idea what happened. One thing I want to talk about is, anyone heard about blindbitcoin.com? Blindbitcoin.com was a Bitcoin mixer in 2011, before Bitcoin mixers even existed. And this used Chaumian blinding in order to not be able to de-anonymize its users. It could still steal your funds, but it wasn't able to de-anonymize the users, which was in 2011, which is just amazing, because in 2011 the centralized mixers were born, and still today they are dominating the privacy space, and that's a step back from what we had in 2011, because they can steal your money and de-anonymize you, and who's gonna use centralized services? Those can steal your money and de-anonymize you. The only people who are desperate need in privacy, which is the bad reputation. That's why we have that. Transaction broadcasting. Oh yeah, I will have only one slide. Only one slide. This is the only slide I'm going to in the whole presentation. So, private transaction propagation. How do Bitcoin wallets, let's say, how do Bitcoin wallets propagate your transactions? Most of them just take your transaction and give it to a backend server that propagates it for you. Alright, so this is most Bitcoin wallets, light Bitcoin wallets. Other Bitcoin wallets might propagate it to the network, or full nodes. Many full nodes are also listening to transactions, and they are propagating to the network, but because they are listening, it's harder to say that who is propagating that transaction. Well, we have a good solution for it. Use Tor. That way, with Tor, is an anonymity network. You hide your IP, and basically, and you are doing end-to-end encryption, and with Tor, you can just hide your IP while you are propagating your transaction. It's simple, but Tor was not designed for Bitcoin transaction propagation. What we have better, what was designed, an anonymity network that was designed for Bitcoin transaction propagation, and that's down the line. That's down the line, and I'm very excited to see it happening in Bitcoin. It doesn't have really. It doesn't really have issues like you don't need consensus or soft fork or anything for that. So that's about transaction propagation. The other thing is UTXO retrieval. So your wallet has to establish your balance. The whole thing is the problem of we have to use multiple Bitcoin addresses because otherwise it's just your Bitcoin address is you, so you have no privacy. That's just a pseudonym. That's why Bitcoin is not really pseudonymous, because you are not your Bitcoin address. You have many Bitcoin addresses, and it's not that easy to figure out the names on the network. Alright. What do Bitcoin wallets do today? How do they establish your UTXO set? How can they show that you have this much Bitcoin in your wallet, and then which Bitcoin to spend later? Well, easy. They ask the central server, the wallet provider. they give the central server all your Bitcoin addresses or just an export key, and then from that they tell you how much money you have, which is convenient but bad for privacy because they know everything about you. If you use Tor, that's better because then you at least hide your IP, so at least they cannot do your IP, they cannot connect your IP to your Bitcoin addresses, which is nice. Other ways to do it is the Bloom filtering SPV wallets, which are less and less wallets like this, so I don't even go in. Good ways to do it are, if you are running a Bitcoin full node, if you are doing something like Neutrino, you heard about the Lightning Labs client-side filtering, or Wasabi wallet. It's a kind of a client-side filtering way to get your address, or a full block SPV wallet, which is the only thing I know about is Breeze. So full block Wasabi, Neutrino, Breeze wallet from Stratis, and if you are not doing that, then your privacy is fucked. It's as simple it is. So privacy is like security. It's like, where is the weakest? That's where it breaks. Yeah, it's and from here on, when we fixed the network part, that's when we can go to the blockchain. There are two things: unlinkability and amount hiding. Let's say that's subset sum analysis. Anyway, from where to where, that's the unlinkability part. How much is the subset sum problems? Let's talk about from where to where. What did we do before? There are two kind of ways how you can go about fixing the link from where to where thing is. One is that's using multiple transactions, and the other one is that's using only one transaction. That's called CoinJoin. The problem with using multiple transactions is that the fees go up. It's going to be expensive, more expensive than you would use only one transaction. But multi-transaction mixing is there are a lot of things built on top of that. So what are Bitcoin mixers? It's like Bitcoin mixer is like Coinbase, right? Or Bitcoin exchanges, or Bitcoin casinos, or Bitcoin mixers, traditional Bitcoin mixers. What's very interesting is that how many of you have heard just yesterday the new podcast came out of Stepan Snigirev, Jack, Elizabeth. So Jack is the CEO of Twitter and also has some Cash app, and Stepan asked him that, well, this Cash app is great and everything, but you know, we have something in Bitcoin that people used to say that, oh, if it's not your keys, then it's it's not your Bitcoin. So would you be interested in giving your users control over your keys, over their keys? And he said, yes, he would be interested, but he said a couple of things why it wouldn't be not that good, and one of them was privacy. He couldn't provide privacy for him if the keys would be owned by the users, which was interesting. So yeah, Cash App is a nice Bitcoin mixer too. It's based on confidentiality. So other multi-transaction mixing techniques, I just want to mention Tumblebeat because I worked on it for almost a year, but I'm not going to talk about it much, but rather let's go to CoinJoin. Who heard about CoinJoin before? Okay, everyone. CoinJoin, big transaction, a lot of people come together, gives input to the transactions and to the transaction, and a big transaction will happen somehow, some magical way. What does it solve? It solves the issue with centralized mixers is that no one can steal your coin, because if you don't see your output in the big CoinJoin transaction, then you just don't sign. the very first used implementation of CoinJoin was SharedCoin from Blockchain Info. But they since discontinued the service. I wasn't really able to attain too much information about its effectiveness, and does it really matter, because Blockchain Info knows all your addresses and all your mixes or whatever. So other research came out of CoinJoin. It was CoinShuffle. CoinShuffle was really interesting. It created a CoinJoin implementation in a semi-decentralized way. It was relying on Tor, anonymity network still, but it only needed a bullet point server, so the peers were just publishing their messages to a server, and somehow a nice CoinJoin were evolving. It was just it was just a research paper, right, at that point. But this was very promising, and we will see later. So two implementations, CashShuffle and ShufflePuff from Mycelium. CashShuffle is a Bitcoin Cash implementation, which was interesting because it's CoinJoin, and people told me who reviewed the code that in CoinJoin they were able to still risk your coins somehow, which was quite something that you wouldn't expect from a CoinJoin scheme. Other CoinJoin implementation was very famous. I don't consider it very important, but you might heard about Amir Taqi's and Cody Bilson's dark wallet. It was a 2 of 2 CoinJoin stuff. I wanted to mention that too. There are interesting schemes on CoinJoins, like CoinJoin cuts through, CoinJoin XT, you are unrolling the light to the Lightning Network with CoinJoins. Those are nice, but those are down the line, right? First, let's just build CoinJoins. So how do we build CoinJoins? One way to do this is with Chaumian blinding, and that's what Wasabi Wallet is using. And if you might notice that CoinShuffle is better than Chaumian blinding CoinJoin, like Chaumian CoinJoin, because it's more decentralized. But Chaumian CoinJoin uses a coordinator, a server, that with that coordinator the peers are, with some signature blinding magic, the peers are negotiating the transactions, and then the coordinator gives the transactions out for signing, and then the peers are signing, and the CoinJoin happens, but the coordinator is more active in this scheme than in the CoinShuffle scheme, which is very important from a decentralization versus centralization point of view. In one way, CoinShuffle is a bit more resilient because the server there is just a bulletin board for message publishing. In the other way, if something breaks, then we can just update the server and then we fix it. But if something breaks in a decentralized system, then and good luck fixing that. But that should be still the direction we are going, and that's why I'm going to talk more about CoinShuffle this talk than Chaumian CoinJoin. CoinShuffle Plus Plus. CoinShuffle Plus Plus is not just a little bit better CoinShuffle. CoinShuffle Plus Plus removes the Tor dependency from CoinShuffle. You still need for hiding IPs, but never mind. Removes the Tor dependency, and and it's using some very old mixing technique, Dining cryptographer networks. This was actually in the first part. I'm not going to talk about. Yeah. And they created DiceMix, which is a mixing network for mixing bitcoins. And that removes the Tor dependency, except that it doesn't remove because you still need to hide your IP, but you are not that dependent on that anymore. So this is CoinShuffle++. This is how far we can get with breaking the links. So, as you may have noticed, this is the end all Bitcoin game. As you may have noticed, we couldn't quite came up with a completely decentralized system. It's still somewhat centralized. It still needs a server, but kind of good enough. Anyway, this is where we can go with Bitcoin, with breaking the links, and now hiding the amounts. Let's try to hide the amounts. So every system I was talking about previously was about how do you mix bitcoins. The subset sum issue is that if I send you some bitcoin and you send him some bitcoin, then based on the amount you can figure out that which sub-transactions there are of the full transaction, which is terrible. So what does all these schemes do, like Wasabi's Show Me and CoinJoin and CoinShuffle? They are simply saying that, okay, we have 0.1 Bitcoin, that's our base denomination, that's how much we can mix in every round. So I have 10 Bitcoin, 0.1 Bitcoin is the base denomination, I need to do 100 rounds. We later improved a little bit on this in Wasabi, but let's see what we can do with it. Sharecoin was using unequal amounts, blockchain info's Sharecoin, which was, well, I'm not quite sure how good that was. I think they weren't doing too much good with that. Well, anyway, Christoph Atlas's CoinJoin Sudoku has shown that it's completely defeatable with the subset sum analysis. So that didn't go that further. What else? Chipmixer. Chipmixer was one of the only traditional Bitcoin mixer, because subset sum also applies to traditional Bitcoin mixers, not only CoinJoins. It just you cannot see it in the block explorer, you cannot see the transactions, but you can still identify the transactions there. So Chipmixer was doing that. All right, you give me chips 0.1, 0.2, 0.4, and then we are mixing that. Other traditional Bitcoin mixers are just how would you say, playing on your naivety that you send them arbitrary amount of bitcoins and they give you arbitrary amount of bitcoins, and well, no one's gonna notice it, because to be fair, blockchain analysis just doesn't care about any mixing yet, because they have such a low-hanging fruits right now. 70% of all the darknet users are sending money to Bitcoin exchanges directly, no mixing. So this is what blockchain analysis cares right now. So even though traditional Bitcoin mixers are easily subset sum analyzable, doesn't really matter, because they don't do the work. Blockchain analysis just doesn't do the work, so they can get away with it. Except Chipmixer. Actually, I don't know if Chipmixer is legit, but that's the only thing I've seen that was actually trying to address the subset sum issue and traditional Bitcoin mixers. Join Market was very interesting. Came up with a very interesting thing how to address this subset sum issue. Join Market says, I have market makers with the yield generator. They are just standing like you guys are all market makers, and you are standing and waiting for people who want to send coin joins like me, and I just pick 1, 2, 3, 4, and I'm going to mix with you guys. And you give me the bitcoins to mix with, and I pay all of you some fee, and I pay all the transaction fee. And I am a joint market taker. You are running the joint market yield generator. So this is great because you can have instant private transactions. Subset sum is solved. Why I'm not going in this way with Wasabi is because the fees go up. If the Bitcoin transaction fees $0.1 and I have to pay 5 transaction fee, instead of I have to pay for 5 people's transaction fee, that's fine, that's 0.5, right? But if the Bitcoin transaction fee is $1 and I have to pay 5, then that's $5. And when the fees started to go up, that's what we noticed, the joint market usage went down. In fact, if you want to mix with a lot of people, you have to select a lot of peers, and what's gonna happen then? You are paying 50 transaction fees as a taker. So it might not be scalable in the future when we will have high transaction fees.
Okay, excuse me.
Almost ready.
Sort of come to the answer. We have to also have one more question because we have sort of almost what left, which is this side.
Almost ready. Give me 1 minute. All right. There are unequal mixing input things, but I wanted to talk about Schnorr signatures and confidential transactions. You heard about Schnorr signatures. You are taking a bunch of inputs and you just use one. You are combining the signatures into one, which makes smaller transactions, which is great for CoinJoin. That's one concept. Confidential transactions blinds the amount. So the amount of the outputs are basically blinded. So we don't have to mess with all these amount stuff, but we can just send to each other in CoinJoins. We can just send to each other money in a way that we don't have to mess around with the 0.1 Bitcoin and joint market schemes. And bullet proofs makes confidential transactions scalable, and in CoinJoins it scales linearly. So you can get to a point where so many people come together that a CoinJoin with bulletproofs, confidential transactions, and Schnorr, a mix with one person, became cheaper than a normal Bitcoin transactions because you are aggregating the proofs and you are aggregating the signatures. And this can be cheaper than a normal Bitcoin transaction. And this is completely private. And this is where we can get with Bitcoin. If when confidential transactions gets into Bitcoin, which is a huge question, but very, very, very exciting. Thank you.
We maybe have time for 1 or 2 questions. Otherwise, please talk to him in the break.
How many people would need to do a CoinJoin for it to become cheaper?
I don't know, maybe 100. That should be fine. Yeah, it's like 1% of the whole stuff. Yeah, 100, I would say. I didn't do the math myself, but if you are aggregating stuff, then it's gonna become insignificant with a lot of people.
Okay.
Hi, thank you for the presentation. So when hiding the amount of bitcoins in the transactions. You mentioned several methods, but you didn't mention Mimblewimble. What do you think about that?
So, what may confuses you that the Mimblewimble implementations, Green and Beam, are using confidential transactions, and that's what they are hiding. That's how they are hiding the amounts. So they are using confidential transactions. It's not Mimblewimble itself.
Okay.
All right. Thank you, Adam, for this talk. And we're going to have a shorter break now for 10 minutes. Okay, see you in 10 minutes for our next session.
They say you don't really should be okay without
We're gonna start in a minute again. Please take your seat. Das Problem ist, momentan kann man nur die Hände, die überlegen, das ist sozusagen theoretisch gesichert. Aber es gibt auch keine Funktion, um sich sozusagen einzuloggen. Das ist das Problem. Aber es ist schon zumindest mal wahr.
Ja, gut, das Problem ist immer dann.
Everybody back. We're going to start our next talk with Bob. Is Bob here around somewhere? There he is. Okay. Last one, please come here. Okay, Bob, he's from the US actually. He just stopped over in Germany on his way back. He's doing Bitcoin things since quite a few years. He works with blockchain, with Bitcoin, and is really expert in this field. He's going to give us a talk on on-chain defense in depth. And we're really looking forward to that and a ton of discussion after that. Thank you.
All right, so I'm Bob. I work at Fidelity Digital Assets. For those of you that don't know Fidelity, Fidelity is one of the largest asset managers in finance. Fidelity has more than $7 trillion assets under management, and we have started a new business called Fidelity Digital Assets to custody Bitcoin and hopefully other assets in the future for institutional customers. So first, a disclaimer from our lawyers. This presentation is intended to be educational in nature. It's not representative of existing products and services from Fidelity Investments or Fidelity Digital Assets. With that out of the way, this talk is really about the worst case scenario, okay? What happens if the absolute worst happens and your private keys are stolen? What can you do? This is basically defense in depth, which is also sometimes called the castle approach, right? So when you build a castle, right, you build big walls, and then you build a moat, and then you put archers on top of the walls, and then you put catapults in the middle that throw flaming hot balls of mess at the people attacking. None of these things by themselves is your protection, right? You have all of them in depth, right? So if one of them fails, you still have other protections. And when you secure assets, you want to use every tool you have available to you to secure those assets. So we want to use multiple layers to protect funds in general. Anybody who's running any kind of service should be doing this. Any exchange, any custodian, anything like this. The failure of any one layer is backed up by security in other layers. And so for the remainder of this talk, I'm going to be talking about what can be done on-chain. And this in general requires changes to Bitcoin, which is the motivation for giving talks like this, is because I want to encourage everybody to think about these tools. These ideas have been around for a while. Nobody's really using them, but we could be. We would like to be. And so if the community thinks that these are good ideas, so let's figure out how to get them into Bitcoin. All right, so the worst case scenario. Your private keys are stolen or exfiltrated, right? Somebody broke in, they stole your hardware security modules. The previous talk we saw the laser etching from the surface of the chip, extracted keys. Maybe they got your backups out of wherever you're storing them. When this happens, the thief has no restrictions on what he can do. He has the private keys. He can write any type of transaction he likes. And generally, today, when that happens, the funds are just gone. There's nothing you can really do. The thief can put these keys into other software, so that doesn't have to use the software that the service provider has. Can use whatever software he likes and write any transaction he wants. The keys that are stolen could be hot or cold or something else. I'm not going to go into wallet structure here. This is a general, what I'm going to discuss for the rest of this talk, covenants and vaults, could be applied at many different layers, whether it's hot, whether it's cold, or something else. So I'm not going to go into exact wallet structure here. This is a general tool that could be applied. So examples, hacker infiltrates your system, is able to bypass controls on a hot system and obtain the keys from a hot system. Cold storage, keys get stolen from hardware security module type devices. We had a great talk about hardware security modules, or via side channel attacks on those devices, or theft of the devices, or physical attacks. Keys are stolen from physical backups, or an insider attack by collusion among operators to get access to the keys. So the general idea is the following. So what we want to do is we want to create a vault. And a vault is a two-stage transaction. Okay, it's two transactions in sequence. The first vault is where you send to a vaulted address using the new Vetch32 addresses, BC1 vault. So Alice is a customer of some service provider, is going to send funds to this vault address when she deposits, right? Now, in order to spend those funds, we want to have a second transaction where we have to use a transaction here from the vault to unlock those funds. Now, this unlock is time locked, so there's a time delay between the vaulting and the unlocked. And we can't spend these funds further, and let's say Bob wants to withdraw those funds, we can't spend those funds to Bob until the time delay has expired. Now, during this time, during this unlock time, the owner of these funds has another possibility to send the funds to another address that evades the time lock, okay? And this is this clawback spend here. So rather than unlocking the funds and then sending them to Bob, I've detected something is going on, somebody's trying to steal my funds, and I'm going to send them back to a new vault, perhaps a backup vault, evading anybody who might have the keys here from stealing the funds. The way this generally works is, first of all, you have to have an if-else statement. The unlocked address looks something like this, where I just have an if-else. There's a time lock here. This is a relative time lock using check sequence verify. This would be 72 blocks long, which is 12 hours. And if this hits the blockchain, then this can be spent after 12 hours by using this particular set of keys. Now there's an alternative condition that evades the time lock, right? That if I use these two keys, which are different from these keys, because my assumption is that these ones got stolen, right? There's a different set of keys that I will pull out to save these funds from the thief. We've had a couple talks in this conference about Lightning Network. For those familiar with Lightning Network transactions, this is backwards from the way the time locks in Lightning work. The time lock in Lightning is used in the abnormal case, right? This is the adversarial close of a Lightning channel. Here, we're using the time lock in the normal case, not the emergency case. The challenge of this is that the vault mechanism is to enforce that the vaulted address can only spend to the unlocked address that we control. That's why it's a two-stage transaction. We have to encumber one address to only be able to spend to a second address. And if we could do that, immediate theft can be prevented. Making a script like this is straightforward. You can do this today on Bitcoin. Enforcing that this address has to spend to another address is what we cannot do today. And so the rest of this talk will be about how to do that. How do we achieve this enforcing that the vault has to go to the unlocked and not somewhere else? Because if a thief could just get to the vault directly and steal the funds directly from the vault, this wouldn't do us any good. So some features of this mechanism. When I send this transaction, which unlocks the vault, this starts a clock. Now, we're using the blockchain as a clock here, right? That's why it requires two transactions. The first transaction starts a clock, and then I have to wait out the 12 hours, and then I can send the second transaction. The blockchain will reject the second transaction before 12 hours. So we're using the blockchain as a clock and as enforcement of that clock. The second transaction here I'm calling a clawback, just nomenclature. Now, during all of this, you have the opportunity to watch the blockchain for your own address. If you're a service provider, an exchange, or a custodian, and you see one of your own addresses being spent in a way that you didn't create or you don't expect, I can always see this, right? I can run many nodes. Those many nodes can monitor the blockchain and look for this happening, right? That's the assumption here, is there's another node that's looking for this to happen. And when this happens, I have a certain amount of time to pull out the emergency keys and claw back the transaction. These clawback keys are kind of more sensitive than your cold keys, right? If this was stolen from cold, these are the keys to the kingdom, right? So now the clawback keys can evade everything and can steal the funds directly. But they're rarely used. They're not used in the course of normal operation. They're only used in case of emergencies, and therefore should be harder to get, or I want to engineer them to be harder to get than the ones that got stolen, the hot or cold keys. Other point about this is you need a place to send the funds after I save them. When the thief is in the middle of stealing them, I need to claw them back to somewhere. I don't want to send them back to the place they came from because the assumption is that those keys were stolen. So I need another wallet, a backup emergency wallet, to send those funds to. So I have to prepare a backup cold storage ahead of time. So for the rest of this talk, I'm going to dive into some technical details about how to do this. But before I do that, why don't I stop and ask for questions on the general mechanism? Yeah?
So assumption is always that clawback private key is not stolen.
Correct.
Okay.
You could do this in multiple layers, and this is a general tool.
Okay.
For those on YouTube, the question was, the assumption is that the clawback keys are never stolen, and that's correct. But they're also never used, so they're harder to steal, or should be. Yeah?
Just your role as Fidelity, are you planning to hold the clawback keys, or is it still a solution that's going to be for the customer only, and it's basically a service that you offer who's helping them?
So not saying how, I mean, so we can't use this today. We are not using this today. If we did use it, so the structure of the service that Fidelity is offering is a fully custodial omnibus wallet. So the customer does not have any keys at all. What we find generally when we talk to customers hire a service provider like us because they don't want to deal with key management. And so we provide that service for them. There are other customers who do want to deal with key management, and there are other custodians which provide that.
Would you then also, are you legally bound to pay back a certain amount, for example, when the keys or the funds are lost, like a normal bank insurance?
This is not a talk about law.
I know, but it does.
I will say about our the solution we have is that it is insured. We do have insurance on the custody we have. All right, so let's get dirty. All right, so there are 4 mechanisms that I know of to do this. Thank you for the previous talk that kind of advertised some of these. So the first, this idea is rather old, but the first to really explain it in some detail was this paper by some folks at Cornell, and they introduced an opcode called check output verify. The second way I know of is the one that I came up with a couple months after I saw this paper. I came up with a way to do it using pre-signed transactions, where you delete a key. I'll talk mostly about this one because, well, I came up with it and I think it's interesting, but maybe it's not the best idea. Johnson Lau, quite some time ago, created a BIP with a new opcode called push TX data that can do this. Finally, there's the opchecksig from Stack, previously mentioned, which can also do it. This one is implemented in Bitcoin Cash as well as in the Elements/Liquid networks. So the first one historically was this check output verify. So this is the code for check output verify. Basically, it's kind of like a regular expression. So what you do is you create a pattern on the transaction where you look at, okay, there's a opcode here, and there's a pub key here, and there's another opcode, stuff like that. And you create this pattern, and then you compare it to the spending future transaction. So you can do almost anything with this. It seems to me, I'm not going to go into very much detail about this particular solution. It seems to me this is quite complicated with potential unintended consequences. Applying a regular expression on a transaction script could do a lot of things. Maybe not the ones you want. And I think in all of these solutions, the onus is on us. The onus is on us to prove that there is an absence of unintended consequences. So the second mechanism here is the one that I came up with using pre-signed transactions. So basically, the way it works is like this. So when Alice deposits her funds, she asks for a deposit address, right? So instead of giving her an address from my wallet, I will generate a new private key, right? I will create and pre-sign a transaction that sends from the vault to the unlocked. And then I delete this key. Now, as long as I've actually deleted that key, that pre-signed transaction is the only thing that can happen, right? So I've created the enforcement by existence of this pre-signed transaction. And after I do this, I'll give this vault address to Alice, and then she will send funds there. This pre-signed transaction depends upon the input transaction ID, so we have to wait for Alice to broadcast her deposit before signing. This is a bit of trouble, so we can't actually delete this key for some time. We have to wait to see what the transaction ID is, which gives a new attack, right? If someone can get in the middle of this deposit process, this could evade the vault mechanism entirely, which is not what we want. Another way to do this is to create what I call a P2TST, which stands for pay to time lock signed transaction. That's what P2TSD stands for. I create this transaction sending from vault to unlocked. Instead of generating a key, I'm going to generate a signature using a random number generator. And through the magic of ECDSA key recovery, I can compute the pub key from the signature and the transaction hash. Now this requires some funny things, which I'll go into some more detail in the next slides. This requires sighash no input, and also this flag sighash script mask, which has been proposed, and the ability to do pub key recovery. Because the sig hash depends on the input transaction ID, which in turn depends upon the previous transaction's output address, which in turn depends upon the pub key, we have a circular dependency on that pub key. So I can't actually calculate the pub key, because the thing I needed to calculate the pub key depends upon the pub key. And the only way I could actually do that is if I broke the hash function. So this is a problem, and this is why we need sig hash no input, which breaks that dependency on that input pub key and allows me to actually compute the address. So just a quick lesson on what a sig hash is. Sig hash is the hash of the transaction data that is used to sign, right? So this is the sig hash that's used in segregated witness. It's got 10 fields. Basically, you just take a bunch of data from the transaction, its previous inputs, its outputs, its values. I concatenate all that data, and I hash it. That hash is the message used in the signing algorithm. The sig hash is an extra flag that tells how I computed this, and there are different ways I could have computed this. I can say that this hash is over all inputs and outputs of this transaction, none of the inputs and outputs, single, meaning just one input, one output. And hopefully someday we'll get no input as well, which zeros a couple of these elements and decouples the link to the input. So part of the reason to start talking about this is we expect there to be a soft fork coming soon. And one of the things we expect to be in it will be the Schnorr signature algorithm. Schnorr's signature algorithm has a lot of advantages compared to ECDSA. It's older. It didn't get used by Satoshi when he created Bitcoin because Schnorr was initially patented. It's older, it's simpler, and it supports aggregation. So two signatures can be added together, and they validate with the sum of the two pub keys. This is not true for ECDSA. It is true for Schnorr, which provides a number of speedups and privacy enhancements that can be created with Schnorr signatures. So Peter Wille has created a Schnorr BIP, which describes how he wants the signature algorithm to work. The Schnorr BIP has a signature function that looks like this. In other words, if this equation is satisfied, the signature validates. And the two elements of the signature are actually the pair R and S, which are here. And the rest of this is a hash over R, pub key, the message, which is the sig hash, and the pub key. You could consider an alternative signing algorithm, which does not hash on the pub key. What we wanted out of this was to be able to recover the pub key, which you can do straightforwardly with ECDSA. With Schnorr signatures, if I use this algorithm, I could compute the pub key, right? So just rearrange this equation a little bit to solve for the pub key, and I can actually compute the pub key using this version of Schnorr. The reason Peter didn't put this version of signing and use this one instead was that because with this signing algorithm, any third party can convert a signature into another valid signature for the same message. So in other words, I can take R and S, I can shift S by a constant times this hash, and this is still a valid signature for this pub key P plus AG. Now, whether this is okay in this context reduces to the question, are there transactions with exactly the same sig hash? And in general, yes. The client, so we're running a service here where people are going to send funds in. And we give the customer an address. And what happens after that is up to the customer and what their process is for wherever those funds came from. There are a couple of common practices in finance that cause problems here. One is that customers often will do what's called a penny test, where they send a small amount of funds first, just to make sure their entire operation is working correctly and that the funds are received. The second thing that they will do is if they're depositing a large amount of funds, they will generally divide this into tranches, so that it reduces the risk on any one transfer. And so if one is lost, okay, that sucks, but we didn't lose everything. So for instance, if they're transferring 1,000 Bitcoins, they may transfer it in 100 Bitcoin tranches. Because the sizes are the same here, this results in exactly the same sig hash and same transactions. And this is a circumstance in which these transaction signatures could be replayed. So the goal here is to figure out how to be able to calculate this pub key and not have this kind of circular dependency on the pub key. So a half-baked idea I had a couple days ago, which maybe somebody in the room will figure out what's wrong with it in the course of this talk, is to break this circular dependency by having a transaction ID which does not depend upon the outputs. So your standard transaction ID is the following. It's the hash over basically the inputs, the outputs, version, and lock time. The outputs are actually kind of committed to twice here because they're also committed to in the signature, right? So a signature on a transaction connects the inputs to the outputs with the policy that the owner of those funds wants. But we also committed to them in the transaction ID, right? And it's the fact that the outputs are here that causes it to be tied to the pub key, which causes this circular dependency. Segregated witness also has another transaction ID which is used internally in the Merkle tree in the witness block that also has the inputs and outputs there. So this transaction outputs are the script pub key, and the script pub key contains the pub key hash in general. So this is where the circular dependency comes from. So instead, I'm just throwing out an idea here. I don't know if this makes sense. But let's define an input-only transaction ID, which does not contain the outputs. This is still enough to be able to look up any input. The fact that the outputs are not there doesn't really change anything. Each input is still unique up to the hash collision resistance of the hash function. So I can still put the inputs in any transaction. So again, the outputs are committed to anyway in sig hashes and signatures, if that is desired by the spender modulo using sig hash no input. This would allow us to use pub key recovery and random number generated signatures with no known private key. And that's what I'm really looking for here, is a circumstance where nobody knows the private key. And particularly the attacker can't find the private key because nobody knows it. This would imply a new modified transaction ID index and sig hash input transaction ID flag. This seems to not be useful for Lightning sig hash no input usage, where they need the ability to change the inputs. So let me check real quick. Sig hash no input has been proposed by the Lightning Network folks. It was in the original Lightning paper. And the purpose of it is that you want to be able to change the inputs being used for a Lightning channel. This allows you to rearrange your inputs and rearrange the amount of funding in a channel. The problem with it is that because of this signature replay problem, you don't want other people to be able to do this to you and other people to be able to spend your transactions. The general advice is that don't use sig hash no input for any kind of wallet. And the reason is all of these signature replay problems. In the context of the Lightning protocol, there's a specific protocol that's followed, right? And I expect the transactions sent to me by my counterparty on the Lightning Network to have a certain structure. And because of that protocol, you can get away with using sig hash no input. But in any other context, the advice is don't use sig hash no input for wallets. And this is a wallet. If we had this input transaction ID, it would evade this problem of the Schnorr signature replay, since this sig hash is now different for each input. All right, so let's a couple words about this pre-signed mechanism in general. These pre-signed transactions are kind of a nice object for risk management. They're not funds in themselves. Somebody who stole this pre-signed transaction doesn't actually have access to any funds. They also need to steal the private key that goes with it. And even if they did that, the owner of those funds still has a backout. These kind of pre-signed transactions could be aggregated into collections of known denomination and divided up and put in certain places like gold bars. I could put some on some database server, I could back some others up, put some online, some offline, etc. These are less risky than keys and less expensive to create than key ceremonies. For an institutional operation, creating the keys for the operation is a rather expensive process. It's audited, it has a lot of secure hardware, various things like this. These pre-signed transactions cannot directly steal funds. They can be redundantly backed up, whereas you generally don't want to redundantly back up your private keys, because that provides multiple opportunities for them to be stolen. But there's some pretty significant downsides to this idea. If you had a responsible hard fork that implemented replay protection, you would not be able to claim the funds on the fork, because the fork would have different address format, different sig hash in general, and this pre-signed transaction you created would not be valid on the fork. Some of the hard forks we had in the last year, Bitcoin Cash, did not implement replay protection, which is frankly rather irresponsible on the part of those devs. You could do replay, but I don't really want to encourage people to do that. Please, if you make a fork, please implement replay protection. Something I've discovered is that deleting keys is generally not done. People, you never know, and there are lots of people who don't want to delete keys in general. If you have to delete keys, how do you really know that you deleted a key? How do you know there wasn't a side channel attack going on at the time and they were recorded somewhere else that you didn't see? Various kinds of hardware and software attacks could evade this vault mechanism. And again, coming back to sig hash no input, this is unsafe if there is any kind of address reuse. So don't do this for wallets. I think I've said all this. All right. So the third idea that's been put out there is this one by Johnston Lau. And this is op push TX data. This is an opcode which basically lets you put any transaction data onto the stack and then do computation with it. This is generally, so this BIP is kind of old. It hasn't really gone anywhere. This approach is generally not the one favored by most Bitcoin developers. There's kind of a difference in philosophy between, let's say, Bitcoin and Ethereum. In Bitcoin, you want to prove that the spend is authorized, right? Not actually perform a computation. Ethereum takes the opposite approach and says we're going to do all computation on chain, resulting in a 2 terabyte blockchain today, which is generally not the approach that is favored by the Bitcoin devs. This also has the problem of unintended consequences, right? There are a lot of different things you could do with this other than vaults. And the question is, well, what else could you do with it? And can I prove that nothing bad could happen from having this thing that is essentially a Swiss Army knife of data that I can now do computation with about the transaction? Finally, there is op-check sig from stack. This one is very, very simple. It just checks a signature. That's it. But there's this funny trick you can do, which was pointed out by Russell O'Connor and Marta Pikarska. Basically what you do is you perform a signature check twice. So the first signature, you put the transaction data on the stack. So this is your sig hash. You put it on the stack. You verify the signature. And then you verify the signature of the transaction using the exact same signature. So we do some stack manipulation here basically to duplicate the signature and put everything in the right order. And then we'll do 2 check sigs. The first checks the signature of this transaction using the sig hash of this transaction. And the second one checks the signature that's on the stack. And what this does is it proves to you that this transaction has exactly the same sig hash as whatever's on the stack. So this sig hash then essentially encodes everything in the transaction. So I've now made an enforcement that this transaction matches what I expected it to. Of the 4, this one is probably my favorite. It is the simplest. And this mechanism has been implemented both in Bitcoin Cash as well as the Liquid network and in the Elements Alpha network. So there's some consensus out there that this one is not as bad or has fewer unintended consequences than perhaps some of the other ones. In general, recursive covenants are possible. You can have a check sig from stack which enforces that the next transaction also has a check sig from stack. And you can do that with all 3 of the types of opcodes I listed. This is kind of a funny idea. So the original covenants paper pointed out that this could be used to create, for instance, colored coins, where you want to create coins that are now non-fungible with other Bitcoins because they're now some kind of asset or something like that. Do we want that? All of the opcode forums can do that. Do we want that? Another kind of drawback to this is that it's fairly obvious to everyone that you're making a vault. It has low privacy. You've got the if-else condition there, and everybody can see that you're doing it. So it would be really cool if there was a way to hide the fact that you're doing this. This alternative spending condition is never executed in the course of normal operation. You only want to pull it out if there's an emergency. So there's another proposal called Taproot. I'll skip that for a second. So what Taproot does is it works by tweaking your public key. So what you do is you take your public key that you normally would have used, and I'm going to shift it by some constant m, where this m is a Merkle root of a Merkle abstract syntax tree of alternatives. Now, a masked Merkle abstract syntax tree is where you take your script. And your script here is just a series of if-else statements, right? And a series of if-else statements can be organized into a tree. Each branch of the if-else is a tree. And when I'm spending it, I have to say which branch of the if-else I'm spending and reveal the corresponding script. So that's what this does. You have this tree, you reveal which branch of the tree you're spending and the corresponding script. So in a way, this is just kind of a different way of revealing the script sig than is normally done. But the interesting thing about this is that this, after you do this shift, is just another pub key. Nobody can tell that you did this by looking at your transactions. Nobody can tell that there exists an alternative spending condition within the transaction. But you can't claim afterwards that there was one, because that would require you to, that would break the discrete log security of ECDSA or Schnorr. Because this uses masked, so masked, you could have many branches of this if-else condition. I could have more than one backout under different conditions or under different sets of keys. The only one that anybody sees is the branch I actually execute. So there could be other alternatives in there. I could have as many alternatives in this tree as I want. And the only one that gets revealed is the one that I actually spend. And maybe after I do that, I want to change my policies, because I'm now revealed to everyone. Whereas if I did not have this Taproot capability, everyone would be able to see in every single one of my transactions what the backout is. And while they may not know where the keys is, it's still useful to know that there exists a 3 of 3 spending condition that evades the time lock, for instance. And then the attacker says, oh, well, there's a 3 of 3 spending condition. Now I know I have to steal 3 keys, and he can go try and figure out where they are. So this Taproot mechanism is really, really good for optimistic protocols, where there's something you do almost all of the time, and there's something you do very, very rarely. And that's exactly what's going on here. Your clawback is the very, very rare case. Transactions are indistinguishable from a single key pay-to-pub key hash. You can also do multi-sig within Schnorr. So this is one of the reasons people like Schnorr, is because you can actually reduce multi-sig to a single sig and put all of the multi-sig within Schnorr signature aggregation instead, which is a pretty cool trick. There's a paper called MuSig. Please read it about how to do N of N aggregation with Schnorr. And there's also an interactive threshold scheme that can be used. For a vault, what you'd end up with is that all of your scripts would end up looking like this. You'd have a time lock and just your one key and then a check sig. Almost done. So one last consequence of this is that you generally have to have some form of fee wallet. It's a similar problem to Lightning. You don't know what the fee market is going to look like between the time you create the transaction and the time you actually spend it. So you need a mechanism to basically bump the fee. If the fees have risen between the time you created this vault and the time you want to spend it, or your Lightning channel and the time you want to spend it, you need to be able to add fees to the channel. It's not really a problem, just something to think about. If you sign your transactions in the right way using sig hash single, you can aggregate the transactions, and then your fee wallet can pay an extra fee, where the fee wallet just has a small amount of funds just for paying fees and does not have any of the main hot or cold keys. This is a good policy anyway for service providers to ensure timely withdrawal. The customers expect withdrawals to happen within a given time frame. You can help ensure that by dynamically updating fees. You can use sig hash single to sign the outputs, and then the fee wallet uses sig hash all and may use replace by fee to bump fees. All right, so that's it. So vaults are a powerful tool that people have been talking about for a long time, and most of the Bitcoin devs I've talked to think it's a good idea, but it's never really gotten far to be actually usable. And if we all agree it is a good idea, let's take the next steps and actually get it done. I personally really like the pre-signed transactions, but they have undesirable qualities. Whether you deleted the keys, you don't want to use sig hash no input, but they have nice properties from a risk management perspective. And I think we need a new idea here. Maybe it's this input transaction ID, maybe it's something else. But the really powerful idea here is to be able to create your signature with a random number generator and somehow calculate the pub key and have that be the mechanism by which you enforce the covenant. And this doesn't require any new opcodes. Of the new opcode class, of the 3 opcodes, I'm personally most in favor of checksig from stack. There is precedent for this because it is deployed on 3 other blockchains at least. I'm not aware of any issues. It's worth thinking about what other things we can do with this. I think there are interesting ways to combine this with Lightning, for instance. It'd be worth thinking about that a bit more. This one is definitely simpler than the other 2 opcodes, which have kind of more like a Swiss Army knife type of characteristic to them. You can do almost anything. All of these mechanisms enable recursive covenants, which essentially can remove funds from essentially being fungible with Bitcoin. One consequence of this is there are other disabled opcodes, in particular opcat, which would also have to be enabled in order to do this, or perhaps there's a different way to just organize that script. Opcat has been enabled in Liquid Elements Alpha, but something to think about if we want to enable it on mainnet. One other sideways consequence of all this, composition, or otherwise known as batching, in all cases is difficult because I am enforcing that one input and one output have a relationship. If I have batching and I have many inputs and many outputs, I don't know which input corresponds to which output. Now I can use sig hash single that says, input number 1 and output number 1. That's where the covenant is enforced, but I've now completely broken my privacy, and aggregation doesn't really buy me that much. I'm only really buying a few bytes in the header, and not really able to do batching nearly as well. All right, that's it.
Thank you, Bob, and thanks for that. You guys have any questions on that?
About problems with checksig from tech, I don't probably, as I understand what is said on the Elements website, they construct the transaction on stack and then verify it. So there's a script size limitation, what is also limiting this. So yes. you cannot make a big transaction.
Correct.
Yeah. So it's and the actual question is. So do you think this?
Well, not necessarily, because the only thing I need on that stack is the hash of that transaction data.
Really?
You don't actually have to put all the transaction data on the stack.
Yeah, because yeah, maybe I should read it because as I understood this, what you actually construct the transaction.
You could do it either way. If I have to put all the transaction data on the stack, yes, then I have a script size limit.
Because we mentioned what over here we might hit this limitation. So yeah, the actual question is so this batching of the while transaction, is it really practical? Because it's while, like probably not. Do you think it's practical?
Do I think batching is practical?
Yeah, do you think it's have a really like real life need for this?
The need from a security perspective and saving your funds is definitely there. From a batching perspective, you can't do batching, right? You have a set of one input, one output transactions, right? And so there are ways I could aggregate those using sig hash single, but again, I'm only buying myself a couple of bytes in the header, really.
Like, there's no need to seek for the method to do a batching because there's no practical need to do batching.
You want to do batching to decrease the on-chain load. I mean, we're doubling the number of transactions here, right?
These are high value. I mean, these are high value transactions, so maybe.
Presumably, yeah. Presumably, you want to reserve this kind of mechanism for very high value transactions, yeah.
Anybody else?
Yes, a small question about the no input transaction. So, do you mean replacing the no output transaction with all, or just have it implemented next to it? So, for example, if you want to push data onto the blockchain through the up return, does it conflict with it, or is it a separate part?
No, I don't think up return is related in any way. There's no up returns used here.
Okay, so then I probably don't know what you meant with the transaction output, getting rid of it.
So with the input transaction ID, right? So the normal transaction ID is computed by hashing all the inputs and all of the outputs of a transaction. And what I'm trying to do here is do something different with what the output is, right? So that's what that is. So sig hash no input is different from this proposal of input transaction IDs. In one case, you're saying I'm allowed to change the inputs. In the second case, I'm saying I'm not committing to the outputs. They're related, but different.
Okay, anybody else? Questions? What?
Just a short remark. I just wanted to say that you as an institutional investor, I'm happy to see that you put all the effort into Bitcoin and not into some arbitrary altcoin token or into Ripple. And I say, welcome to Bitcoin.
So I don't see anybody else. Question?
Just a quick question. Have you thought about as an alternative to using this wall technology, just having in-flight transactions that are time locked, they're staggered?
Yes.
Is that something that you're thinking about? Yeah.
Yes, and we prototyped it too, but still have to delete keys. Right. So all the negatives are still there.
How big is your team actually?
We have about 150 people within Fidelity Digital Assets, mostly in Boston. I also work half of my time in the blockchain incubator. We have about 15 people who are doing basically research on various things. This kind of stuff. Yes?
So you mentioned that some of this stuff is already basically available on different implementations, such as, or different chains, side chains, whatever you want to call them.
The check sig from Stack is, yeah.
So is it true that most of that could already be done on Liquid and Elements?
Yes. So there's a viable alternative there. So if you wanted to implement this and you're a member of the Liquid network, you could put all of your cold storage on the Liquid network instead of on the mainnet.
So they already used basically the commandant type idea into to split the, because they have like each validator has a cold storage and the hot wallet kind of thing, and they already use the idea for the validators, right? So there's like the idea is already implemented, and the question is why you're looking at different things if it's already implemented. That like what's the
because it's not Bitcoin, right? So I mean, yeah, you could tie yourself to the success of the Liquid network, and maybe that'll be successful. But I mean that's a separate bet, right?
True, but like the idea would be that's already working, and we could do the same in Bitcoin. So in your perspective, would it be a good solution to just go with that because that's sort of proven, or would you still try a different option in terms of like on the Bitcoin blockchain?
Again, you know, there's precedent for check sig from Stack because it is used there, and as far as I know, nobody's come up with any problems with it. You know, if I had to guess which one of these opcodes could get into Bitcoin the most easily, it would be check sig from Stack. But I would really like to see people think about this more. In particular, let's assume we get check sig from Stack. How would you use this with Lightning? I've heard a handful of comments here and there about using this for your Lightning transactions. Some more specific exposition of how to use it would help make the case that this is the right answer.
Okay, I think that's it now. Thank you, Bob, and welcome to join us on the stage, please? Bob and James and who else? Please come up here. Thank you. Of course, grab your drink if you want.
Mouth is dry.
It's a Bavarian beer though, it's good. Okay. Welcome. Right, we're going to talk about the future of Bitcoin now, and Daniel, he's going to moderate our panel discussion with our high-style people. Yes, probably. I'm sure he's going to do it. Right.
Okay.
You feeling good?
Yeah. So, okay, great. Good. So maybe I take a chair. One chair. Yeah, I mean, it's really annoying for you. Can you move a little bit forward, because the beamer would be really helpful to collect all the questions. Because what you can do, I mean, I will start with some general questions, and then we will go over to all your questions. So if you have questions, please start to enter them into the Slido tool. Really easy to use. Also, if for all the YouTube listeners, please join us on Slido, ask your questions. We are. I'm happy to add them here. Maybe also, so before we start with the panel, I have some few annotations or a few comments to make. So first thing is Christoph from bitcoinblog.de is here. Yeah, he's over there. Yeah. So he wrote a beautiful book. It's mainly a big Bocker book, but no, just kidding. But it's really good read, but it's in German. So if anyone is interested in reading a German book about Bitcoin, about the history of Bitcoin, go to him. He has some versions available here for purchasing. Then tomorrow there are some workshops, and one workshop is the Cypher Full Node workshop. Which is being led by Jörg. And Jörg, if you are joining this workshop, please come to Jörg after the panel, because there are some details we need to figure out, like which would help to figure out today. And also, if you have some multi-plugs and network cables, please bring it tomorrow. This would help us for the organization. So then, of course, if you like what you have seen today, please let us know if we should. Yes. Okay. You can vote them up and down. so we have a common sense afterwards. So maybe we flag it out. Yeah, let us know what you think about the conference. If you should do it again. If you like the format. If you would like to see some improvements. Whatever. Use Twitter. Use the hashtag Bitcoin TechDays. @mention Bitcoin MOOC, or just send us an email to contact@bitcointechdays.org. Yeah. So before we start the panel, maybe let's bring in Kemal. So Kemal is kind of the person who is responsible that the Lightning node this evening for the party is working and has enough liquidity that you can actually enjoy some great cocktails like the 51% attack, and I'm pretty sure it has more than 51% of alcohol. So that you can pay with Lightning and with some extra discount. And he will, yeah, like take 2 minutes about his experience of setting it up and what, like, from a business perspective, what needs to be improved in order to make it more viable for businesses to use Lightning.
Okay, thanks a lot, first of all, for having us, this project, as the official after party. I want to keep it real short because we're already running late. We're doing this as a project called ideasarelikeflames.com, and we encourage physical stores to use Bitcoin and Lightning And since these are mostly non-technical people, we just give them support and advise them on the right setup. And coincidentally or luckily, we managed to convince the owner of Bikini Mitte, which is in central Munich, and it's going to be Munich's first Lightning Bar, and the kickoff is tonight. And
yay!
If you want to know more about how I did this and how we did this and how we convinced the owner and which setup we used, make sure you're at the party, buy your beer with Bitcoin, and yeah, see you later.
It's only 99,000 satoshis. Yes. Great, cool. Thanks so much. Okay, let's start with some questions, some general questions and some specific questions we talked before we go over to the audience questions. So of course there are some topics which are in mind if you think about the future of Bitcoin, and typically what comes up is things like scaling, right? Or things like how do you do actually governance? Who's deciding stuff here? And I would like to address these things. And maybe let's start with the general topics like who is actually deciding about something which is again coming up, like the block size, right? So we had this discussion. I don't need the microphone basically. we already had this discussion about increasing the block size. Now we have the discussion about decreasing the block size. If Lightning works quite well, as Luc Deschier proposed this 350 kilobyte blocks. So what is your take, or does someone have a take on decreasing the block size? In terms of looking in the long term on Bitcoin and the Bitcoin network. Yeah. Okay, Bob, thanks.
So Luke Jr. has been talking about this for a long time, and basically the motivation is that how many people have started a Bitcoin node here before? Raise your hands. How many people are really annoyed at how long it took to sync the chain? Yeah. So that's basically the motivation. So with segregated witness, maximally we could have like up to 2 megabyte blocks, basically. In which case, you know, the chain is growing faster than it was before, and after 10 years, we'd be looking at like a 2 terabyte blockchain. Now it already sucks. It's about 225 gigabytes now, and the motivation there is to try and prevent that from growing any faster. And the thought is that, okay, now we have the Lightning Network, maybe we don't need as many channels on chain. I don't know, personally I think this isn't going to go anywhere. I don't think the benefits outweigh the costs. Hardware is getting faster, storage is getting cheaper, and you know, 10 years from now we're not going to be fighting over 2 terabytes. But
someone else?
Yeah, so I basically agree. Luke has been saying smaller blocks already since there was the discussion of raising the block size, I think, and maybe even longer. And I think the current status is also already quite conservative, which I think is good, because like otherwise people won't just run a full node anymore or sync. But I don't think it's really necessary to decrease it anymore, because the current state is already working well for like my 6-year-old laptop, for instance.
I would rather we argue about things like, you know, what non-protocol changes we could do to make the situation better, like the node launcher, these different, you know, node in a box solutions. I think those are where the fights and the arguments should happen, and that'd be a lot more productive. And like the protocol changes is an absolute last-ditch effort, and we're not nearly there yet.
Okay, cool. Thank you so much. So also like thinking forward in terms of Bitcoin and what's going to happen, and especially if the price increases before halving and even increases massively after the next halving. Like one topic which is always coming up, especially in the mainstream press, is the energy consumption of Bitcoin, of course. And does someone of you have like this final statement, which I would say like forget it. Like, we don't need to care about this, or like does someone have an argument which puts like a decal on it? I don't know the English word here. Bob again. Okay, thank
you. There's a report that came out a couple weeks ago from a company called CoinShares up in London. They have the European ETF on Bitcoin. And according to their analysis, 78% of the Bitcoin network was powered with renewable energy, primarily hydroelectric. This is far more than any other industry, far more. And so the philosophy here is that Bitcoin is not, nobody's burning coal to mine Bitcoin, it's just too expensive. And that Bitcoin is essentially the energy buyer of last resort. We don't have any lack of energy on the planet Earth. Energy is just in weird places, right? The sun is beating down on us every day with many, many terawatts of power that we can never use, even if we wanted to. Hydroelectric dams in the spring, the reservoir gets full, and they have to just open the sluice gates and let the water run off because there's no buyers for the electricity. And so that's what's happened, is that the Bitcoin miners have come and said, well, I'll buy that electricity. And the hydroelectric dam says, well, I'm not going to make any money otherwise, so I'll take it. And that's going to continue to happen. I don't think we're going to see people investing in very expensive sources of energy, right? Bitcoin energy consumption has to be cheap, and this is not a problem in any way, shape, or form, but it gives us security for the blockchain. You need that expenditure of actual real-world resources to secure the chain. If it doesn't cost anything to attack it, the asset's not worth anything.
Okay, cool. That's it? Okay.
I think so. You're probably way better informed than me about this report and so on. But like even if people sometimes claim that in China there are miners with dirty coal or whatever, then that just means that the price of electricity is wrong, right? So if electricity is mispriced so that in China you can buy cheap electricity that is hurting the environment, then that's not a problem of Bitcoin itself, but it's just a problem that the market is wrong and that the price should be higher for the actual cost because it's subsidized or something like this. So it's just, Bitcoin is just a scapegoat for like problems that are elsewhere in some sense.
Thank you so much. Someone else? René, yes.
I kind of want to disagree. Like, I see your argument, Bob, and I think it's a good argument, especially if you, for example, look at Iceland. There's a lot of Bitcoin being mined and produced, and that's reasonable. But the problem is, it's still a lot of energy, and a lot of energy that could be used for other stuff too, and I think it is actually a problem that we should face. So I tried to estimate once what the cost for physical money actually is by looking at how many cash transports we have in Germany. And I was quite surprised that Bitcoin is actually way more expensive in terms of kilowatts that are being used. And then, of course, you can consider of where you produce your Bitcoin or not. But the thing is, Bitcoin is like a global ecosystem, but regulation happens in every different country. And then you run into problems that China, for example, says, yeah, we don't care, we just push in all the coal and there we have it, or oil, countries might use this oil. So it's just not that simple. So I think we as a Bitcoin community should be a little bit more honest about the problem, that this actually really is a problem, and we should not just ignore it and say, yeah, it's difficult, or it can be solved in a certain way. And in the sense of if we discuss energy, that people say, oh yeah, Bitcoin is really bad, I think we should proactively argue with this and find solutions.
Okay. It seems like that you opened the box again, so there is no really a closing for this box, and probably this discussion will go on for years and years until we see how it's going on and what will happen. But this actually leads me to research. I mean, if you think about what happens with energy and what could happen, or what impact could Bitcoin have on energy in terms of research, how to harness energy, but it also, like, research is all over the place in Bitcoin. Bob, you told us that there's a 15 people team researching on several things, like storing Bitcoin securely, and then we have Bob, who is researching. Sorry. Then we have Adam, who's researching on privacy, and of course René, who's researching on Lightning and how to root Lightning. And like there are all these researching approaches and implementation approaches. And my question is, well, it's less the question. It's more like a discussion. How can we actually manage this research? Or is there like something you would add to people? How can they get into research? How can they make money with research? And how can they make a living? I mean, René, you're making a living with research in Bitcoin, right? Well, you're trying at least, yeah. Maybe you start to talk a little bit about this.
Yes, so I think research is a really important fact. In the same way as education is an important fact, I might say. The problem is, in general, people kind of don't like to pay for it. Like, in the sense of, it's always easier to make quick money with a business model than investing in research and development. So one thing that I think is that research should go back to universities. Research usually is publicly funded. And nowadays, if you look at universities, there is a lot of blockchain programs arising. And the problem with those is that they are blockchain programs. They're not necessarily Bitcoin programs, because Bitcoin also to some degree has this like bad image to some degree, because it was first used in WikiLeaks or on Silk Road, and it sometimes has this like bad touch. So what we can do as a community is we can talk to politicians, we can talk to the ministries and ask them to spend more research money for universities that is dedicated specifically for university level research, and ask them to set the goals not to make some blockchain research but really Bitcoin research, or argue that if it is blockchain research it should be at least include Bitcoin research. So
quickly, how would you build that argument?
So yeah, I would probably build the argument in the way that I would say that Bitcoin currently is the most used technology, it's the most relevant technology. We could, for example, use the energy argument from before and actually admit to the fact that there is a lot of energy being used in Bitcoin. And the solution to it is not as simple as saying, yeah, let's just use a different proof of work algorithm, right? Because there's already an entire industry being built up on this. So I would use the argument of saying that Bitcoin is currently the most relevant cryptocurrency. I mean, that's what every other cryptocurrency is measured against, I would say.
Thanks. Adam, do you have something to add here? I mean, you're doing a lot of research in privacy, right? And privacy is like, it feels like it's your passion, and it's like similar to René, it seems like it's your intrinsic incentivized, but of course you kind of need to make a living out of it.
I think research should not go back to university, not in a way as it is done right now, because we have so many great tools, like just simply GitHub. Like right now, if someone gives out a research, a PDF, no one can really do anything with it except reading it, right? But they should upload it to GitHub, and then people could contribute, something like that. And I think we are researching in that direction, like with the Bitcoin improvement proposals and things like that. I really don't think the old school university research in its form should be forced on us, because we just cannot comment on it. And yeah, just recently I've seen that researchers are actually paying for making their research public, which is just interesting. I don't know.
Bob, can you listen to Bob? Yeah.
So, I mean, full disclosure, I spent my entire life in theoretical physics. I've been doing research forever. So first of all, if you want a job in research, we have several jobs open at Fidelity. Go to jobs.fidelity.com and type in blockchain.
Some people might have a problem with working for
that's
a
fine.
full-profit company and doing research.
Agreed. But I think it does make a lot of sense to tie a for-profit company to that research, and there's precedent for this before. AT&T had Bell Labs back in the day. Xerox had the Palo Alto Research Corporation, which were fundamental research organizations. Today, Microsoft and IBM both have big research labs which do pure crypto research, and I think it makes complete sense for an organization like ours to do that. Not promising that it'll happen, but we're already doing some research, and I hope to grow it. one thing that Fidelity did that I thought was very smart. So a number of years ago, there was this conversation, blockchain, not Bitcoin. You've probably all heard it. All the big banks joined R3 and Corda and Hyperledger and things like this. Fidelity did something smart at that time and didn't join any of those. Instead, they joined the MIT Digital Currency Initiative, the Cornell Institute for Cryptocurrency, IC3, UCL, Center for Blockchain Technologies, which are relationships I help manage, and we support those organizations. And so with that, they do fund graduate students working on research. The fact of the matter is today, most of the best ideas are coming out of universities. And I'm biased, I spent most of my life in universities, but I think that needs to continue. I think that the plight of someone trying to be an independent researcher is very, very difficult. There is a phenomena going on here that is essentially tragedy of the commons, right? Satoshi created his creation, which is now a many billion-dollar market, and it's a commons, right? It is. Lightning is too. The people that are creating it may or may not ever be paid. The companies could all go bankrupt, and we're still going to use Lightning, right? And so Grin was created entirely off the labor of people who were not paid for it. But these are going to be the most valuable things in the space, and there's a huge contradiction there. That the most valuable things in the space are the things that are not owned by anybody. But that's also why they're valuable. And I think we absolutely do have to figure out how to fund people.
Thanks. This brings me to the next question, which is probably directed to Justin, because if we have all this research and getting this content together from different initiatives, and be it private or coming from a for-profit company, how do you see how we pass on this information which is being researched in a way that people actually gonna be able to apply it? I mean, a lot of people, especially for me, the experience today, I talked to some people who today had the experience like I didn't understand anything, and it was like really hard for me to get a head start here. And how do we actually pass this information on, because it takes so much time to get into it, right, and to understand it?
Yeah, I think to a large degree, the things that the researchers focus on probably shouldn't. I mean, they probably shouldn't be communicated to the average user. It's just information overload, and they probably don't. I mean, the question is like, what are the important things that the lay person, the user, the developer need to, these are like increasingly sophisticated consumers of the Bitcoin protocol. Like, what do they need to know? And I mean, I think a lot of times the game is how to eliminate things that they don't need to know, because there's just so much that you could include. And so, I mean, so yeah, that's like in my role in the last few months attempting to train Bitcoin developers, I feel like most of the time I'm trying to throw things out rather than to add things. And I think that's true generally, is it's, yeah, I think you got to keep the message really pure, like focus on those, the few things that are the most important, and it's really hard to figure out what those are. That's my perspective. Like, it's really hard.
René, can you add something to that, especially as you're writing a book about with the idea to get people on board, right, and to educate people?
Yeah, I would agree with what Justin said. When I was in university, I always had a fight with my supervisor, and I would always say that in education, it's not particularly as important as in research to be 100% exact on everything. Right? Sometimes you want to make simplifying assumptions, or you don't want to tell the full picture in order to have it simple enough for people to understand the concepts. Once they understand the concepts, they can go out and read the research paper and get better educated on this. But you need to have this like head start thing where it's really difficult to figure out what are the important concepts and how to communicate them to them, right? So yeah, education is I personally think one of the most difficult challenges in general. How do you communicate knowledge? It's just really difficult, because also every learner has a different background, has a different perspective to the topic, and this is really tough. So one solution that I personally think helps to mitigate these problems is to be open in education. Right? You mentioned before that researchers have to pay to publish, and that's outrageous. Right? And this is not necessarily a problem of the university itself, but a problem of the publishing industry, and a problem of our government, how we regulate the publishing industry. But if we force academics and force educators who are paid by the public hand to publish everything that they do under an open license, well, at least everybody can have access to education. And this gives the power back to the people who want to be educated. And then, of course, we have to create good content.
This is a good closing in which, Bob, do you have to add something here? Okay, sorry.
So the publishing industry is kind of a nightmare. There's this thing that was invented at CERN where you could put stuff on the intertubes. It's called archive.org. This was a major reason the World Wide Web was invented, was to be able to put research papers on the internet, literally. So archive.org is now run by Cornell, but researchers can post to archive.org. If you need permission, contact me. I do have posting permissions on archive.org for my physics career. There's also iacr.org. These are both preprint servers, right? You're not going through a journal. The computer science field is rather weird in this respect because they generally submit to conferences, and then there's this whole thing that goes on, and professors are jockeying for position and who gets into the best journals and stuff like this, and it's all garbage, right? Just post your paper. But the second half of that, I want to admonish everyone here: read those papers, right? In this world,
and understand them, which is more difficult, right?
Well, yeah, but in this world, everything gets compressed into like a 2-second soundbite, and we end up bike shedding over the size of blocks and which hash function we're using, which really does not matter, and the really important concepts never get discussed. My approach to this is journal clubs. So everywhere I've ever been in my career, I've had a journal club. We sit down, we read a paper, beginning to end. You have to read the paper to come to the journal club, and you discuss it. But these papers are worthless if nobody reads them. So put it on yourself to actually read the paper, try and reproduce the math, try and understand the equations, and that's what's going to bring us all forward. And also I applaud the efforts of Justin and Jimmy Song and lots of other educators. The Chain Code Labs has a residency this summer. You should all apply. Of pushing this forward and educating more developers.
Yeah.
So I had a little experience with this. I set up a little reading group on the internet, and we read a couple Bitcoin papers, and one of them was actually the Lightning paper, and René joined us. And that was really interesting, actually, to get a group of people together and discuss it, just try to really figure out what's happening in the paper. The first time I read it outside of that, I didn't find the paper very good. Like, I didn't really understand it, and this time I think I did. So it's a cool experiment.
Yeah, sometimes you read the paper 2 or 3 times.
Yeah,
it's a fact.
Cool. This is good that you have the microphone again, because you led me to the next question, which is if you think about generating or doing research, publishing papers, but also reading papers and trying to understand papers, you need to have the motivation, right? And normally it's not always and not only a financial motivation, because I think basically every one of you could have done something else than Bitcoin. So my question here is, what especially makes you be interested in Bitcoin? And tell it in a story or in a short story that it can be inspiring for other people to look into Bitcoin in different ways. I mean, everyone has a different perspective on Bitcoin, right?
So everyone.
Yeah.
So what makes me interested in Bitcoin is actually the Lightning Network, so it's vice versa. I like Bitcoin, but I saw it has the problem of this scaling issue, and I was working as a data scientist thinking about how to scale architectures. And the way how the Lightning Network works was just mind-blowing for me. This idea of making something in private and have a contract that is enforceable by somebody. And this is really a strong intrinsic motivation for me to pursue this, because I think it's just one of the coolest technologies I have seen basically in my life. I don't know, the internet maybe, but yeah.
Cool.
Yeah, I'm really just about the limited money supply. I mean, the largest theft that someone can do is to print more money, and every country in the world is printing money like crazy. And well, this can change the world in a very, very fundamental way. So limited money supply. Everything else is just details. It doesn't matter. Limited money supply.
Yeah, I became really so I'm a capitalist. That's I believe in free markets, and I think they're very important. And so I became really interested when I realized that we had sort of a Soviet-style top-down market for money, which I never thought of. And so that's when so I see Bitcoin as a way to basically restore a free market for money, and I think that's really important. It's the most important market, the market that sort of intermediates all other markets. So that's what got me interested.
So I heard about Bitcoin first in 2011, but after the initial bubble, I only learned about that later. But when I learned about it, I was really fascinated that you could do something that I thought was impossible before, like doing a transfer of value without an intermediary. And at that time, I was really just fascinated by that you could do that, and I didn't really think that it could go mainstream in some sense. I mean, maybe it's not even now gone mainstream, but I didn't think that it would be relevant in practice. And I also bought too little, of course, because of that. But the tech was fascinated me, that you could solve this problem. You could solve double spending, you could build a money system that worked fully decentralized and fully trustless.
I agree with everything you guys said, but let me tell a different story. So my background's not in finance, and I spent a couple years in New York, and now at Fidelity. And there's a funny thing in financial institutions. Everyone will tell you a story about what happened in 2008, and their scars from the financial crisis in 2008, and what they were trading and how they were trading it. And a lot of the finance people who are in Bitcoin now looked at the situation and said, "This is just crazy," and there's a lot of really crazy practices that happen behind the scenes, I think, in finance markets. And one of the big causes of the 2008 crash was essentially loans upon loans upon loans upon loans, where there's effectively a double counting that's going on, where the person who's loaning money is counting the money as their asset. The person who's loaned money also counts the money as their asset. This should be illegal or something, but it's not. And this was the cause of a big part of the cause. Not your keys, not your Bitcoin. We can't do that with this asset. And this is a fundamentally different asset class, and there are fundamentally different properties. And if we do it right, we're going to provide a mechanism to provide protection against those other asset classes, which will have this problem again.
Thanks. These are really great words. Thank you so much, everyone. Before we go over to the questions from the audience, one special question which I promised to a guest here. This is Pierre Rochard 2 days ago twittered, Bitcoin's monetary policy is an attack on government inflation taxes, and Lightning's privacy is an attack on government income taxes. So I mean, as Bitcoin is already quite critical from an inflation tax perspective, if you call it an inflation tax perspective, then Lightning comes on top as an additional challenger. Would you say Lightning is critical, or it's like dangerous for Bitcoin in terms from a surveillance, or even from a perspective that a nation state would kind of prohibit or forbid Bitcoin? And if yes, is this a bad thing or not? Does someone have an opinion here?
Yeah, so I don't think we have to worry about that, because right now we figured out Lightning, the basic things. Now we are working on how to make it more user-friendly, and what kind of compromises we should make, what kind of trade-offs we should make, and these trade-offs are, many of them are about privacy. So I don't think we have to be worried about that it will be too private.
Bob, can you add something here? Someone who is involved in the financial.
I have one other
cool.
I think that in general most governments are very nearsighted. They don't look very far out in the future. And I think that if you take a longer view, Bitcoin's going to be waiting, and if you can always just wait out the storm if they come and attack it. Like that's what I would do.
I personally don't see any government attacks coming anytime soon. In many ways, Bitcoin is, as has been said, protection against hyperinflation and things like that. And every event that comes where there's hyperinflation in some country, there's a movement into Bitcoin, and it's not going to go the other direction, right? So over time, every country is eventually going to have a financial crisis. This is just going to keep pushing in this direction. I don't know, and we'll see. There are a lot of important projects out there. I'll call out the Blockstream satellite project, for instance, which would allow someone to continue to transact with Bitcoin even if the internet is cut. And so as time goes on, the infrastructure is getting better and better for us to actually protect ourselves from government attack. And we'll see. If a serious concerted government attack came, it'll survive or it won't. But we've certainly all learned a lot in the process, and if it dies in the ashes, we'll know how to build a better one afterwards.
Thank you so much. Great. So let's move over to the audience questions. I think the top voted question is destroy POS in 60 seconds, or proof of stake for everyone who doesn't know what POS means. Does someone want to take the chance to destroy it in 60 seconds? Seems like the physicist. Or even less.
The only way you know the chain tip in proof of stake is you Google it. This is the concept of weak subjectivity. In other words, the only way you knew the state is because you knew the state yesterday. And if you just come into the chain, you have no idea what the state is. It's very easy to destroy proof of stake by creating 10,000 chain forks. No one will ever figure it out. It's dead. Proof of stake is the assumption that it's proof by induction, right?
So you're talking about the nothing at stake problem, right?
It's different. This is weak subjectivity, right? The idea is, so Vitalik brought up this phrase into the lexicon, but the idea is essentially I can Google the chain tip and get the right answer. And that's just foolish. How many times have you Googled something and found something different than what you expected, right? The proof of work is immutable, right? Anybody can determine it without reference to any external state, any trust whatsoever, right? Proof of stake is a trusted system. You have to know who the validators are, or you don't know anything at all. And end of story.
René, do you want to add something? No. Someone else? No? Okay. Cool. Then let's move over to the next question. What is the biggest threat for Bitcoin from a long-term perspective? Probably 10 years plus. Someone want to answer this question?
How about quantum?
Quantum, yeah, maybe. This is a good question, yeah. Does someone want to answer the quantum question? Wasn't it answered today by Stepan already? No?
Oh. I don't know.
Stepan still here? No, sorry.
I don't know how to answer this question, but I'll respond to the quantum question. There's good reason to believe that we will never see a quantum computer. Making quantum computers is really hard. Entropy is not your friend. If you want to create a quantum state that has 256 bits of accuracy, you have to have an error on the creation of that state, which is 2 to the minus 256, which is a really small number. You have to be really, 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 really precise, right? And that's why quantum computers have to run at absolute zero. There are a lot of physicists that are very skeptical we'll ever see one. Error correction can only get you so far. Don't know. Maybe I'm wrong. Wouldn't be bad to prepare. We have good quantum resistant algorithms anyway, and it doesn't hurt.
And we can easily implement them if we have consensus.
Not so easily, but I think one of the things I love about Bitcoin is that it's a giant canary in the coal mine for the existence of quantum computing.
So maybe my opinion on that question is that there are maybe like 3 different things that could be a problem in some sense. One would be, I don't know, government regulation, but I think that's unlikely at the moment because Bitcoin is already quite big and there are already like a lot of institutions also and people who have interest in it, and I don't see governments trying to crack down on it. Then another thing would be like a fundamental problem in the protocol, or maybe a quantum computer. But I also think that it's like battle tested over time already. So hopefully we don't see it, and if something comes up that we have enough time to fix it, like maybe with post-quantum algorithms or whatever, And maybe the third threat or the third thing that could happen to like not make it successful is that it just isn't successful because no one cares, or like because it stays at the current state and it just doesn't solve a critical problem for like enough people to really reach another level of mainstream. And my opinion is that that's probably the likeliest thing to happen. But I also think that Bitcoin is really great, and so hopefully people will see that.
I want to add greed and herding behavior of human beings to it. So if the next bull run comes and people Google Bitcoin and they all come to bitcoin.com and buy Bitcoin Cash, you know, I mean, no, I'm serious. I mean, we have already seen how entire elections have been bought with fake news, and it's really incredible how small entities that are economically powerful are able to like drive a market somewhere or an opinion somewhere. So I think this is really an issue, and yeah.
Cool. Let's head over to the last three questions. The first one adds to the question we just had. I mean, it's kind of an evergreen, right? So it's I think this discussion will go on and go on until we see what's going to happen, which will probably be the case in 50 years or something like this. But how will post-block reward? I mean, post-block reward basically when the block reward is really, really low. Bitcoin play out. What are your thoughts on that? Do you have any thoughts? Should we skip that? Okay, we have some thoughts here.
we need really large blocks, otherwise we don't have a fee market, according to some people from the Bcash industry. Joke.
Good one. I think it's easy answer, right? We just pay the miners from the fees.
I agree. Like, I think there's this observation that we don't change Bitcoin, Bitcoin changes us, you know, and I think maybe now we like to have we like to pay hidden costs in our culture, and maybe Bitcoin will help us, will teach us to pay more explicit costs, and maybe so that's kind of my answer.
This is nice to hear.
So the context of that question is that there was a paper published a few years ago by, I think, some researchers at Princeton who showed that Bitcoin without a block reward is not stable. And the argument goes as follows. If you create a block and it gets mined, and the mempool is empty, right? I'm a miner, and the last block just got created. I've got no new transactions to mine upon. There's no block reward. My incentive is not to mine a new empty block with no reward. It is to orphan the previous block and try and steal the fees from the previous block. So that's a paper, I think the title is something like Bitcoin is unstable without the block reward. My response to that is that that's a long time away. Let's not worry about it for now.
Yeah, okay. Great, thanks. So let's stay with you.
I think I have to answer the next one.
Yeah, probably. You can read it?
Yeah, the question is, why did Fidelity Investments set up a custodial management service focused on Bitcoin? The short answer is our CEO told us to.
That's simple.
We are very privileged to have a very forward-looking CEO who, literally said, "Go do this." A lot of the other big finance firms have various conflicts. You've probably heard Jamie Dimon saying crazy things. There are people at those companies who are researching blockchain, but they don't have support from the top. We do. There's a lot of other things that have happened, in the meantime that I guess people didn't pay much attention to. But Fidelity's been mining Bitcoin for almost 4 years now. We have an integration with Coinbase where you can see your Coinbase balance on your Fidelity.com account, on your brokerage account. We have Fidelity Charitable, which started accepting Bitcoin and Ether donations for our donor-advised charitable fund. In 2017, we took in $70 million in Bitcoin and Ether. 2018 is probably less. I don't know the numbers top of my head. So yeah, it's been a long road. This has been in the works for some time.
Cool, thanks. So let's take on the last question. You don't need to answer it if you don't want to, or take it general. But what's your take on the best personal key management setup? Multisig with different hardware wallets, or Shamir secret sharing, or something else? What is your take on that? Like, if you don't want to share it, don't do it. But like anyone who wants to add something here can feel free to add your comment.
My answer is I don't know.
You don't know. Okay.
Yeah, I think today we have seen that hardware wallets in general are, you shouldn't believe that they are secure. So math on the other side is something that is pretty secure. So I would say Shamir secret sharing seems at least better than hardware wallets.
You guys watched my talk, Defense in Depth, right? Always have multiple options. If you're dependent upon one key for all of your assets, that's a bad situation. Multiple devices, multi-sig. The company Casa is creating something like a 3 of 5 multi-sig, where you've got 5 devices in different places, and you can lose one. And that's the situation you want. Multi-sig with a large number of devices is my answer.
Great. Cool. Last question from my side. Or do you want to add something? Sorry.
Yes, I just wanted to add that what did the Electrum developers say? Security that is not used is not very secure. So why am I saying this? Because in Wasabi wallet we did not get any reports of users getting hacked, but we get so much about losing or mistyping their passwords. So maybe that's the most prominent way how people lose money. They lose credentials. So maybe we should concentrate on fixing that too.
Thanks. Cool. Last question from my side, as I said, it's more like directed to all the developers here who are interested in becoming involved in Bitcoin somehow. So what is your advice from your own experience in the different kind of levels, like being involved in protocol, being involved in building something on top of Bitcoin, whatever it is, and being involved in research. So what is your take, and what you would what would you like recommend someone who wants to dig deeper into Bitcoin? René, maybe do you want to start?
Yeah, but I can only say for Lightning, just read the bolds. They are pretty well written, much better written than the white paper, much more informative. Double check this with the source code. I mean, there's many implementations nowadays, so it's much easier to read it. And then start with some issues on the issue tracker, because if you have a concrete issue, you can like check with the bolds and the source code of how stuff works, and then you get going and just be really, really motivated.
So I think you should go to work on an altcoin or a blockchain project, and after the next rally, come back to Bitcoin and have fun.
I think you want to find something, some specific thing that really like possesses you, that sort of pulls the best out of you, kind of like Adam's done with privacy, right? You can tell he really cares about it. And so it just pulls his best work out of him. So that's what I'd say is it's a search problem. You got to find that one, find one thing that will really engage you and bring the best out of you.
So my own experience have been that I've done best, or that it's, for me at least, it was the best approach to just do what I need, which means that like you can start writing like scripts that automate some things you want to do by using, I don't know, the RPC interface of Bitcoin Core, and then maybe like for me, I'm more on not on the Lightning side or something, but on the Bitcoin Core side. So basically, I worked on other projects or worked on things and wanted to do something, and it just didn't work the way, or there was like some difficulty because some feature was missing from Bitcoin Core. So then I just because I needed that, I went and tried to implement it myself and propose it as a commit. And I think that works better to like get you motivated and get things done than if you just say, I want to do something, so what can I do? But you're not actually interested in doing that because you need it or something.
I guess I have 3 answers to this question. First is give yourself a project. So make a Lightning payments app. Make your own blockchain. Give yourself a project that you're actually going to work on. Second of all, ask the experts. There are lots of forums in this space where you can find people. There are Slack channels. There's a Lightning Slack. There's
they're much
IRC.
more accessible than you think.
They're much more accessible than you think. Absolutely.
They'll always answer your questions.
Yeah.
It's amazing.
I learned everything I know from the Bitcoin Wizards channel, and Greg Maxwell and Peter Willa answered all of my really stupid questions back in like 2012, 2013. Those people are still around, and if you look for them, you can find them. It's always better to ask somebody who knows than waste your time in a rabbit hole. And the third recommendation is read some papers.
Cool. Thank you so much, everyone. Thank you so much for joining us today, and thank you for this great speeches you gave us today. And we're really happy to have this event together with you. And without you, it would not have been a success. So, Michael, do you want to add some final words here? No? Okay. Just thank you, right? We are all happy. And
thanks the organizers.
Yeah, thank you so much.
Mike is here finally. Come on here. It's one of your party as well. Sorry for that, but I think it was a great thing that happened here. Thanks for the sponsors, for the guys who are here. And it was really a pleasure to see all that happening in the Bitcoin community. And I hope that you have a lot of fun tomorrow for those who go to these workshops tomorrow. And hope to see you at the Bitcoin Munich events later on the meetups. Thank you.
Thank you too. One of my motivations for organizing these meetups is, a lot of us from Munich, we go to these Bitcoin conferences like Honey Badger, but I feel it's often just like preaching to the choir. And so my motivation is also to bring maybe make more developers in Munich here, in the local communities interested in Bitcoin with good events. So maybe when they come to meetups, or events, maybe they don't understand everything, but they maybe grasp some things here and there. And so I think that's just my idea of helping Bitcoin further.
Okay, some minutes for socializing, then hope to see you all at the bar for the kickoff. Bye.
Hello. Okay, we have one request. So if everyone who goes out just would pick one bottle or two bottles and put it into the kitchen, this would be really great and helpful. Thank you so much.
Probably the best way is to send me an email. What's your name? That's just my name, Bob McElrath. I don't know. R.